Hello, everybody. Welcome to today's Engine Professional Super Webinar. We appreciate you joining us. My name is Amanda Harmoning, and I am an admin assistant here at AERA, and I will be moderating today's event. Joining me from the AERA team is Rob Munro and Steve Fox.
Hey everyone, Rob Munro here. I look after membership and technical development over at AERA. Now I'm super excited for today's event. I mean, to have 4 presenters of this caliber to all get together for one event, it's a huge treat for us. So what we're gonna do is we'll have Amanda and Steve and we're all gonna be in the background. We're gonna help answer any questions you have throughout the webinar. Right now, I'll go over to Steve for a minute and let him introduce himself.
Welcome everybody to the first ever super webinar hosted by AERA. My name is Steve Fox and I'm the operations manager here at AERA. To begin, I'd like to thank those 4 industry leading professionals that are here with us today for taking the time out of their day to join us for this webinar, as well as you, the attendees, for coming along and taking time out of your day as well.
All right, well, let's get on with what's going to shape up and how things are going to look today. So what we're going to have is we're going to have introduce everybody here in just a few minutes. We'll let everybody get a chance to tell a little bit about themselves. Presentation number 1, that's going to be Lake Speed Junior Total Seal Piston Rings. There will be a Q&A session following each presenter. It'll be about 30 minutes long, and then we will have a small break. We're going to give away some prizes today. We're also going to give everybody a chance to grab a snack and just have a quick break if there is time. Presentation number 2, we're going to have Billy Godbold of Comp Cams. Then presentation number 3 is going to be Keith Jones of Total Seal. And our final presenter will be Ben Strader of EFI University. So we are going to leave time at the end. We will have right around 4:15 Central Time. We're going to leave time for a Q&A wrap up at the end. And we're going to bring everybody back on. So get your questions jotted down and get them in that questions box. And then we'll get those over to everybody at the end. So all right, well, enough of me speaking. I mean, let's get on with today's event. So Lake, Billy, Keith, Ben, how are you guys all doing?
Doing great.
Very good here.
Super.
Happy
well,
Friday, everybody.
Yeah, no kidding. Well, I'll let you guys decide who's going to go first, but yeah, just fire away and let's hear a little bit about what you guys got going on.
I am Lake Speed Junior. Thank you everybody for tuning in today. This is really incredible. Thank you for AERA for hosting us. For those who don't know me, during my presentation, I have a little bit of slide, but my dad is Lake Speed Senior, the former NASCAR driver. Also, kind of almost more famously, the only American to win the 1978 World Go-Karting Championship, and he beat a guy named Ayrton Senna that people said was a pretty good race car driver. Keith and I had the chance to go to the Phoenix Art Museum, but about 2 months ago, I guess it was, Keith, and see the Legends of Speed, and they had this fantastic exhibit of all these legendary cars and stuff, you know, that from early Formula One cars, you know, Grand Prix cars, Le Mans, the actual car that won Le Mans, the GT40, and things. Yeah, so got a motorsports background and history. I'm a certified lubrication specialist, member of a group called the Society of Tribologists. There you go, Ben. And lubrication engineers. You can keep it count, right, Ben? You're gonna keep count today. Obviously, the 4 of us know each other pretty well, and we're going to probably joke around a little bit. I think that's one advantage of this format is that we don't have to be maybe as formal. We can be a little more informal, and I hope that's going to be the case, especially with the Q&A. That's one of the reasons why we wanted to have more open Q&A to hear from you and make it more interactive and not just us talking all day at everybody.
I'm Billy Godbold. I've been at Competition Cams for 25 years over the Valvetrain Engineering Group, for at least 24 of that. Background's a nuclear physicist, so if you ever need somebody who can put the fizz into a soda pop, I actually have a degree in that. You know, just very excited to get to talk to everybody today, share a little bit about what's going on, try to do a broad-based presentation, scrunch it into 30 minutes, see what questions pop up, because I'm hoping I'm going to go through the slides fairly quick. I hope we'll be able to go back and look at stuff and have some good Q&A, especially at the end with this whole group, because we really are good friends, and it's fun to hear all of us kind of talk about the same subject at the end.
Hi, this is Keith. I've been with Total Seal 24 years. I'm the Director of Technical Sales. Originally from the Chicago area. Grew up in a racing household, always been around this kind of stuff. Old man ran gassers back in the 60s, hung out at Arnie the Farmer Beswick shop, Mr. Pontiac. So kind of got a little Pontiac blue running in my veins, but I appreciate everything out there. Here at Total Seal, we are gearheads. We are racers. I mean, from Matt Hartford, our CEO, running NHRA Pro Stock and setting the new record in Florida, which was, so impressive. These guys worked so hard over the years to get where they've gotten. It's just very unfortunate because of COVID that the season's delayed at the time. But my point is, we're very active in this. We don't just manufacture parts. We race what we make, and we enjoy the heck out of doing it. And as Billy said, they're fairly short presentations, so we're going to try to pack a lot into a short period of time. So hang on, it's going to be a whirlwind. But please ask questions, put them down. We love answering the questions. And your question will lead to another question that we may have not thought of. So, like I say, don't be afraid to raise your hand and ask a question. We love it.
Right on. Hey, everybody, I'm Ben Strader over here at EFI University. And I'm just thrilled to be here with all of you guys and with all of these guys because, I feel like standing in the presence of giants. We started this school 17 years ago now, and the original goal was to teach people about EFI and fuel injection and engine tuning. But over the years, while that's been really great for us, we recognized that the demographic had changed. When I started this program in 2003, what we had was a bunch of engine builders that were used to carburetors and distributors and maybe were really intimidated by the computer thing. And so there was a huge hole in the market. And, fuel injection has been unbelievably good to me over the years. It's taken me all around the world, met some amazing people. I got caught up in groups like this, and it's provided a lot of opportunities that maybe I wouldn't have gotten otherwise. But along the way, I noticed that the trend was changing, and, where it used to be older guys that were building engines and not sure how to tune them, what we started to see was a lot more younger guys who were really computer savvy, but sometimes didn't know the difference between a crankshaft and a connecting rod. I've literally had, 15 and 16-year-old kids come through our program, and they know all the buzzwords, they know all the terminology for computer and tuning and hooking up a laptop, but lack a real fundamental understanding of how the engine works. And so we started to add to our program a few years back, probably 4 or 5 years ago, and now we have a complete engine development program. And that's led to opportunities to work with guys like Lake and Keith and Billy, and we've all been friends a long time. And so it was just awesome to go from, hanging out to each other at the trade show with each other at the trade shows to now we get to actually work together and do meaningful research and projects. So I'm super thankful for that. I'm glad to be here with all of you guys, and I hope that whatever I have to add today will bring value for you guys. So I'll shut up and give somebody else the mic, and we'll get going on this thing.
Super, guys. Well, we got a few minutes before Lake's first presentation. So, Lake, let me ask you, I kind of noticed, I was on your social media stuff there, and you were working on a little 250cc engine, and that looked super cool. So maybe just share with us, like, what are some of the projects, and I'll start with Lake, but what are some of the upcoming stuff we can expect? What have you been working on, or what's coming down the pipe?
Well, that was, like I said, yesterday. I was over at my dad's yesterday, which is kind of funny. Walked into Dad's shop yesterday, and he's back in the old cylinder head porting room, and he's got the die grinder in there porting a cylinder on a 2-cycle engine. So I got a couple of slides in my thing just to say how Dad's doing. But so the old engine shop at Lake Speed Inc. is, if you don't know, Dad, for most of Dad's career in NASCAR, he was owner driver. So we had our own shop, built our own engines, built our own cars, all the stuff. We actually have the car he won with at Darlington in '88 still there in the shop. It's just got a Thunderbird body on it. So Dad's, we're full on head over heels into this vintage go-karting stuff. I was telling Keith the other day, I got to get some videos for him. We've got these twin engine 135cc go-karts that are just super fast, wicked cool, and 2-cycle on methanol. I mean, the sound and the smell of these things is just phenomenal. The smell of castor bean oil in methanol in the morning, and that little chirp, little crickle crass sound of a 2-stroke is just fantastic. So Dad's working away on that, which again, all of us together, I was like, hey, wait, he was getting that thing together because he was going to send it out to get it Nicosil coated, because it was basically too big now and to keep the bore stroke ratio he wants. He's going to send it up to Millennium to get it coated. And I'm like, hey, when we get it back, let's grab handy dandy profilometer and let's check it to make sure we know what the surface finish is, which we're going to talk about that more today. All of us probably will, just to make sure we've got a good handle on what we have baseline now when we get it back from Millennium, because Millennium's going to be the one honing it versus us. We can compare the notes to see what that surface finish is of what Millennium sends back versus what he's normally doing. So that's some kind of fun stuff. So we'll be showing that, right? So that's one nice thing about being at Total Seal now, which, is fantastic, because I can take everything that I learned at Gibbs, at Driven, working with Billy and Ben and Keith, and we can bring it all together, and we're going to be showing more of that. It's kind of like what Ben's doing with, his competition engine development program class, which, by the way, is super, super cool, because you're taking an engine like Spinal Tap, like the Small Block 40 did, and you're showing everybody what it is. It's not being secretive. It's not being hidden away where you can't be seen. That was one of the coolest things that Matt was doing, last year, and hopefully we get a chance to do maybe some more of it this year. Like the videos on Matt's social media where he took Joe Costello and he's rebuilding a clutch, rebuilding a transmission, changing the valve springs in a Pro Stock car. Stuff that is super secret is being shared. So that's one really cool thing that I think people have to look forward to, is that, we're learning through all of this, and we're taking advantage of these kind of platforms to be able to show what we're doing and not keep it hidden in secret, so that people can access it. So guys, like Demas that was in the class and Marcus that were in the class can make that step from, I know computers, but I don't know engines necessarily, to make that step and be able to move forward in their career. So we have a next generation of guys to do this.
Hey, Lake, that two-stroke thing, is that why I have this weird engine in my desk that doesn't have a camshaft in it? Like on a mount, like a profilometer would stick up in there?
Yeah, that's what that was for.
It's a kind of blasphemy to send a two-stroke engine to a cam guy, isn't it?
Yes.
Unless he's a nuclear physicist.
True.
I've been looking for where the cam goes for a while.
Can you make a fizz?
How about you, Billy? What's coming down the pipe at Comp? What is some of the stuff you've been working on?
Really, this has been a super exciting time. We've basically gone in and turned everything that we're doing on profile development kind of on its head the past 5 years. Ben was a very early adapter to that, probably because of necessity. We kept blowing up his Spinal Tap engine, and now that's kind of going on through the masses. Really starting to learn about and talk about designing packages as systems instead of components. I think there's a lot of misconception about components versus systems. Keith and I will both be talking a lot about material technology and about tribology, surface engineering, especially surface engineering and materials. And everything is just growing at such an amazing rate. It's hard to imagine. Ben showed me something that was 4 years old. If you look at 4-year-old technology versus what we have today, the 4-year technology it makes you look at it and go, well, bless your heart, you're still running that. And I had a friend stop one business, went to another. He wasn't gone 18 months, and by the time he came back for a professional type engine, everything that he was running then was obsolete now. So it really is. It's a super cool time, and we're excited to talk about it today.
All right, and how about you, Keith? What's going on in your world right now?
Well, kind of like Billy said, I mean, it's an unfortunate situation that the country is in, but it's found a lot of people with a little extra time on their hand, and it's allowed us to work with these guys to develop the next generation of parts, as Billy was saying, working on material technologies, coating technologies, and just ring designs. How far can we push it from our gas ported rings and our total conform rings? There's guys out there that's like, hey, we're busy, but we're not that busy. maybe we can finally try some of this stuff. Maybe we can, do proof of concept and get it out there. And we work with a lot of different customers, besides our own abilities. We depend on a lot of different people because there's a lot of different kinds of engines out there, from, F1 all the way down to a karting engine to, everything in between. And working with these guys individually, we're able to get some new designs out there and things that we think will work, but get them in real hands and real applications, because there's no better feedback than the real world. We can run it on a dyno, do all that kind of stuff, but trust me, the things that we think are brutal and the things we think that we could do to damage it, not even close to what happens in the real world. Trust me, if they can break it, they'll figure out a way to do it. So it's been, we'll say it's an unfortunate situation, but a fortunate situation, because it's given some of our very valued partners the time to work on some new projects.
Okay, and Ben, I know your world's probably changed drastically with virtual learning and that kind of stuff right now. Maybe just share what, how's that going?
Surprisingly, it's going pretty well. We were pretty nervous at first when they closed everything down, because I'm a firm believer in that there's never going to be a replacement totally for live, in-person, hands-on training. We were joking earlier about it would be really tough to teach somebody how to use a feeler gauge online. Hey, this is what it's supposed to feel like, and so for us, that's been a little transition. Now, luckily, we've been doing some online training for 4 or 5 years now. And so while our live and in-person stuff obviously ground to a halt, our online stuff luckily has taken up the slack for us. But the benefit to having all this spare time is we never run out of projects here. I say all the time, at EF University, we only teach the things that we want to learn. And what I mean by that is I don't really consider us an engine shop. We have a few, but not very many actual engine customers where we build and supply racing engines for them. But we build engines on some of the highest levels out there, primarily for research and development, so that we can learn the things that people want to be taught. So, it's not just using the same old curriculum that we were using 20 years ago because people will pay for it. If we get stale, the whole industry starts falling behind. And I think Keith touched on exactly that. One of the greatest things that happened last year in NHRA Pro Stock was somebody had the guts to finally step out of, Pro Stock is super voodoo magic, chicken bones, top secret stuff, and say, hey, we're going to take the valve covers off and let you do it. And that's kind of what we do here. We try to build the stuff that everybody else is afraid to try. And we're in a unique position to be able to do that, because our engines don't have a deadline or a customer that's waiting to make a race. So most engine shops, unfortunately, just can't afford to take a chance on new technology. They don't know what's going to happen, or the engine is a series of dependent events. So I might have this thing over here that's good or that's better, but if I put it in my engine, it might not mesh well with 20 other things. And so as an engine supplier, I can't afford to take that risk. But as an R&D house, which is basically what we are. I mean, we have 4 dynos in the building. We have 2 roller dynos, a hub dyno, an engine dyno, a spintron, CNC equipment to do some of the machining work, and plasma table that we can make and try stuff. We have the advantage that unfortunately a lot of people don't, and that is we don't care if it blows up. And some days we're actually rooting for something to fail, because I've never learned anything on the days that everything went right. If we build an engine and say it should make 600 horsepower, and we put it on the dyno and it makes 600 horsepower, we didn't learn anything. It did what we thought. It's when we put it on the dyno and that 600 horsepower engine only makes 490, and we go, what just happened? And we dig in and we start researching and learning. That's the advantage that we have at EFI University, and getting to work with people like Lake and Keith and Billy and the Pro Stock teams that we get to work with and the NASCAR guys that we get to work with allows us to have access to information that isn't shared publicly hardly ever. And so it gives us an avenue to package it and give people access to stuff that previously just seemed like mystery and magic. So all this time we've been sitting around, not sitting around, but waiting for the world to go back to work. We've been grinding away, building engines and testing stuff and running the dyno and trying to wear stuff out. So it's actually been a super exciting time for us. And frankly, I can't wait to go back to doing real classes and share some of the stuff that we've learned even in the last few months. Billy said, if you got stuff that's 4 years old, I'm sure it works and it's good. And we're not saying you should throw it away. But frankly, if you have camshafts or valve train stuff that's 4 months old, there's probably newer stuff out there. And so we're really proud to be a part of that and get to play with all that new stuff. And sometimes it doesn't work out. Sometimes we end up having to build a Spinal Tap engine 3 times or something like that. But the reward is always worth the effort, and I'm super stoked to be able to do it.
I just want to touch real quick on what Ben said. This is a very common thing that I hear right now in this time, because there's so many, we'll say, crazy ideas that we come up with, that we work with a customer. Hey, what do you think? You want to try this? I really think this is going to work well. Let's see how it does in your application. And I'll call them in a few weeks. It's like, hey, what do you think? Well, we haven't had time to touch it yet. And then a couple months goes by. Well, we haven't had time to touch it yet. And what's happened in the economy of racing is, 4, 5, 10 years ago, pick your time frame, especially in the circle track world, these guys would have 4, 5, 6 engines in their trailer. And when they got back into the area of the engine builder, they might drop off 3 of those engines to be built, come back in a few months, pick them back up. Well, today they've got 1 engine. If they're fortunate, maybe they've got 2. So that engine hits the door on Monday. They expect to pick it up on Thursday and go racing. So the ability for the builders to actually test and do R&D and develop has diminished greatly. So this time, again, as unfortunate it is, has given a lot of them the opportunity to do the things that Ben does passionately, and test things and try things. And I think coming off of this, as the world gets back to some kind of a normal, you're going to see some big jumps in power. I have some customers reporting back that, things that they finally tried, and it's like, wow, that really worked. Can't wait to be able to put that into my package. But, from a time point of view, they've had to make sure that what they did was reliable. As Ben said, there's so many things that, it all works together. It's all links in a chain. And if they throw one bad link in there and the whole thing fails, well, that's an engine build-up, and they've got an upset customer. So now they've been able to test it, try it, prove it, and it's going to become part of their package. So there is an upside and a down world this time.
All right, super guys. Well, what I'll do, I'm going to throw things back over to Steve here for a minute, and then we'll be able to get on with the first presentation. So here you go, Steve.
All right, thank you, Rob. So today we're going to start things off with our first webinar. The presenter will be Lake Speed Jr. from Total Seal Piston Rings. Lake will be speaking about what is tribology and why you should care. So without further ado, I will turn it over to Lake for his presentation. Lake, it's all yours.
Thank you, Steve. Appreciate it. Thank you again, everybody joining. I've been watching the counter, everybody coming up. It's been pretty awesome to see this many people coming on board and watching today. So hopefully everybody's in for a great day. It's going to be a fantastic day. So let's go ahead and get on with it. Pull my screen up here. Just for anybody that's tuning in later, I didn't know, I am Lake Speed Jr. I'm with Total Seal. I was, previously at Driven, before that at Joe Gibbs Racing, and my dad is Lake Speed Senior. And as I had kind of teased earlier, how's my dad doing? Dad's doing great. The little picture of the shop there, all the vintage go-karts and the modern go-karts, and we got the engine dyno and the run-in stand. So getting to have a whole lot of fun there. Spending time with my dad, one, is really great. The fact that Dad's an engine guy at heart, that's one thing I noticed. I've really learned about my dad is that, yeah, he's a driver and people know him as a driver, but walking in there yesterday, seeing him in there, porting a cylinder, porting a cylinder for that 2-cycle engine. He's an engine guy. He's one of us. That's what he loves, the making the power and working on it and having the dyno and everything. So looking forward to being able to spend time with him, and then be able to take that information that we learned from that and share it with you, and be able to give you detailed data, detailed engine build specs, what we have for back clearance, what we have for end gaps, where we're changing ring packages or something, and give it to you so that you can have information to action on. That's the goal. And so with that, let's get on with what is tribology, right? It's a big word, and really what it means is the study of friction, wear, and lubrication. And one thing I really want to make clear, and I know Keith's going to hit on it and Billy's going to hit on it today as well, is that, tribology isn't just about oil. And people know me as the oil guy, but really don't limit me just to oil, because really at my heart, I'm a tribologist. And tribology is friction, wear, and lubrication. And just to throw another curveball at you, lubrication isn't just oil. Just let that sink in just for a second. If we think about lubrication, you think about oil. You think about that stuff in a bottle, magic mystery. But dry film lubricants, coatings, those are lubricants as well, grease. So lubrication isn't just oil. So make sure as we go through today's presentation and we ask questions, let's not limit the idea of lubrication to just oil, and understand that friction and wear and lubrication also involve understanding materials, surface finish, and then the chemistry and how they all relate together. It's that bringing those together, that synergy, kind of like Billy was talking about. It's not just about components, it's about systems. Think about lubrication and friction and wear as a system. It's the tribological system. It's why I love piston rings. I had no idea how much I love piston rings until I came to work here. And I'm like, I absolutely am in love with piston rings, because as you will see, it has a fairly unique role in your engine. So with that being said, let's move on. So stages of lubrication, right? The Stribeck curve is really the key to understanding how all of these things, fit together. And you're going to say, wait, you're talking about oil here, and you just said lubrication isn't just oil. I know. Just bear with me. Let's just walk through it and we'll get into all the details. So without any lubrication, with no lubricant, you're going to have a high level of friction and a high level of wear. If you look at that very first slide where it says no oil, and as we all know, there are no such things as completely smooth surfaces. There's always peaks and valleys. Now we can go through a lot of different things. We can use a device like the profilometer to measure that surface. And then we can do a lot of different things like Billy's with the MSC process to be able to smooth that surface. But still, there's always going to be some peaks, some valleys. And that's not a bad thing, by the way. Having the right surface finish, the right ability to hold oil is going to be key. And I know Keith's going to talk about that, which is why I wanted to talk first, because I think a lot of what I'm going to talk about will basically help set the stage for what those guys talk about. And in the end, hopefully we all have a good package, better understanding how to make more power, better efficiency from your engines that you're building. So with the idea being no oil, high friction, high wear. When you add the oil or any type of lubricant, you want to try to maintain that full film lubrication when possible. But that's not always going to be possible. And then you move into the mixed film, which is where you basically have barely a film, where those high peaks begin to contact each other, but there's still valleys in between where you don't get the full film effect going on. But then you've got they call the boundary condition. The boundary is where the oil film itself can no longer support the load. Essentially, the load is so high and the speed is so low, or relatively the two, that you're going to have that metal on metal contact. And that's where the additive package or any kind of dry film lubricant or coating, that's what's going to provide the protection. And that's really what the Stribeck curve is all about. So let me kind of walk through each of these stages in a little more detail, because it's really important to understand them and their place in the engine, because you can kind of see there on the chart over to the right side of the screen that your valve train is going to pretty much live in that boundary to mixed film lubrication stages. Whereas the engine bearings, they're going to live in that full film. But as I mentioned, piston ring, my favorite thing in the engine now, it lives in all three. It experiences boundary, mixed, and hydrodynamic full film in each engine cycle. You think about it, what does a piston have to do twice each stroke? It's got to stop. So for it to stop, it's got to basically come to, it's going to be at mid-stroke, it's going to be at full speed, right? The highest velocity. And then from that mid-stroke to TDC, it has to slow down. So as it slows down, approaching TDC on the compression stroke, what happens? You have building cylinder pressure because you're compressing that intake charge. As that cylinder pressure is increasing and my speed is decreasing, what's happening is I have load increasing, speed decreasing, which, as you can see, the calculation there for the Stribeck curve is viscosity times speed divided by load. So I have decreasing speed, increasing load, the oil viscosity is staying the same. So what happens is I go from full film to mixed film to boundary. That happens twice every stroke. So a piston ring really sees everything in terms of lubrication, which is why I love piston rings. Because I'm a tribologist, I love tribology, and a piston ring is just living in tribology his whole life. So anyway, might I digress and rant? That's not why you're here. Let's move on into the more detailed discussion of each condition. So your full film hydrodynamic, and the best analogy I can give for these different stages of lubrication, if just the visual charts don't do it for you, is water skiing, right? If I go out and visit Ben, in Lake Havasu City, Arizona, I would love at some point in time for me and him to have enough time where we're not just thrashing busy, on the hub dyno or the engine dyno doing a project, to go water skiing, because Lake Havasu is huge. And I grew up water skiing. It's one of the things my dad had me doing early on was water skiing. If you think about water skiing, when the boat is stopped, where's the skier? It's down in the water, right? Then as the boat accelerates, the skier comes up. Well, once the boat's at full speed or cruising speed, and the skier's up on water, right? So you've got the skier on the water. That's that full film hydrodynamic lubrication, right? The ski is riding on top of the water because for the speed and the load, now you're up there. A good comparison is he's now 18 years old and he's bigger than me, right? But when I first started talking about this stuff, he was a lot smaller. And my son Ben, when he was little, he would go out there and water ski with us, right? But Ben could pop out of the water really quickly on 2 skis because he weighed half as much as I did, and he had 2 skis, so the boat could just pull him right up very easily. But when I go out there to slalom ski, I had twice the weight he did on half the surface area because I was on 1 ski. So the boat had to go a lot faster to get me up there. Hopefully that analogy is kind of helping make sense and ring true on what's going on here in terms of that full film. The mixed film is that transition state, right? We know that, when the boat's not moving, the skier's down in the water, but you don't just go from stop to moving, right? There's that transition stage where the boat begins to accelerate and the skier comes up out of the water. And that mixed film is that transition state. And a good analogy inside the engine for that mixed film is a hydraulic roller lifter, or even a solid roller lifter for that matter. The wheel in contact with the cam isn't actually in full contact with the cam because there's actually some deformation of that wheel right there at the surface. It's like a tire on the road, which is why, if you think about it, why does this slick tire not work well in the wet? Well, because it's got all that contact, and what's going to happen is it's going to deform, and then you're going to have the water on the road acts as that lubricant, and it's going to separate it, and then it can lose traction. Okay. Same thing with this mixed film condition. What you have is you have the peaks touching, but the oil inside that's trapped in those areas in between, the pressure on that oil is so great that the oil can actually become solid. There's a thing called the pressure viscosity coefficient. And Billy and I spent a lot of time when I was at Driven working on this, understanding how the pressure viscosity coefficient has an impact on things like valve train components, like hydraulic roller lifter wheels, push rod tips, and the such, is that as that pressure builds in that contact zone, you think about that wheel as it rolls over and it flattens and it traps the oil in there, and you have all the dynamic forces of the valve train pressing on that area, the viscosity of the oil increases. And not all oils have the same rate of increase. That was one thing we worked on, was finding an oil that wouldn't go solid so that it can't flow, so that it can't cool, but one that also just didn't stay fluid to the point that it just got pushed right out. You wanted one that had this kind of gradual progressive slope, so that the harder you push on it, it would just maintain that viscosity increase to maintain that film, so that you don't have it too slippery, but it's also not building enough film as well. So that's the mixed film. And then your boundary condition, that's where it's on the additive package, which when the best example, not an analogy, the best example of that we all know is the flat tappet zinc fiasco that happened 15 years ago plus, and we've all had to solve that, and we've been able to get a good handle on that. That's where the issue, where in that boundary condition where it's metal on metal, the only thing that prevents wear at that point is an additive film. And that additive film can come either from a few different sources. It can come from the additive package in the oil, where you're using the oil to be the delivery device to bring the additives to the surface. Under heat and load, they react and create the film on the surface, or you can put a coating on it, right? We'll talk about that in a minute. And that coating is what's going to be able to provide the protection. So that boundary condition is going to be typically characterized by very high loads, very low speed, which is, thinking about the valve train we were talking about earlier when we were looking at the Stribeck curve. One of the key things about the valve train is we all know that it runs at 50% of crankshaft speed. So, and you have valve spring pressure, so you have static load to overcome. So when you have higher load, lower speed, you're going to be in that boundary condition, in the valve train, whereas on your engine bearings, they don't have that same load. They have much higher speed, so they're in the full film. So understanding what's happening where in the engine from a friction wear lubrication perspective is key to being able to help to unlock the potential of the engine, to be able to know what tools to pull on, what levers to pull in order to be able to effectively increase the performance of the engine without risking damage to the engine. Like we said before, additives aren't just things in oil, right? A lubricant isn't just a fluid, right? It's not just an oil. The PVD coatings that we apply to, say, a ring face, be it, moly or tungsten carbon, WCC, or chrome nitride, these are different coatings that can be applied, DLC, for a lifter, which, by the way, I've got one, right? So that's one thing that made these lifters so successful in NASCAR, is that the DLC by itself lowers friction and reduces wear, because we've taken a tool steel part and we've DLC coated it. That DLC, when the surface finish is right, again, jumping ahead, but with the correct surface finish, the hardness of this part and its carbon nature, it's its own dry film lubricant, just like you're seeing on the slide there with the PVD. So you want to think about tribology and how we increase the efficiency of the engine. And it's not just about lubricants by itself. This was part of a system that we worked on at Gibbs. I mean, we designed the oil to work with these components, these coatings, as well as the surface finish. So it was material, surface finish, and chemistry, because the coating was part of the chemistry. That was part of that big, synergy we were looking for. And that's really how, everybody in NASCAR at that point in time was able to raise the game, in terms of RPM and reliability of those engines, there in 2004, 2005, that era when things really took off. So again, just kind of reiterate that grouping of face coatings that we apply to rings, and understand how those ring coatings are very similar because they're all PVD, just like DLC, which is obviously one of the ones on the list. And we also have hardness too. So they can impart different characteristics that you can, again, utilize. Something like moly, which is a good, low friction, but it's also pretty soft, right? So when you go to, say, a Nicosil liner, like you mentioned, Rob, in the 250cc engine that we're working on at Dad's, that's a Nicosil liner. So one, it rules out the use of chrome, because chrome is going to have some nickel in there, and that's Nicosil. So the electrofusion chrome contains nickel, and nickel doesn't work well together. You're going to have welding, so you have to go away from that. So one of the things that Keith and I are looking at is, okay, different coatings we can put on the rings for some enlightened Nicosil or Alusil in order to be able to get lower friction, better performance, and still have material compatibility. The things aren't just in oil. We can utilize the coating technology to help move that along. So this is kind of a summary of a few different ideas of different coatings you can use to help affect that surface, chemistry wise, from not just an oil perspective and additive wise. But let's go ahead and move on to the next one, which is surface finish, because I want to make sure I'm doing okay time wise here. I want to get through everything. So the surface finish, like we were mentioning on the DLC lifter, if this was very rough and you DLC coat it, all we made is a diamond cutting tool, right? Because it's going to be extremely hard. You can see that Diamond Light Carbon had the hardest, Vickers rating, or in this case is 2,500 Vickers, right? Very, very hard. If it's very, very rough, it's a cutting tool. And you don't want that, obviously. So when you look at surface finish, there's a couple of things. One, that roughness makes it more abrasive, and that's not a good thing. The other thing is load carrying. When you have all high peaks, it's kind of like doing push-ups on your fingertips. And I'm sure people who've heard me talk before have heard me make this analogy, but it's really key that when you have that real rough surface with all those high peaks, all the load is then hitting the peaks. And that really gives you a couple of things that are going to happen, from a tribology perspective, why that's bad. One, now all the load's concentrated here, which means viscosity times speed divided by load. Well, now I'm going to be pushing those areas here into the Stribeck curve, right? So I'm going to be shifting into a higher friction, higher wear perspective. And the other thing too is it makes the oil viscosity have to be thicker to try to move it back into a lower friction, lower wear regime. So it's easier to lubricate full film, low friction, low wear, a smoother surface. So if I have a smoother surface, it's easier for my oil film to protect it. Number two, it also distributes the load so I can carry more load, which also means less fatigue of that part. One thing I'm sure Billy's going to talk about that he taught me that I learned in working with him is all failures start at a micro level, not a macro level. It's these peak-to-peak contacts. That's where the chemical bonds between the grain structure, that's where it's going to break. It's the contact fatigue. We think about like fatigue pitting. That's where that same point, that same grain structure is being pushed over and over again, and finally those bonds break, and then that micro pit occurs, just like a pothole. Over time, it just gets bigger and bigger and bigger and bigger, and then you have the big macro failure. We see the macro failure, but it really originated at a micro point. So it's these little bitty surface irregularities are the key to preventing the big failure down the line, which is why surface finishing and understanding your surface is so critical. Again, I know Keith and Billy are going to beat this point to death today, but I'm going to beat on it a little bit more here. We have 8 more minutes. That's Billy's profilometer there at Comp that I used tons to do cam break-in testing with. And one of the things that I want to kind of point out here on the slide is that, okay, the slide to the left there, if you look at the middle graph, right, this is the flat tappet cam before and after break-in. If you look at that kind of that middle to the bottom slide down there, you can see that surface roughness as ground pre-break-in. All right, so then we're going to put on assembly lubes, we're going to put in braking oil, and then we're going to run it. And what you see when you look at the one on the right you can see that there's still some valleys there, which is key because those valleys will hold oil. It's important to have some surface irregularity, some roughness to hold oil, because as we were going to cover in the end, proper lubrication is right oil, right place, right time, right amount. So you can't have a surface so smooth that it's devoid of any ability to hold oil, but you don't want it so rough that everything's point loaded, because that's going to increase friction, increase wear, cause fatigue problems and things like that. So you can kind of see pre-break-in, post-break-in, as everything kind of breaks in, smooths out. You can see that transition. A few weeks back, the guys from Line to Line did a seminar with AERA, and one of the things I really liked about their abradable skirt coating is that it can kind of show you in this slide that change, that when you have something that's very hard, thin coating that doesn't change, that say the skirt profile, all that load is being concentrated at the highest area. And that thin, hard coating doesn't change that much, but with their little bit softer skirt coating, it abrades and kind of conforms to the natural distortion of that cylinder. Now you more uniformly distribute the load. So that way, that on the Stribeck curve, you're less towards boundary, more towards mixed film, which is going to mean you can carry more load, which means that piston skirt shape with that abradable coating can now handle more cylinder pressure before you have a rupture of the oil film, which then is going to basically put more wear on the board, because you're relying more on the additive package in the oil. So the oil itself loves this. It's going to be a help for that. And in comparison to the flat tappet cam, here's what that skirt coating looks like prior to break-in, post-break-in. You can still see that same thing. You go from those peaks and valleys, and as it starts to break in, there's still a valley to hold oil, but you're getting more flat, that plateau that can hold the load, which is the key to being able to provide a surface that's durable, low friction, low wear. Because in the end, that's how you're going to make the most efficiency and durability, is to have surfaces that are smooth, that can hold load, but still provide good durability and low wear. So surface speed. So what does surface speed have to do with this? Obviously, when Ben talks about spinal tap and 11,000 RPM engine, that's a thing you got to kind of keep in mind, is that as surface speeds increase, right? When you go from no surface speed, you have very high load, very low speed, right? Stribeck curve, you're in that boundary condition. That's going to be the highest friction, highest wear. But as you move in speed and increase that speed, you begin to build that film. But then at some point, once you've built the film and you just keep going faster and faster and faster, now you begin to create more and more drag, more and more heat. That's one thing at a very high RPM engine, say an 11,000 RPM engine versus a 6,000 RPM engine. All things being equal, you want a lower viscosity oil in the 11,000 RPM engine than you do the 6,000 RPM engine, because the 11,000 RPM engine is going to generate so much additional heat from the fluid film. Because all viscosity is a fancy word for resistance to flow. The higher the engine speed, the higher the surface speeds in the engine, the lower viscosity you want in order to try to find that right balance. Like Ben's going to show you on some stuff, an 11,000 RPM engine, you're not beginning that pull at 3,000 RPM. You're not starting way down here and going all the way to there. So when you shift that RPM window up, think about that, and you're at to move that viscosity down to compensate for that. One cool thing you can do with some of the things with lubricants is that the viscosity can shear. So as you design the oil, some people are really afraid of like, oh, that 0W20, 0W30 oil, that's super, super thin. Well, yeah, remember, the polymers in the oil that are an additive you can put in the oil, which are, they will actually shear thin with increased shear stress. Well, that shear stress can come from that shearing of the surface speed. So a higher surface speed creates more shear stress in the oil. So you can design the oil to basically thin at higher engine speeds. So you can go and say build a 0W20 oil that can rev to 11,000 RPM and maintain a slope so that as that engine speed increases, your friction isn't going linear, it's actually plateauing off because of shear thinning, which is, why you would not want to run a straight grade oil and say an 11,000 RPM engine. That's where, taking advantage of the multi-grade additives, is something you can use, which goes back to something that most people that know me and have heard me talk enough know. When it comes to oil, application dictates chemistry. If you take nothing else away from my section of this today, please know that application always dictates chemistry. There is no one size fits all best oil. Doesn't exist. It's the application. The needs of the application are going to dictate what the base oil viscosity needs to be, what the additive package needs to be. Again, back to DLC, this is going to be a different additive package than something that's, say, cast iron. So when you have different applications, don't get yourself locked in. Well, I've always used this one oil and I'm going to make all these changes. I'm going to use that. If that synergy is key to pulling it all together, so don't overlook that. When it kind of goes back to the Stribeck curve, and if you think about engine efficiency and you use the Stribeck curve as that tool to understand what's going on where in the engine, then you can really make some key gains, because what you want to do is try to flatten that curve to unlock some potential. So just for a little quick fun, everybody that's on the panel today have all been involved in helping make this possible. This is, well, it would have been published this month at the Society of Tribologists of Lubrication Engineering meeting, but it was canceled because of the COVID situation. So I'm going to go ahead and share it. So Billy and Keith and Ben all helped out and participated in a multi-year project that we did when I was at Driven with GM and Oak Ridge. And what you see here is a Stribeck curve that GM had ran on one of their simulation rigs, where they took 5W30 Mobile 1, Gen 2, and then they changed to some different oils we were running. And this one with they call it ionic liquid, with some pretty cool stuff we were working with there. You can see there was a 23% or 23.8% decrease in friction as the increased speed. So it was kind of neat, as you can see that, okay, that CPO 356, that's a 0W12. So pretty low viscosity oil. But what we did was, by using the right polymers, the base oils, and the additives, again, that synergy, putting it all together, you can see that as the speed increased, you would normally see that film get thicker and thicker and thicker. That's not what's happening here. What's happening is you're getting it decreasing, because we were making sure that even as the speed increased, by understanding base oil viscosity, polymer shearing, working it all together, we were able to actually increase the efficiency even at higher speed. And then here's the trick where you're actually looking at the same speed. So you're fixing the speed and you're fixing the load, and you're just looking at steady state friction over time. And that's where the additive package came in. So between this, looking at how you play with viscosity, because 012 is going to be thinner than 5W30, so you would expect it to be better. But I guess what I was really trying to say in this previous slide is, if you look back at the boundary condition, even though it was a thinner base oil, it wasn't, increasing friction, because we had everything dialed in right. And then when you look at fixed speed, fixed load, again, over time, the additive package was doing a better job. So we're putting it all together. I mentioned it earlier, proper lubrication is the 4 R's. You can define it as the right oil, right place, right time, right amount. Those are the key things that you want to keep in mind, that you got to have the lubricant where it's supposed to be, when it's supposed to be, and enough of it. And then you can help the oil itself by adding things like PVD coatings, things like that are really key. And then for your oil itself, in service, what can you do to help protect your oil? Temperature, the higher the oil temperature, the shorter the oil life. That there's really two things that affect oil and affect how well it can work and how long it can work. One's going to be temperature. The hotter it gets, the shorter the oil life. Oxidation, which is the chemical decomposition of the oil itself, doubles, that rate of oxidation doubles every 20 degrees Fahrenheit, roughly. It's 10 degrees Celsius technically that it doubles. But every time it doubles, your oil life's cut in half. So an engine running at 300 degrees Fahrenheit will have a shorter oil life than one running at 220 degrees, substantially. So, but you want to make sure the oil's hot enough, say about 220 degrees Fahrenheit, to get the water, the moisture out, because water, which is a byproduct of combustion. That's one of the things we make in combustion is water vapor. And when you have blow by, the gaps, bad ring seal, you're going to get more water into the crankcase, right? More fuel into the crankcase. So when you get water and fuel in the crankcase, water and fuel are really bad lubricants. So they're going to degrade the performance of the oil and then decrease the oil's life. Short trip, low temperature operation is the worst thing for your oil. That's why, the drag race guys, they typically don't get a lot of heat in the oil. So their oil life is going to be, and think about mileage, right? If you've got, 40 quarter-mile runs, on the oil, that's 10 miles. But there's NASCAR stuff running 400, 500 miles, with the same oil. And it's less degraded than 40 drag race runs. Why? More fuel, more water, because of low temperature operation. And then obviously, if you get dirt in there, that's just bad, right? So you want to keep the dirt and the contaminants out. My daughter's doing the speed diagnostics oil analysis deal, and I can tell you from, helping her on that program, 99 out of 100 samples that have a problem, it's fuel dilution and then water contamination are the two main sources of problems. So if you really focus here on trying to keep the water and the fuel out of your oil, it will make a big difference in the longevity and the performance of the engine overall. And okay, almost the last slide here. I know I'm 6 minutes over. And so the first one, right, first guy, right, and I'm already out of the box behind the game. So we'll make up for it. Trust me. Why does all this matter? Why this really matters, why we're talking about tribology, is because outside of putting a supercharger or turbocharger on there, you do all this work, to get as much air into the engine as you can and get the right amount of fuel in the engine in order to make power, to create that heat energy that's going to move the piston to make energy, to make the engine make power. The biggest source of loss of power is engine friction. Be it the piston ring, which is itself about 46% of engine friction is related to the piston. And then you've got oil and seals and all that. Point being is the lowest hanging fruit in order to increase the efficiency of your engine is using and applying tribology in order to maximize the potential of your engine, because you've done all the hard work with manifolds, carbs, and tune-up to make power. This is how you make sure that you don't waste the power you made. So with that, let's take some questions.
Great, thank you, Lake. Good information as always in your presentations today. What are the pros and cons, if any, of DLC coatings, and when to use and when not to use?
Oh, okay. Well, the pro of DLC is that it's, this is a flat tappet lifter from the Coca-Cola 600 that has over 700 miles on it, race miles, and it looks absolutely brand new. So when DLC is done right, it's kind of like, any kind of coating is no different than painting. If you have all the surface prep done correctly, and then the coating is done correctly, it will have a very good looking, long, durable finish. So DLC done right provides extremely low friction, very long part life. When it's done wrong, it is catastrophe. If this stuff comes off, you've just got diamond particles, basically diamond cutting tools running throughout the engine, and it's terrible. So there's a risk reward with this type of technology, and I'd say probably the biggest downside to DLC is that it is expensive. That's where I'd say easily, I'm sure both Billy and Keith and Ben will have some other comments on that as well, what their thoughts are. DLC is fantastic technology, but it is expensive and it's got to be done right. So just approach it with that mindset. What else we got?
Okay. Next question we got. Any coating to material combinations that work best? For example, specific coatings for aluminum, steel, ductile iron, etc.
I'm not sure about what works best. There's some things that don't work. Like we mentioned. Electrochrome with Nicosil, really bad. You can't do that. So traditional chrome with Nicosil is a material incompatibility. Really what I'd say is, if you can avoid the stuff that's bad, you've already moved yourself in a good way. If I think back to, say, I'm gonna look down here so I can see where I'm at. And when we talk about good and bad, we also have to kind of define what do we mean by good? What's the objective, right? If it's, I'm going to use titanium nitride and WCC as an example. So if low friction is your goal, right? So a WCC face coating on a ring face for compacted graphite or or gray cast iron bore, that's going to be your lowest friction combination in terms of a dry film lubricant, thin film coating. But it's not going to live as long as titanium nitride. So nitride will live longer, but it will have a higher friction coefficient, which again, nitride great with a Nicosil bore because Nicosil is very hard. Titanium nitride is pretty hard. So you've got more closely matched hardness. And so the longevity of that's really good. One of the coolest things that we ever did when I was at Driven, with that little test engine we ran out there at Shavers, is that, Keith, said, here, let's put some titanium nitride coated diamond finish rings in that engine. Not only do they make more horsepower because they were, 0.7 millimeter diamond finish rings, that nitride coating, although harder to break in, but of course we had the right braking oil and good break-in procedure, we were able to break it in successfully, no issues, no dramas. That, because of that hardness, that thing lasted forever. So it became more consistent, so, like I say, a bracket racer type of guy that's looking for consistency, I would go more towards something that's going to give you that better durability, less change over time. But if the goal is all out max friction reduction, lowest drag possible, well, then you need to change it. So it's a very long way of not giving you a definitive answer, but hopefully giving you kind of a frame set of what do you define the application first, like I mentioned earlier, then the chemistry will follow. So objective will then dictate what coating technology to apply.
Great, thank you. Okay, we're going to try another live question here with Charlie. Charlie, you can go ahead and ask your question.
For an engine you want to ride on the street, say for a truck, good old pickup, 4-wheel drive type thing, which would be the and I'm assuming just plain iron cylinder bore, what would be the likely optimum? The titanium nitride or something a little softer than that?
I would probably go, I mean, Keith can probably weigh in. I'm not sure if he's unmuted or not, but Keith is truly the ring whisperer. I'd say, you know, for longevity, right? If you just want total longevity, I would do the either the chrome nitride or the titanium nitride. The chrome nitride is going to be really good. It's like it's not so it's a little bit softer than the titanium nitride, you know, so it won't be as hard. You know, it's going to be very durable. I think either one of those two. And then the key thing is you got to bring in the oil as part of that equation too, right? What oil you're running, make sure you're running the right viscosity for your bearing clearances, and then, you know, use something that, you know, that's good quality, and then, you know, change it regularly and let all the coating along with the oil work together. That will give you the longest durability possible.
Great. We'll move on to our next question here, Lake. This is from Clint. What have the OEMs done to improve durability now that they have start-stop?
Well, one thing they've done is they've gone away from, you know, traditional cast rings, and they've gone to, you know, PVD coated, you know, or some type of, you know, coated steel ring. You know, they've obviously Total Seal years ago, and I go back, you know, when I was at Gibbs in 2004, every engine we built had Total Seal rings in it, you know, and had before that, and still do today, you know, that, and all those rings were steel rings. So, you know, Total Seal really came out with that steel ring technology, you know, before everybody else did. And now the OEMs are catching up and applying what they learned from racing and putting steel rings in there, and they're putting, you know, different face coatings on there in order to try to help with the start-stop technology. You know, there's no way they would be doing start-stop technology and having long warranties if they had just, you know, cast rings in there with no face coating on it. It'd be a disaster.
This is from Neil. What are your thoughts of titanium instead of zinc for anti-wear additive?
It's not. So titanium is not an anti-wear additive. It's a type of detergent. There's, you know, three primary types of detergent additives: calcium, sodium, and magnesium. Titanium detergents have been introduced. Really, the titanium part of it is more of a marketing thing. I know they claim that titanium can have some frictional benefits, but really, calcium, of the three detergents, calcium has the lowest coefficient of friction typically in an application. The downside to calcium, you know, going back to the webinar we did, you know, this time last year on direct injection engines and low speed pre-ignition, is that calcium has a negative effect on LSPI. So basically above about 1,600, 1,800 parts per million of calcium in the motor oil, low speed pre-ignition increases, which is a type of detonation that can destroy a direct injection engine. So you really want to have lower levels of calcium. About 1,500 is a pretty safe number, or a little bit less. So the new API SP oils that are now available this month, they will all have a new detergent package in them that's going to be lower. But, you know, really, there is no replacement commercially available today for zinc, which is really, we call it, technically we call it zinc, but really it's zinc dialkylthiophosphate. That's a family of chemicals that's manufactured by companies like Lubrizol, Afton, Ornite, Infinium. Those are the four main additive companies that supply to the oil blenders. The only product that I've seen in my experience that allows you to reduce zinc substantially, not just partially, but substantially, and actually see an increase, not a same or less performance in terms of wear protection, is the ionic liquid that when I was at Driven we were working with, that was developed by Oak Ridge that was part of that process, right? When you look back at, okay, let me get to the right slide and answer your question. Boom. Right here where it says IL. So the difference between the CPO 356 non-IL and the CPO 356 IL is the non-IL is just a regular, 1,000 parts per million ZDP type concentration. Actually, it's like 850 to be exact, but I was rounding up just for round numbers, so I could cut the numbers in half in my head easy. But the 356 is IL is half the amount of ZDP replaced with the equal amount of IL. So, for example, if you went from, say, again, rough numbers, 1,000 ppm of ZDP, and now you set it to 500, you've now replaced it with 500 ppm of IL. So the total amount is the same, but it's half the amount of ZDP. And in this case, you saw less friction, less wear in that case. So that's the only thing I've ever seen that can replace ZDP is the IL. And that's still kind of new technology that's emerging that's not even on the market yet.
Okay, our next question is from Benjamin. He goes, if you have some engine components coated, do you have to buy specialty oils that won't have adverse chemical reactions with those particular parts that are coated?
I wouldn't say you have to, but you probably should. If you spent the money to buy all the good stuff, you should probably buy the chemicals that go along with it that are designed for it. That would just be my approach. I mean, there's nothing that says you can't go buy off-the-shelf oil and run it in an application like this. And it may not fail, but it probably won't work as good as it could. I mean, there are some series, IndyCar is an example where they run off the shelf. They make them run off the shelf Mobil 10 W40, and those engines do live. I can tell you from looking at used oil analysis reports from different engines running different oils, you can have, say, the same exact engine built by the same engine builder to the same spec, and see different wear metals based on an off-the-shelf oil versus a specialty oil. And I've seen it be half. Both engines are fine. Neither one of them are blowing up, but the wear rate is half with the specialty oil versus the off-the-shelf oil. And it's not because the off-the-shelf oil is bad. You got to remember an off-the-shelf oil that's got the API symbols on it. It means it's designed to cover everything, a wide range of applications. So in that regard, it's got to be able to cover the short trip driving. It's got to be able to cover, towing up, the hills in Arizona and things like that. Whereas a specialty oil, because it's not trying to be all things to all people, it can narrowly focus on being the very best it can be for this specific application. And that's where it can be the A student. That's one thing I'll think about in terms of, race engine lubrication is, yeah, you can go to Walmart and you can buy something, you can put it in your motor, and it probably won't blow up this weekend. But how long will that engine live before it needs to be rebuilt versus if you use a specialty oil made for that application, the longevity of that engine will be longer with the specialty oil versus the generic oil, just for those reasons.
Okay, our next question. Is there any particular characteristics to oil that one should use to help control piston slap during warm-up in colder climates?
Well, that's a good question, and it's a catch-22. It's a double-edged sword. If you've got piston slap at startup in a cold environment, it's chicken or the egg type deal. You need viscosity to fill that gap, right? The reason why you're getting piston slap is because you got at cold, you've got more piston to wall clearance. So you need a high viscosity oil to fill the gap. The trick is a high viscosity oil by itself can't get there fast enough. It goes back to right oil, right place, right time, right amount. So what you would rather have in this environment is an oil that flows well at low temperature. You know, you'd want an oil that, I'm not saying you need a 0 grade oil, because I'm not sure, exactly what temperature you're talking about. If it's, sub-zero, or if it's 40 degrees, or if it's 100 degrees, Fahrenheit. But what you want is an oil that can get there fast enough so that you can do it and still have enough viscosity to minimize that piston slap. But then that oil still has to maintain enough viscosity that as the engine heats up and gets to full operating temperature, it can do it. So there's a chart that I wrote when I was at Driven that you can get from Driven that is recommended oil viscosity based on bearing clearance and oil temperature. You should definitely look at that as a tool you can use. And then other thing I can do, make available, and y'all bear with me real quick. I'm gonna escape out of this, and I know you can see my screen, and I'm gonna show you a chart that we were working on. I'm going to show up here, and we can make this available to everyone watching. This is the chart for flow rate of oil versus temperature for break-in. And it really, the idea is here, we want, why is Excel not cooperating with me? Of course, right when it needs to be, aha, here we go. So boom. All right, so just so you know, I'm not looking at the camera because this screen's over here. Just so you guys know, I'm not trying to ignore you, but so I can actually read what I'm looking at. That's why I'm doing this. What this is going to do is going to give you oil flow versus oil temperature. It's for piston ring break-in, but your piston slap would also go with that. So this is going to give you based on fuel type and induction method, be it NA or boosted, gasoline versus an ethanol type blend fuel, which changes the air fuel ratio, which means how much fuel is interacting with the oil. These are viscosity grade recommendations based on temperature, operating temperature range, and then it will basically, those are just kind of summaries, and this gives you actual examples. So between the Driven chart and this chart should help give you some information on that. And again, everybody that's on this webinar, we'll be happy to send you this chart if you would like to have it. I'm not sure, Steve, how you want to handle that. If you just want to blast it to everybody or have them request it and then we can send it out, doesn't matter to me. But this is a tool that we can make available for you, and hopefully that helps answer your question.
Perfect. Okay, we're going to try another live question here from Michael. And if it doesn't work, I do have a Oh, he's there. Perfect.
All right, I hear him.
Hey, Lake, how you doing today?
Doing well, sir. Thank you for joining today.
Hey, thank you. Question for you. A lot of people run these big inch motors on the street, aluminum jobs, and some of them are using the Morel type, tight tolerance hydraulic roller lifters and such. And the usual recommendation's been for, run like a 5W40 weight oil on that because of obviously the tolerance and such. But, with push rod loading, push rod loading in the small surface area of the plunger, but then you got bigger main journal clearances and such. Have there been any changes in the weight recommendation for that type of lifter, like with the additive package or molecular structuring that's going on with the newer oils?
Not that I haven't heard Morel say anything about what their recommendation is, but you're right. That is a really it's a catch-22 situation when you've got an aluminum block engine, where you're going to have clearance growth, and you've got high spring pressure, so you're going to have load, on the push rod tips and all that. I know I'm going to sound way biased on this, but just bear with me. In all the testing I did at Driven, and trust me, I get paid zero to say this. I have no financial stake in this. The GP1 oil that we developed at Driven, in my opinion, is the best oil you can run for your grassroots motorsport, your street strip high performance. That oil has got some pretty unique characteristics. The Pennsylvania grade base oil has that linear pressure viscosity slope that we were talking about earlier. And for that reason, Mike, to your question, it can kind of help with that. It can give you that trade-off where it's going to act thick where it needs to be thick, and it can be thin where it needs to be thin. That's about the best thing I can think of to say to use in that application is like probably the 15W40 GP1. And if for some reason it's a little bit loud, there's nothing that will stop you or make it where you can't blend some 1030 GP1 with some 1540 GP1 to thin it out a little bit at low temperature to get the lifters to be quiet and to be good as they come up and still have enough protection when it gets hot. That would be my recommendation.
Okay, we've got time for a couple more questions here, so we'll keep rolling along.
Sure.
From Aaron, what are some of the adverse effects of common additives, either trade-offs or downfalls of too much?
I'm a big believer, don't put anything in any motor oil ever. It's simply Russian roulette. If your oil isn't doing the job, get a different oil. Don't try to fix it. When for motor oil, to me, that's 100% truth all the time. If you got to put some kind of stabilizer in there to thicken the oil, you just use a higher viscosity version of that oil. Because when you add in a stabilizer, typically there's nothing in it. There's no ZDP or that kind of stuff in it. You're just diluting the additive package. You're raising the viscosity, but diluting the additive package. If you put in something that has an additive in it, there's no way that you know that the type of ZDP in that additive is going to work with the type of ZDP in your oil. Because just because it's ZDP doesn't mean it's the same. There's 4 different companies and there's multiple different versions of ZDP. They don't all work together, and not everything will blend in properly. I mean, I've seen some really, really bad catastrophes. I've seen grease be made from an additive and a motor oil in a crankcase in just a couple of minutes because they were so different, they just clashed. So for the additive clash reason, to me, safe bet, just don't put an additive in your motor oil. Now you can put a limited slip additive in a gear oil. There's no problem there. And you can put some, detergent additives in your fuel. I have nothing against additives where additives are appropriate, but additives are not appropriate in motor oil, in my opinion, in my experience either. Hope that answers your question.
Okay, we're going to go to our next live question, and that'll be from Mark.
How you doing, Mark?
Yes, this is Mark Neidick. Lakesby, got a question for you on your oil temp, and you were saying that for every 20 degrees over 200 degrees, the oil life is cut by 50%. Just wondering, how do you determine what the actual oil life is? And what the engine I'm thinking about is a air-cooled Harley V-twin, and those engines routinely run 240, 250 degrees in hot weather. So maybe you can enlighten me a little bit more on that.
Yeah. So, I mean, 240, 250, that's not crazy hot. That's fine. There's nothing to be concerned about. Hopefully what I said didn't panic anybody. If the engine's running in that range, it's fine. That's most, I'd say oils are designed to work in that. They're routinely tested. API certified oils actually run in a 100-hour test at 300 degrees Fahrenheit. So that's a standard for even just off-the-shelf motor oil is 100 hours at 300 degrees Fahrenheit. If that gives you a frame of reference what we're talking about. But to determine oil life in a specific environment and application, The only scientific way to do that is to do used oil analysis, which looks at the oxidation, the chemical degradation of the oil, and you can look at that and look at the oxidation level, look at your wear metals, and then do, say, 1,000-mile drain, and then maybe a 3,000-mile drain, and then maybe a 5,000-mile drain of the same oil, and then look at it and compare those numbers, and then you can create a slope from that, and that will tell you, when it's optimal to change the oil. That's the only scientific way to do it. Everything else is just a guess.
Our next question is from Joshua. For applications with leaded fuels, what can be done to prevent lead buildup on the pistons and rings?
A good detergent package is the best thing you can do. Detergent additives in the motor oil can help with that. That's one key thing, is that if you're allowed to use an additive in the fuel, using a polyetheramine based fuel detergent additive can help clean pistons, combustion chambers, rings, all that. And then obviously you want to use an oil that has some detergent level in it. There are some race oils that are super low detergent, which helps the friction modifiers be, fully effective, right? You can get the most benefit from it. But those are made typically for, we'll call it pro racing engines that are going to be rebuilt every 500 some miles, every few races, so they're not trying to run longer. If you're in a situation where that engine is going to see thousands of miles of use before rebuild, and it's on a leaded fuel, and you want it to stay clean longer, then one of the key things would be fuel additive if you can, and then run an oil that has some detergent level. Obviously, you don't want to run too much detergent, because then it competes against the ZDP and can throw the whole balance off. But you want to have some detergent in the oil, and then you want to make sure you've got some detergent additive in the gasoline as well, if possible. Some race fuels have very low detergent levels, so you can probably look at something that's got some polyetheramine in it, and that should help you out a little bit.
Okay, and our last question, even though there's several more, we'll save those till the end during the panel discussion, and then we can get those out to you. This is from Harold, and he seems to be having some issues with coatings that end up in the bottom of the pan, and it just looks bad. The coating goes into the oil. I'm having sporadic hydraulic roller lifter problems. His question is, are they related, and the lifter brands vary?
Yeah, I mean, obviously hydraulic lifters, there's a piston in there, and most of those things are going to be very suspect of sticking if there's contamination. So contamination is a big problem, and it sounds like you kind of answered your question already, that you've got coatings that are coming off in the engine, ending up in the oil pan, and now this stuff is ending up maybe in the lifter. So that's where, a couple things you kind of look at is, one, maybe check what your filtration is. Wire screen filters provide very low restriction, good horsepower, but they only filter, particles that are the size of the hole or larger. They filter nothing smaller than that. So filtration might be something to look at, and then what your oil change interval is. I was breaking in that Swiss Auto 250 yesterday. I had about a little over an hour of engine runtime on it, and you know what? I can probably pull this up. I think I can pull this off. We're going to get real fancy here. I'm taking a big risk of just live, trying to pull things up and make this not be terrible. So we'll see what I can do. I'm going to show you this picture. So I don't know if I can make that larger or not. Let's see. Yeah. So that's the oil that came out of that engine and the stuff in the magnetic drain plug. Of course, that engine's got no filter on it. It's a little 250, splash, lubrications type engine. That's BR30 with an hour on it, and how dark it is, So I think, is there another one here? of all the nastiness. No, that's the only one that's uploaded so far is that one. You know, but you can see just how nasty and dark and dirty the oil is, you know, and that's just a case where you just get combustion buildup in there. So how often you change the oil is going to be key in removing that stuff. So I would look at oil change interval, I'd look at filtration, and then obviously go back and maybe look at the coating and see what's happening there to try to minimize as much contamination as possible, but and still make all that stuff work. So see if I can make this thing go again. There we go.
All righty. Lake, thank you again for a great presentation. Appreciate it very much, taking the time out of today to do this for us.
I'm happy to do it. This is fun.
Excellent presentation. Lake always does a great job, and lots of good information there. And that's kind of the whole idea of what we're doing today. We realize that, you know, typically we would have a tech and skills conference. We usually have 4 of them a year. And of course, with the COVID situation, we just haven't been able to put those on. So, you know, typically we would have presenters, you know, like we have today, and they would come on and we would do presentations and we'd have prizes. So we thought, you know what, if we can't bring this to you, you know, live like we typically would, then, you know, let's do this. And it was a great idea. And Lake and Total Seal, Comp Cams, on EFI University, Ben, they all came to us and said, you know what, we're available on this Friday, and we would love to be able to put this on for everybody, because we realized that, you know, everybody's at home, they've got a little extra time on their hands, and you know, let's keep the information flowing. Even though we're going through a little bit of a struggle, maybe with trying to get information, especially right now, because we can't travel and we can't get out to see stuff. Let's bring it to you. You guys still are busy. You need this information. We still need this kind of stuff for our shops to succeed and that kind of stuff. So again, we're very, very happy that these guys were available and to be able to put this on for us. So to keep things kind of rolling and on time, you know, you can listen to me chat all day, but what we'll do is I'm going to bring Steve back on, and then what we'll do is we'll bring up Billy, and we'll just roll right into the next presentation.
Okay, our next presenter for the day is Billy Godbold from Comp Cams. Today, Billy will be talking about beyond the specs, what to consider when choosing a camshaft. What I'll do now is I'll turn it over to Billy so he can get this presentation going. So Billy, take it away.
Okay, so we're going to go through something called Beyond the Specs, and it's what to consider when choosing a camshaft. And we're going to go through a lot of things pretty quick. What I'm really hoping is, as we go through it, go ahead, I'm going to go through it a little fast. We're going to go ahead and at the end go through question and answer so I can back through whatever we need to do. I went ahead and put this one slide in of that our marketing guys did. I want you guys just take a look at who Comp Cams is for 30 seconds, then you get me for 30 minutes. Well, hold on. Maybe you get me for, let's try again.
Duplicators. Your engine knows the difference. Comp Cams camshafts are always original designs, from precision engineering to premier manufacturing and unrivaled testing again and again by the most advanced engineering team and equipment in the industry. Buy the original, not an imitation. Copies might look the part, but horsepower doesn't lie. Comp Cams, no comparison.
Okay, well that should give you just a little look at who we are, and we'll throw a little bit of a discount at the end for this. So let's talk about what we're going to go through and what lies beyond cam specs. The first thing we're going to talk about is what profile development is. You know, one of the things that people, a lot of times you'll hear that camshafts, they're about the same size, they're about the same lift, they're about the same specs, they're going to run the same. Well, we know that's not the truth, and we're going to try to explain to it why. We'll go through a little bit about all the testing we do, go through a little bit through all the manufacturing and the quality. Hopefully you can see beyond what's going on in normal camshaft. You know, when most people talk about camshafts, we want to show you more than what you normally would see. And one of the most important things in that way is actually a systems approach. You know, a valve train isn't just a camshaft, a spring, a rocker arm, a push rod. These components are all necessary, but it's really a system. You know, I talk about sometimes that the valve spring is like Ginger Rogers and the cam profile is like Fred Astaire. Well, if you really think about that, it has to do everything that the low basket to do, kind of backwards in high heels. So we'll go through about how this whole system works and how that is really what's going on. In part of that system, we have to talk about the components, because any system is just a series of components all working together. So we'll go a little bit through lifters, valve springs, even cam cores. And I think I'm going to end here with where we're going to start, and that's material manufacturing topography. You know, Lake set a tremendous foundation on topography and materials. I'm going to build upon that, and then Keith's going to come in behind me, and he's great. But I put down here, like any great meal, you know, how a recipe turns out is very dependent on the quality of the ingredients and the skill of the chef. Likewise, valve train components require optimized material selection and manufacturing techniques. So what we're going to do here is let's start in material science and then work our way back and go all the way back to the to where we started. Okay, so the materials. Okay, so the roller cam materials that we have, basically all cast iron, all flat taps are cast iron. So there's really not a reason to talk too much about cast irons. Every camshaft you've probably dealt with is mostly iron. 90, 95%, 98% of it's iron. What separates the materials is what's added to that iron. So let's go through here and look at what's added to iron in the typical roller cam materials. Go over 8620, 9310, 5160, some of the high-end tool steels, and then some of the tool steels that sportsmen use. Okay, so here's your four main materials. It's 9310, 8620, 5150, and 5160. Note that the first column is carbon, 9310, 0.1 carbon, 8620, 0.2 carbon, 5150, 0.5, 5160, 0.6. It's really clear that in this ANSI SAE style, the last two numbers are the percentage of carbon. So somebody tells you, well, what's 52100? Well, that's easy. It's a 52 series steel with 1% carbon. What's 8620? It's an 86 series steel with 20% carbon. So what makes the first two numbers? Well, it's what lies beyond that. So 8620, very common steel, is 0.8% manganese, 0.22% silicon, 0.5% chromium, 0.2% molybdenum, and 0.55% nickel. 5160, you can notice here I put the chromium in red. You can see that it's another 60% higher chromium than 8620. We'll talk about why that's important. Okay, so 8620, a little brief history. Already went through the chemistry. This started out in World War II aircraft engines as far as camshaft. 8620 is actually a gear material, but when the guys at Rolls-Royce are building the Spitfire, building the Merlin engine, this is the material they chose for the camshaft in that. Harvey Crane would tell you that he came up with 8620. I know when Harvey was born. I know he didn't do the Spitfire, so okay. But he did adopt as a standard for roller camshafts in the performance industry. 8620 requires, to get 100,000 case depth, it requires 36 hours to heat treat during the carburizing oven. So basically, this means all of our 8620 camshafts have to be run over the weekend. So what happens is the guys load the oven on Friday, the last thing. They run it all day Saturday. It shuts down and cools off Sunday. Then they quench and temper it on Monday and send it to us. So when we're doing a run of 8620 camshafts, kind of has to be out of our business about Wednesday, Thursday at the latest, and then it comes back to us on Tuesday the next week. Really, if you think about carburizing, if you've ever seen the old swordsmiths where they'd stick the sword into a fire, a charcoal fire, and then they take it out and beat on it and stick it back in the fire, they didn't really know what was going on, but what was happening is the low carbon steel was being penetrated by the carbon. The carbon was actually diffusing into the first 10, 20, 30, 50 thousandths of material, and that was what's creating the hardness. 8620 camshafts, the copper on it is not to do anything except for getting the parts you don't want hard, not hard. So it's kind of neat that the copper is not an enhancement. It's not to make it look good. It's to keep the camshaft from breaking when you straighten it. 9310. This is something you'll hear more about in Top Fuel than anything. If you look at it, it has a lot more chromium and 6 times more nickel. 8620 and 9310 are both considered gear steels. So basically, very, very similar. 9310 is considered a more premium gear steel. The real place where 9310 comes in our world is top fuel applications. The 6 times the nickel, I don't think that nickel stake was about being tough, but not the nickel part of it. It was the cheap stake. But when you hear tougher than a nickel stake, I think about nickel. Nickel makes the added 6 times 600% more nickel in 9310 makes it where you could practically tie a 9310 cam into a bow knot before it would break. Now, normally nickel really hurts the wear characteristics. So 9310 has the chromium. The added chromium offsets the wear reduction of nickel so that you really wind up with almost identical performance in A620 and 9310 in camshafts. The only place this wouldn't be true is where you see really, really drastic bending. Maybe a flathead Ford with a little 800 barrel that has only 3 bearings, so it's got really long spans. That would be a place where it'd use 9310. 5160. 5160 started, 5150, 5160 both started with both the aftermarket and OEs all went this way at the same time. There was a lot of metallurgists, a lot of people sitting around tables going, if we could make the best possible camshaft, what material will we use? And somewhat surprising, this is sort of what came out of it. The nice reason that what makes 5160 so good is the induction hardening lets you really tune in the heat treat. You can make it deeper or shallower. If you make it too deep, say if we decide we want to make a 1/2 inch deep induction hardening, we can do that. The problem with it is really likely to crack, and it also makes the camshaft kind of brittle. But one of the big advantages is it doesn't require copper masking. There's 2 ways to put copper on a camshaft. You can put it with electric plating, or you can put it with sodium sulfide. Hold on, that's sodium. Basically, good, like arsenic stuff. So basically, you really, really, really don't want to do this in your garage because it's liable to kill you. The other problem with 8620 and 9310 is those 36-hour carburizations. That's a big furnace going for 36 hours. So you can imagine the CO2 that's produced in this. One thing about the 5160 is how much it came out really in the early 80s, but it's amazing how much that technology improved. In fact, by the late 90s, early 2000s, most NASCAR teams were running 5160 with a quench and temper beforehand in all of their roller cam applications because it's really, really good on wear. Here's the other thing about when I talked about heat treat depth. The cam on the left is an 8620. You can see the copper masking. You can see the heat case depth on it. It's only about 100 thousandths. And then you can see it starts getting really fuzzy. If you look at the cross section of the cam on the right, this one's 5160. You can see where I've done hardness checks, and you can see how the hardness changes. It's a 1/4 inch deep on the nose and still over 100 thousandths deep on the base circle. This gives it a lot of flexibility on what grinds we can put on it. It also is just a lot deeper road. If you think about like your driveway going to your house, if it's concrete, it can't be thin concrete. You need to lay down gravel, pack the soil, and make sure that it's going to be good subsurface support. The 5160 cam on the right has tremendous support underneath. And you can see this with this picture of theory of it. 8620 is going to be the same depth all the way around. Any place that doesn't have copper, the carbon's going to diffuse into the surface, and you're going to get the type of profile you look on the left. With induction hardening, you're going to see more of that profile like you see on the right. I think it's really gives a lot more flexibility. If you look at that plot in between, that's the difference between a UGL, how we'd mill a lobe in blue, versus the finished grind in red. And you can see where we're taking off material, where we're leaving material. We really want to have that extra flexibility from a deeper heat treat where possible. So tool steel. Tool steel is what you're probably hearing about most in professional racing. all tools, when somebody says they have a tool steel cam, that's kind of like saying you have a black car. There's a lot of different ways to have a black car. NASCAR teams use a powdered metal M4 tool steel. So really, this isn't like powdered metal rods. This is really state-of-the-art stuff. The biggest issue with that is the material in like a NASCAR cam is $400 for a 24-inch bar, 2.5-inch diameter for PMM4. And then the heat treat is another $400. So basically, you have $800 into material and heat treat alone. Nice things is through hardening means you can't grind through the case. And because it's through hardened, you have the same compressive stresses throughout the core. The problem you might have in 8620 or 5160, if you grind 50 thousandths off one side and 10 thousandths off the other, somewhere you're transitioning between a deep case and a thin case. And where it's deep, it has more compressive stress, and when it has shallow, it has less compressive stress. So you get more deflection. That uneven loading can cause spalling from the bottom. And that's why we really want to make sure that when we're taking a core, that we grind it properly. We have actually a whole computer program that picks which core is going to take the most even material for a given grind. But what we learned from PM, we actually made new grades of tool steels. We're starting using different conventional grades of tool steels. They're excellent choices. This gives you an idea of the tool steels we tested for camshafts, just a few of them. You can see the S7 up there. One thing you're going to note really quickly is how much more alloy content. You look at A8, it has 5% chromium. That's so much more than what you saw in the other materials. S7, 3% chromium, but only 0.5% carbon. If you look at our grade that we use most, which we had a mill make for us, it's got twice the carbon of S7. So we can use that in a lot more applications than people can use the normal stuff. Look over at M4, 4% vanadium, 4% moly, 4% chromium, 5.5% tungsten. You can see why that material is so expensive. Well, let's talk about surface engineering. Like I already showed this device a little bit, but one of the things is I had a conversation with one of the guys at Cummins one time, and I was talking to him about all the material science stuff I was doing, and I was really proud of my ST4 grade that we had people make. And he goes, well, Billy, how much did you increase the ultimate tensile strength? I said, well, I've got this ultimate tensile strength up by, all the way up. It's 10% higher, 15% higher. He goes, well, what if I told you I've doubled my strength? I'm like, well, that's impossible. He goes, well, I didn't double my strength. I doubled the area that I was loading. So if you think about walking across a field that's full of snow with snowshoes versus walking on some sort of pointed toe boot, you're going to sink more with less surface area. So what we're doing with surface engineering is trying to broaden out that surface area. So there's skid profile, those profilometers like you can buy on eBay for $50, and then there's stuff like we have that costs $50,000. A little bit about RA. RA is a lousy measurement. Keith will get into this more, but if you look at the upper right-hand corner, all three of those surfaces up here in this corner have the same RA, but they don't at all have the same performance. So when you start looking at a profile like this, this would be great for a camshaft. This one here in the middle would be lousy for a camshaft. And this one over here would be kind of in between. And what we're going to start talking about is material ratios. And you can see material ratios if you just come down from the top, cut it off, and you look at how much area you're actually loading. So in this plot, this will be a 35% material ratio, or what we'll call bearing area, effective bearing area. I want you to see that this isn't just going on with comp cams. On this slide, we see two OEM camshafts. The one on the left was from the 90s. The one on the right is fairly modern, 2015. And you can see how much they've improved the surface at the OEM level over the past decade and a half. So when I said that, if you bought a product 5 years ago, it's sort of embarrassing today, that's not just in the aftermarket. The OEs are doing the same stuff. So you'll hear people say, oh, well, I've got a polished camshaft. That's going to be great, right? Well, take a look at this. This is another manufacturer that polished a camshaft, And you can see the RA here is really good. It's 16 RA, but the waviness is 131 microinches. So it's not really going to load down here in this nice part. It's going to put all the load on these points and bust out. So you can't just go up and polish a camshaft and go, hey, I've got a great cam. One of the failures we saw a lot going back from 2005 to 2015, 2016 was edge loading on camshafts. And I think I can explain it after having these gauges. If you look at this profile, you can see where the failure actually occurred. And this failure occurred on the edge of the lobe. So if you look right here where I have circled in red, you can see this spot on the edge. And so what was happening is when you ground it flat, as the wheel eroded, it made sort of a bathtub shape to the cam face of the cam. And then you would get the sharp edge of the lifter wheel riding on that sharp edge, right into that edge, and it'd start flaking there. So the first thing you'd see is a little bit of line in it, like somebody cut the lobe with the razor blade, kind of like you see up here. And then the next thing you see is starts falling out around that stress riser. So what have we been doing? We've been working on a lot of stuff with CBN and CNC grinding, and then some post-process polishing. Here's a really good flat dress on a CBN grinder. You know, if you go back and look at what was going on in 2012, 13, 14, this was sort of state of the art for us after we changed our wheels and after we changed our dress profile. The problem with this, it was easy for it to get that edge loading. About 2016, 2017, we started to go to a crown dress on all our rollers. And you can see this is very similar, but we're slightly convex. When you start looking at this, this is 300 microinches plus and minus. Fine talcum powder is bigger than this whole scale. But you can see how we drop about 100 millionths, about a tenth of a thousandth of an inch on both sides of the lobe. And that made a tremendous difference. Now, after we do that and got our dress right, the material right, got everything going, then we went to a high energy, high kinetic energy. There's three ways to polish. You know, you can use electrical energy, you can use chemical energy like RIM that anneals, but that leaves surface carbides out, or you can go to a physical polishing. Now, belt polishing isn't isotropic, meaning it leaves lines and it can do things. We go through a centrifugal system that is isotropic, so it leaves a really, really nice finish. And we've been able to increase the loading of our camshafts by 2.5 times, a 250% increase in effective load bearing area. And this is the result today. You can see these bearing areas are so much higher. We never saw anything in the 90s before. Now just about everything that comes out of MSE at 20 millionths of an inch, 90% of the area of the camshaft supporting load. Now let's look at some other components. So basically, if you look at our left, that's our original, comp cams roller lifter design. And you can see when you start loading it down at the bottom that you get a lot of deflection there in the bottom. We came up with the Elite lifter that was better but still had some deflection. And then our new Sportsman was on the right. And you can see how we loaded it. We've really decreased what was going on. Basically came up, so you can see the pocket mill here. We've got a much lighter weight. We've got multiple oil paths. We've got two coming down the legs. We've got one coming from the skirt. So a lot of stuff going on in this deal. Now you'll hear people go, well, should you run needles or bushings? Well, needles are really good because they're low friction, less wear on the camshaft, and great endurance. And they have very little oil sensitivity. The negative of it is has high point loading. So if you're out of control and slamming together, you can get bad stuff like this needle and the axle can start spalling. The bearings can rapidly fail. And those needles are spinning at a really high RPM. And if you do fail a lifter, you've got all these little bits of needles that go all through your oil system and make a mess on your dry sump pump. So bushings, they're very forgiving in extreme loading conditions. People who run systems like a dirt car that might be out of control or anything with a turbocharged that runs one of those popping boost controllers, I always want to see them in bushing. When they do go out of control and they impact, it spreads out that impact. There's no way to get a needle in the oil pump if you don't have needles. And the bushing wear normally is pretty even. What's the problem with it? Well, the material in the bushing becomes super important. The camshaft is absolutely going to track more and wear out earlier because there is more friction. They're going to be more expensive. They're going to have more frictional power loss in the valve train. And they're going to be much more sensitive to what oil you run in it. But if you don't know if you're in control, it's a great choice. It's a little bit on a camshaft, you know, talking about the whole system. When you start loading a camshaft, if you look at this guy right here, when we load it in FEA, we're seeing 3/1000ths of bending. And it's kind of funny because if you go back to when Grumpy Jenkins was changed his journal size, you know, Bob was beating Grumpy. Grumpy goes, how can that happen? You know, Bob was actually working harder than him, so you can see kind of what was going on. But he went to the bigger journal, got NHRA to do it, and he said, hey, my cam's 4 degrees too big. And I'm like, check it on the lifter. It's not 4 degrees too big. He goes, well, it acts 4 degrees too big. So we came back from this design to this design. And it's pretty interesting because if you look at this design, now the bending is 1/4 as much. And it's funny because that bending actually became the 4 degrees of duration that he thought he was losing. So we're going to go through, speed up, go through some conical development. You know, regular flat wire dampener springs, they're problems they have. They're one frequency, so they're very easy to resonate. They're simple, but they're heavy. The dampener in it creates a lot of friction. And generally, they're fairly large in diameter, so you have a lot of mass. The Beehive was a great step because they had the smaller top, so you could run a smaller retainer. You had some progressive pitch, especially at the ends, so that made it not all one frequency. But still, there were about 2 or 3 coils that were the same frequency. Then you had the ovate wire to kind of fit more spring in a smaller installed height, and it also distributed the stress better across area. The benefit of the conical is you still have the small ID top, but now you have tapered sides, so the active mass reduces as each time you go through. If you think about it like a football player, you have your defensive back up at the very top, and you have your middle linebacker, you know, nose tackle in the middle, and linebacker somewhere in between. So each spring is asked to do a different task. So we can kind of like model this spring like this, and you start looking at coil 5 on this plot moves so much more than the rest of the coils. So we're doing modeling, and we can see here's the motion of each coil, and then we work to figure out what stresses each coil. Not only can we calculate this in a model through the modeling software, but we can even go in there and put a strain gauge on the spring itself. You can see it here in this picture right here. There's a strain gauge glued right here. There's another strain gauge glued right here. We've got strain gauges that we can glue on each coil, so we can actually see the exact stress of that spring at each coil. So it lets us go back and modify this pitch spacing to make sure that we even up the stress through every one. If we modify the pitch spacing, we can go in here notice the spring on the left never stops vibrating. Every time it cycles, it actually goes through there and cycles 4 or 5 times. The spring on the right, you can see that we've really, because of the different frequency, we've got much less oscillations going on. We can go, well, Billy, that's great, but that's not for race engines. That's just for, well, endurance race engines, but not for drag race engines, not for things with over 600, over 650, over 700 lift. Well, I kind of call this project Spinal Tap Junior. Ben and I were working on Spinal Tap, and after we got through, we realized that nobody except us could ever afford to do something like this. So basically on Spinal Tap Junior, we said, well, instead of 11,000 RPM, let's go 10,500. Instead of 1-inch lift, let's go 800, 850 lift. So we took this dual conical and some of the low shock profiles, and we worked with this. And you can see here's the run at 3,500, 9,500 RPM, 10,760 RPM. This is a package he ran on the dyno. He can talk to you about it, but just an amazing deal. A 10,000 plus RPM package that doesn't cost nearly as much as something like the 1-inch kind of pro stock type applications that we've worked with. Okay, so I've mentioned low shock a couple of times. I guess I need to talk to you guys about what is low shock. Well, this part of the presentation about how to learn to relearn to compare cam lobes and select the camshaft with a very asymmetric profile. So how are we all taught to compare profiles? Well, we're taught to just look for lobes with a similar duration at 50 and lift, find the one that was the smallest it could be at 20 thousandths lift and as big as it could be at 200 lift, and that'll always make the power. So the smallest at 20 and the biggest 200 was always the best choice as long as it didn't leave exit wounds in the valve cover. Okay, well, Billy, how can that possibly be wrong? Well, we knew exhaust lobes didn't follow that rule, just the intakes. 2, we didn't understand that the opening side and the closing side had very different things going on. And 3, we didn't really think about what really limits the duration that you select for an application. So what do I mean when I say what really limits the duration? Well, normally you'd think, well, minimum and maximum RPM. Well, okay. The other thing you start thinking about is piston to valve. And that's 100% true, both in the race and street. The intake opening side is always going to be tight on any good engine. Number 3, definitely on the street, idle stability and emissions. If you open the intake too far, too fast, you're going to have real trouble with idle stability. You're going to have real trouble with hydrocarbons on any emissions test. Number 4, low RPM performance. What we didn't understand is low RPM performance had 100 times more to do with the closing side than the opening side. High RPM performance. We're really going to talk about more. So let's look through what happens at each valve timing point. So here's the complete cycle way I look at a camshaft. You can see the power stroke, the exhaust stroke, the intake stroke, and the compression stroke in all 4 events. So exhaust opening, you note, it happened in the middle of the power stroke. It didn't wait till the bottom dead center. It's like in the middle. As soon as you open the exhaust starts to blow down. You get to empty the chamber and then start back over again. So all of the exhaust that gets out around bottom dead center, you sort of get out that for free because you don't have to push it out later. But as soon as you open the exhaust, you've stopped your power stroke. So now none of that energy, all that energy is for pushing out the exhaust now, not for pushing down the piston. So here's a graphical representation of that. You can see in this application, the exhaust opening is not even midway. It's around, 280 degrees, 290 degrees before top to bottom dead center. So you can see that all of this first area is where we're getting in the power stroke, and then we get the free exhaust. So we have to look at those two quite separately. So what's the next event? Well, the next event is the intake opening. So as soon as you open the intake, you start your overlap. The remaining pressure in the chamber, what you're trying to do is time that exhaust wave out. So when it gets to the end of the collector, it's reflected back. So you have the positive wave going down your header. It hits the collector. It's reflected back as a negative wave. And you want to set the length of the exhaust system so that negative wave arrives back at the exhaust valve to create negative pressure in the chamber when the intake opens. So basically, in emissions, this is kind of like a little EGR. If it's cracked a little bit, you can actually do some good things to emissions. You do need to know that this whole thing works together. So the exhaust opening is the highest pressure. That's the beginning of your wave tuning wave. Then everything else kind of is triggered off that super high pressure. Now, where people would get a little goofy about this is looking at overlap. You can see that you can get all caught up with this peak piston velocity that occurs about 70 degrees after top dead center. And so where do you open the intake to try to get peak lift there? If there's a limit to how quick you can open it and you want it open as much as possible there, that's why you got the Ultradyne type deals that delayed the IO and then went super fast. And I kind of joked with those that, you know, if you slap the spring really bad, you get into some issues. So we try not to do that. The intake closing is the most important deal in this whole combination. You know, is once the intake closes, the air stops moving through the port. Earlier intake closings are better for low RPM. Later intake closings are better for high RPM. But one of the things that we want to see is, check this graph out. You look at the first graph, you see the momentum keeps filling it well past bottom dead center. As soon as you close it, now you start the compression stroke. But how I showed in the second graph on the right, that lift at bottom dead center is super important because there's a lot of flow there. So let's see how we'd use this. Here's a plot in blue of a normal big block Chevy drag race cam with a normal profile compared to our new low shock lobe. And you can see the new low shock cam has the earlier EO, but yet the steel piston valve, but a much later intake closing. Now, when you go for a low shock opening, it doesn't mean that you're going slow the whole time. It just means that you compress the system before you really get after it. One of the things we'll call it sometimes instead of a slow shock is a crack and whack. Get everything going and then really push harder. That's why you have the same area on the opening side, even with that slow early opening. But because if you think about the spring as your dancing partner, and think about marriage, you've heard happy wife, happy life. Same deal with this. If I can go a little slower early, keep the spring from doing that surge that we saw in the video, then I can ask more of it on the backside and get this earlier intake closing that I'm talking about with the same backside area. But now with this cam, you're actually going to have a much earlier intake closing, so it's going to act like a smaller cam. So what can I do to avoid that? Well, what I can do is spread the lobe separation out a tiny bit, 1 degree, go to something with a little more lift to get a little closer to coil bind, add 4 degrees duration, and then all of a sudden I'm picking up all of this backside area with the same intake closing. So this cam looks like a slower camshaft, but it actually makes a lot more power, and it allows you to put a bigger camshaft in it with a slower lobe without hurting it anywhere. Now you guys are going to go, does this stuff really work? Well, here's a test that Jeff Smith just posted to Engine Labs here on the 12th, and he did this test at West Tech. He took our best LS cam from a couple of years ago and then compared it to our brand new low shock cam. And here's the power difference. Note that we're up, you know, this is similar spec camshaft, left to right. I welcome you to go look at the article. But you can see that we're making 16 more horsepower and we're carrying out easily an extra 500 RPM. So basically, I run a little over, but I appreciate you guys letting me do this. Here's the conclusion question. I want you guys to know that's AER Save 10. If you buy anything on our website, there's already some discounts, but you can save additional 10% or something like that if you do the AER Save 10. And let us know how we can do questions.
All right, Billy, we got a couple questions that came in.
Okay.
What about a turbocharged engine which may have a greater intake manifold average pressure than exhaust manifold average pressure?
Yeah, that's a great question. What's going on with turbo deals? Our first question when somebody calls in a turbo is, what is your boost to back pressure ratio? You know, a lot of the stuff you read about turbo cams, read David Vizard's books from the 80s, they had 3 or 4 times the amount of back pressure to boost. Today, what you're seeing is that normal camshafts for professional racing turbo systems where you have that 1-to-1 ratio or even less to 1-to-1 ratio through most of the pull, they wind up looking a whole lot like the same camshaft that you would see in a normally aspirated motor. Where the real difference will be in these is that the ones with the good turbos is they'll be slightly shorter duration, because all of a sudden now the cylinder head that we thought flowed 400 CFM, because you've got such a more dense charge, now it acts like that is that's a 500 CFM head or 1,000 CFM head. You know, it's like drinking Diet Coke versus drinking a Frosty. I hope that helps.
Okay, our next question, as they keep coming in, do you favor an asymmetrical exhaust lobe with a more aggressive opening over a gentler symmetrical lobe?
I've played with that a whole lot. A lot of times we were going with, like, if you look at our CPX series and our NXX series, those are definitely like that. They're a little slow very, very early, but they get after it. Once the valves open 50 thousandths, they go really, really fast. Where you get in trouble with that is, like, if you took a top fuel motor that has a lot of has less stiffness in the rocker arm and has tremendous exhaust pressures, you can't get back into the throttle at 50 thousandths. That valve's probably not even off the seat. So you really have to go with some, it depends, it's very application independent. Another thing is, like, guys running sprint cars run really fast exhaust lobes. And the problem is, if you run a fast opening exhaust lobe, is the guys who do it well normally have a wall full of either headers or a wall full of collectors and links they can play with. Because when you open the exhaust really fast, you wind up making that waveform very, very sharp. So if you think about that, when you make it really sharp like that, you wind up with it coming back and being very, very strong, but not very broad. So a fast opening exhaust is going to be very header sensitive. Where if you take a more symmetric type lobe and run it on the exhaust, not truly symmetric, but more symmetric, it becomes much easier to tune, because it's going to have a slower wave opening. And so when it comes back, it's not going to just be, if you're a 20-inch header and a 30-inch header and a 32 and a 34, if you have a real fast opening exhaust, it's going to want one of those and hate two of those. If you run something like an XX profile that's very smooth, or XNX for a newer one, it's not going to be nearly as sensitive on the exhaust opening.
Okay, our next question is, what do you do differently when speccing a performance diesel camshaft versus a performance gas camshaft?
Well, that's a pretty interesting one. A performance diesel camshaft is going to normally be much, much smaller. You know, you'll see guys that'll go in there and go, hey, this diesel goes almost 4,000 RPM. It probably needs a 230 duration camshaft. Well, the problem is, if you put a 230 duration camshaft in it, you're going to have to put on tight lobe separation to get to tune there. If you do that, you're going to carve up your piston so bad that your combustion efficiency is going to be horrible. So unless you're running like nitrous, propane, and 60 pounds of boost, those big carvings that carve out that you've done the piston is going to tear the thing to shreds. So you would just absolutely be shocked how well, because of all the boost, because of the density of the air, how well short camshafts, 188 at 50, 191 at 50, 200, 205 at 50, a much smaller camshaft becomes very, very good. And that's where some of the stuff that we're doing with this low shock technology and the new cam designs is extraordinarily valuable, because if you learn, making a big duration camshaft smooth is easy, because you've got a lot of time for the spring to recover from the opening to the closing side. When you start making really short duration camshafts and try to put a lot of area in those, that's a much more difficult problem to solve.
Perfect. Okay, our next question is, cam bearing and journal clearances. It's a two-part question. Say for
this is a great one.
Say for a 2-inch journal size, what would be the minimum oil clearance you would run on, say, an LS at about 5,000 RPM?
Okay, I'm going to tell on myself. We had LS bearings, 2165 bearings in a NASCAR block, and I messed up and put a camshaft in it with big block Chevy bearings in it. and we ran an entire durability test before I figured out what I screwed up. After that, I was totally convinced there's only one reason that you want, one reason and one reason only you want tight clearances on a cam bearing, is you're talking about the inside of the bearing to the outside of the camshaft. The only reason you'd want that tight is because of windage on the crankshaft. So, you know, you can run 2, 3, 5, you know, and never hurt anything in the world except for a guy running 5 thousandths clearance on his camshaft to the shell. He's going to have a lot more windage. He's going to have a lot more oil fall down than a guy running, you know, 1, 2, 2.5, 3. So I get really nervous with very, very tight clearances. We see that all the time in our world because racers like to run a little bit of extra crunch on their blocks. So if they're doing an LS, they're like, hey, I'm going to run this with an extra 0.5 thousandths crush. And when they do it, it makes the inside of the bearing tight, and then they run a standards cam size and it tries to seize on them. I've never, ever seen a failure because the guy was running too much clearance on his camshaft.
Okay. Next question. How does an inverse radius lobe compare to the low impact lobe?
You know, almost any camshaft that you'd see for a small journal, like a small block Chevy 1868, big block Chevy 1948, 1949, almost every one of those roller camshafts is going to have some section of it that's inverted radius of curvature. In fact, because remember when I talked about the low shock, I called it the crack and whack. Well, that's actually pretty difficult to do in a small block Chevy or a big block Chevy, because if you're going to go slow at first and then catch up, it's really hard to catch up. The reason I think low shock took a long time to come around, you know, people were playing with this technology in the Glidden days and doing really well with it. But as springs got better, what happened is we just didn't have enough ability with standard rocker ratios and small journals to use slow fast, you know, to ease into it and then go. So we kind of had to just get a running start. And if you think about it, think about an NHRA Superstock guy with a 50-pound flywheel revving up to the moon and dropping the clutch to get the car off the line. Very similar. This is the type of things that people had to do. They ran really fast openings and a lot of lash because they couldn't get energy into it. As we have higher ratios now and we have bigger journals, we can do some things we couldn't do before. So the low shock stuff is definitely better on the 50, 55, 60 millimeter journals than on the standard journals, but we're using it some on the small blocks and had some very good success. It sure does like a little more rocker ratio though.
Okay, next question. What do you consider to be the maximum allowable surface chatter around the face of a lobe?
You know, to talk about that, you really have to go how you're going to measure it. The best measuring tool I know is on the AgCol, and it's a fast Fourier transform. They call the program Spectrum. And generally, you'd be surprised that maximum chatter you can have is about 10 to the minus 6 inches. So it's a extraordinarily small amount of chatter. If you can look at a camshaft and see chatter that's down in the 10 to the 7th inches. So if it has the same chatter all the way around it and you get fluorescent lights, you get on a good table, you can actually see chatter down in the 10 to the 7th. So if you see visual chatter, there's probably an issue. And especially if you get an eye for it, you can see where you have problems. You know, what's funny is we used to think it was servo chatter in the CNC grinders. Sometimes you get in there where actually the camshaft between centers and the grinders starts to vibrate. And it's kind of a very interesting deal because we started seeing different chatter on different lobes on a CNC. It's like, well, that can't be a servo. And that really brought us in. So we've changed all of our grinding wheels over on our CNCs. They used to be steel hubs. Now they're all carbon fiber hubs. And that carbon fiber has just enough, really not compliance, but it actually has enough absorption of high frequency that it takes out a lot of the chatter of the camshaft in between centers or in between steady rests.
Okay, our next question is, how does lifter roller wheel diameter affect lobe profile choice?
Like if you have a bigger cam journal or a bigger lifter wheel, it really lets you go to a little bit quicker profile. And the reason being is you get less torsional vibration of the camshaft. we didn't talk about this in this presentation, but I did in my AETC a couple of years ago. The camshaft doesn't turn at constant RPM. On the NHRA Pro Stock, when they were going 11,000 RPM, you can see on intake opening it's slow all the way down to 8,500, and then on intake closing it's speed all the way up to 13,000 RPM. It's crazy how much torsional vibration you get in the camshaft. As you go to a bigger wheel, you put less pressure angle into it. It creates a little bit less of those torsionals in the camshaft. So one, you want to have a camshaft that's designed for it. We use a master suffix. So if you go from a 50 millimeter cam with a 750 wheel, that'd be an R suffix. If you did it with the 850 wheel, that same, it'd be an RG. If you did a 60 millimeter with the 850, it'd be an MG. And if you did a 60 millimeter with a 950, that'd be a RH. So we went ahead and made different designs. So the tappet moves the same. The bigger wheel, you need to have a cam design for that wheel, but it does allow you to perhaps move up just a skosh on aggressiveness and move down just a skosh on duration. When I talk about skosh, like 2 degrees.
Okay, getting to our next question here.
By the way, great question, guys. I mean, that was tremendous.
Is it better to run a lower lift cam with a higher compression on a naturally aspirated street engine, like 11.5 to 1, 588, 570? And can I still achieve 6,500 to 7,000 RPM rev limit with conical springs?
Okay, last question, yes. Now let's go back to the first question. Lower lift doesn't, what's funny is that peak torque is peak air demand. So generally, as long as your head is still going up in flow, you want to maximize the valve spring lift. So if you have a spring like a conical that's designed to run 625 lift, you don't want to run at 575s because now instead of being 50, 60,000 combined, you're 110, 120, 130,000 combined. So you got to be careful. You know, you kind of want to pick, if you're going to run 550, 575 lift, you want to pick a 550 or 575 lift spring. Now, the thing is a lot of people think the extra lift hurts them, and I have never seen extra lift hurt on the intake side. There may be some turbulence deals, some really old heads where I think I saw it, but I'm not even sure. If you ever watch John Causey has this video where he sticks his finger into a port when it's running, you start realizing you don't have steady flow to that port. It's not like a flow bench. So basically, if you want to run 575 lift, that's great. The head may not really, there's a lift to diameter ratio. So in a 2-inch valve, you may not get a whole lot going from 575 to 625, but try to run the lift around the spring. And I really don't think you'll see any correlation between compression ratio and lift. You'll see a difference between compression ratio and intake closing, but not compression ratio and lift.
Okay, looks like we got time for one more question, I think.
Well, I'm sorry I ran over on my part of it. I tell you guys, I really enjoyed it, and I'm loving the questions.
No, it's great. We got a lot of good questions coming in. Does LSA really matter for EFI to carburetors on LS engines?
90% of it's no. Usually you can't put the lobe. The reason that carburetors generally like tighter lobe separations than EFI is that airspeed matters through a carburetor more than it does through an injection. Now you're pulling me right outside of my bailiwick and put me right into Ben Strader's, so be careful here. But you need that air moment, you need that air volume, you need that momentum, you need that charge, you need that signal through the carburetor to get the boosters to work right in a carbureted application. The EFI system, you really just need the air in there. So sometimes on the carburetor, that extra overlap puts some more air, and it made the carburetor much more responsive at low RPM with a real tight lobe separation and more overlap. Now you ask about LS in specific. The interesting thing about LS, unless you change the pistons, you really can't put a lot of overlap in an LS without crashing the valves in the piston. You violate the space-time continuum. You made a cam and the valve, things blow up. It's bad. You don't want to be there. I've been there. It's ugly. So if you don't have room anyway, then the camshaft becomes exactly the same. If you're not changing the piston on an LS, the carbureted cam and the fuel injected cam are the same. If you do change the piston, it just depends on how interested you are in low RPM throttle response. If you need the absolute most, say you're dirt track racing and all the passing, it's a really tacky track that you run at, all the passing comes out of the corner, you're going to need a tighter lobe separation to make that carburetor work the best it can with throttle position changes. And I think that's one thing that as an industry we don't talk about enough. Engines normally aren't run like they are run on a dyno. On a dyno, they're loaded. They go up to a certain RPM, they stabilize, and then they accelerate very smoothly. In the real world, we're always changing throttle response, throttle position, and that creates something totally different. So to get that throttle response that you want, the lobe separation will be tighter because that carburetor needs more overlap, because it needs more air going through it to atomize, to pull the fuel through the booster, to atomize it well, and to make it work. The fuel injection is going to be pretty dumb. It's going to go, I don't care how much is going through my throttle body. I just care how much you told me to give at this RPM in this throttle position.
Okay, we actually got time for a couple more, Billy, if you got time.
Sure. Oh, I love it. This is my favorite part. I hate the presentations. I love Q&A.
Gentleman's asking, he's heard that the racing turbo motors are running higher compression ratios now. Older days 8-to-1, now I hear 10-to-1. How does this affect the cam profile?
It really doesn't change the cam profile. I mean, the thing is people think, oh goodness, I'm running 20 pounds of boost. I can't run the 6-to-1 compression, 8-to-1 compression. My son is working on his PhD in combustion right now. He's specializing in diesel, but he knows the gas pretty well too. It is absolutely amazing. It is not uncommon at all to see people run super high compression ratios with E85 and even higher compression ratios than you'd think on gasoline. The more nitrogen you put into the chamber, you cool it down. As you put more and more fuel, there's things that are going on in a turbocharged motor that don't go straight over. So you really don't generally we don't change camshafts very much based on compression ratio. The reason we put a little bit, you see bigger cams with higher compression, is because bigger cams act super bad at low RPM without compression. So that's why you see this cam needs 13-to-1 compression. What that really means, you read it, is if you put this cam in something that has 10-to-1 compression and it doesn't have boost, and you try to go full throttle at 3,000, it's going to misfire and be a pig. But under wide open throttle, we saw this when NASCAR dropped back from 15-to-1 to 9.5-to-1. That basically the cam durations, we thought they were going to change 10 degrees. They changed 2 or 4. And they only changed 2 or 4 for the very low RPM stuff.
Okay. Our next question here is, and they say it might be a little bit off topic, but they were wondering if you could address the mythology of rocker axis perpendicularity to the valve stem. That's a long word for me. I know exactly what
he's asking. Yeah. You know, when you look at a rocker arm sweep, here's the rocker arm of the valve, where does it get perpendicular on the valve, and where does it get perpendicular on the push rod? And this is all about design rocker ratios. And T&D has one school of thought, and the Jessel guys have another school of thought, and other guys have different schools of thought. And if you ever want to get into something that's like a religious argument, get into that argument and say, hey, which one of these guys is right, which one of these guys is wrong. As a cam designer, I've actually learned to work with any of it because we deal with overheads, the finger followers, and they sweep different on the opening side and the closing side. So all of a sudden you get really good at designing at the valve, and you can coordinate, you can do a coordinate transformation, go back to what you need in the cam profile to get the valve to do what you want to do. The engine only responds to what the valve does, not to what the cam does. So I can fix that where it works any which way. Now, if I was going to design a rocker arm, I'm going to tell you that I'd probably have the tip go perpendicular somewhere between 30% and 50% lift. The reason I want to go perpendicular then is because I know that's when the push rod loads are the highest. And so I want that rocker arm to be as stiff as it possibly can be at that point. I want no wasted energy. Likewise, I probably want the push rod either close to perpendicular, somewhere between the base circle, because then I get the least wasted motion, to about half lift. And so even though it doesn't make the most constant rocker ratio, something that goes perpendicular on both sides around 30% lift is what I personally like. Now, if you personally like something else, I still want to sell you a camshaft. And I absolutely positively can design around any rocker geometry system that you can imagine. So it doesn't affect me, but as far as if I had to pick a church of where to be, I would be close to 25-30% perpendicular on both sides.
Great.
And sorry if that was inside baseball to some of you guys.
Well, I'm glad you knew exactly what the question was before I finished.
Yeah, it's a hotly debated. There's about a dozen people that care very vehemently, and there's about 1 million people that don't even know what's going on there. And I wish I was in the million, not the dozen. But oh well.
Okay, our next question is: I'm not seeing low shock cams for cathedral ports. Would the LSR cathedral port cams be a better choice over the rectangular port LST? And how specific are the cams designed for the individual port designs?
Really, they're not. We do have a low shock cam for the budget cathedral port deal. It's called a drift cam, but it's not. It's a 54778-11. And it's for a real inexpensive budget type deal where somebody wants to use our new LS6 Plus spring. I think its part number is 26906-16 or 26906-kit. That system is a beautiful system for somebody who's trying to take a junkyard motor and make it into a race motor. But honestly, I've sold a bunch of people that are running 5.7s, the 54-301-11. That's our smaller of the LST kits, and that runs amazing in a good, in a 5.7, 6-liter, cathedral port engine. I think it probably actually runs better in that than it does in the LS3, and we probably should have marketed it different. But it's just a super all-around camshaft in a cathedral port.
Okay.
And definitely beat on sales to get more of those, because I love making those packages. They're kind of fun.
Okay, our next question. At one time, inverted flank or peanut lobes on roller cams was the craze. Is this still the case? And if yes or no, discuss the merits and disadvantages.
Like I said kind of earlier, that almost every roller camshaft for a small journal is inverted. Now, what's funny is I wanted to come up, when I started at Comp Cams, all of the extreme energy hydraulic rollers are inverted flank lobes. And I mean, they're inverted as much as the grinder will make. But when we did the XE cams, I wanted to call them IR cams. But Scooter said, "Oh, you can't call them IR cams. People think IR cams blow up." The inverted race curvature isn't what blew up anything. What blew up people's engines with the early IR cams, those peanut lobes, was how quickly they went into the inverted flank section and out of the inverted flank section. So sometimes cam designers learn a new technique and they get a little greedy and they try to take full advantage of it. The inverted section usually is pretty happy, but how quickly you get on the gas and how quickly you come off the gas going into that inverted section and going out of the inverted section determines the harmonic content of it. It's what causes it to go crazy. So basically, any lobe that you see that's specifically designed for a small block Chevy, a small block Ford, or big block Chevy size journal, that cam is inverted. We just don't talk about it because inverted got a bad name, so we don't really promote it very much. Now, the thing is some of the early attempts at inverted racer curvatures, I know Crane had an IR series that had skulls and crossbones on it, and our TK series is really, really inverted. Some of the early attempts at inverted camshafts, we probably pushed things a little more than we should have, and we probably got ourselves in a little bit of trouble. But the inverted is not the cause of the trouble. How quickly we got in the inverted and how long we stayed before we got out. And it's very much like driving a road race car. How soon you get on the gas, how rapidly you roll on the gas, and how soon you get off the gas going into a corner on the brake. If you allow the car to transition, it's very, very smooth. Even though you're already on full brake and you're already on full gas at some point, it's how well you how you change the car from full brake to full gas. Very much with the inverted flank. The inverted flank doesn't break anything. How quickly you get on the gas to get to full, and then how quickly you get on the brakes. If you make that transition too quick, you will upset the valve spring. You'll let everything go into loft, and the problem with loft isn't loft. Loft's great. It's kind of like jumping the ramp over the bus if you're Evel Knievel. Jumping's great. Landing can be bad.
Okay. Next question. Low shock lobes and street durability for a daily driven vehicle, say about 10,000 miles a year. Is there a durability issue, or is there a threshold that makes you nervous?
No, absolutely, positively. If I was going to put anything in something I was going to try to drive 10,000 miles, 100,000 miles, it would absolutely be a new low shock design. They put so much less early deflection. They're so much easier on lifters. They're so much easier in valve springs. To give you an idea, on a bracket race car, I took a guy who was going about 25 to 50 passes. He changed the springs at 400 passes because he felt guilty. And his lifters look better, the cam look better, everything looks better. You'd see the same thing on the street, that the low shock is definitely the way to go. Which low shock cam, that could be interesting on what you're going to do, but 10,000 miles, that's not going to hurt these things at all.
Okay. And then our last question we got here, and then we'll give away some more prizes. On a roller cam, how large of a pressure angle is used on really aggressive cam designs, and how large of an acceleration value has been successfully used?
Well, here we really need to talk about acceleration values at the valve, not at the cam, because really the cam doesn't matter. It's how fast we're accelerating the valve. So let's start with pressure angles. Pressure angles, when they get much above 30 to 33 degrees, they really tear up lifters. I did one with the Briggs that was 40 degrees. It broke the lifter the first time we turned it over by hand. The old NHRA super stocks, when they were running stock journal sizes in the small block Chevys, they were up around 31, 32, and blocks would only get about 40 or 50 passes before they just trashed the lifter bores in them. Clearly, once you start doing some good clawed stuff and you start putting good bushings in it, you go a little bit more passes. But once you get past 30 degrees, it really, really tears up lifter bore angles. Now that journals are bigger, I can tell you that it may have been, I've never looked at the pressure angle on an NHRA Pro stock lobe, because they're always 60 millimeter plus journals. They never have high pressure angles. I know when you reduce the pressure angle with a bigger wheel that your torsionals are less, but it's really not the driving factor in anything. Now, going back to the first question about the lobe accelerations, you start looking at it, and does it really matter what the peak acceleration is? Because remember, when we're doing these high lash lobes, non-low shock, we might only be running 3.035 inches per degree acceleration at the tappet, but we were running 35,000 slash, and we were crashing the thing early. So you had huge dynamic accelerations. So who's to say that you can't run 20, 30, 40% higher tappet accelerations if you don't have all of this compliance and you don't have all this crash? And some of the NASCAR teams have measured deflection. We've measured push rod loads. We can see kind of what's going on with deflection with the laser, with prox probes. And I can tell you that the valve acceleration isn't nearly as limited by tappet acceleration as we really thought it was. That we were getting double and triple the valve acceleration that we thought we were getting because we were like a pole vaulter. We were running up there and we were jamming the pole into the pit and making it bend and storing all this energy and then slinging ourselves up. Now that we're putting that pole in smoothly, we can run much higher accelerations later. So, being an extra 10, 20, 30%, 15% wouldn't even be a break-even point. That you'd see. That's why it's hard to do low shocks on small journals where it's easy to do on big journals, because I can't run an extra 20% higher acceleration on a small journal, but you really can on LS and definitely on modern engines.
Okay. Billy, thank you for your time. Great presentation. Great answers to the questions. If you guys didn't get your question asked, remember we are doing a roundtable at the end, so we will be asking some of those questions to our panelists at the end.
Yeah, great presentation so far, everybody. Man, it's just a sponge here, learning all kinds of stuff. And so yeah, we've got a few minutes, everybody. What we'll do is, again, this would be the time if you want to take a break, go to the washroom, maybe grab a snack or something like that. What I'll do is I'm just going to flip forward here just a couple slides here for you. I just wanted to show you a couple things that we've been doing here in the background at AERA. And I'll just go forward here just a few slides and just show you what's been going on. So we've been working hard with PROSIS Pro. We've been spending lots of time lately on it. And a lot of shops, what they're doing now is they've gone to a mobile device. Like we have a lot of shops that are taking the PROSIS Pro software and loading it onto a tablet. And what this does is it just gives you a lot more mobility. I mean, you're able to, rather than go to your printer in the shop and print something off, take it back to your assembler and that kind of stuff, we've been working to do it this way where we can put it on your phone or have it really accessible on a mobile device. So we've done that. We've got it all formatted. And that is another thing that shops are doing that makes it very handy. The other thing too, keep in mind, everybody, if let's say your internet service is not that good and you're using PROSIS Pro, we do have a thumb drive that we can send you so that you can put it on your desktop. So you don't have to rely just on, really great internet. There is an option for PROSIS Pro to put it on that thumb drive, and you can do it that way. In the background here at AERA, like all us techs, the internet version is still your best version because we literally update those specifications every single day. So that's the way to go. I mean, we're on there. We're adding new engines, like I mentioned earlier. We're at 10,000. At just over 10,600 engines now. So it really is a large database. And we've got everything in there from Z-Tor tractor, to a lot of stuff, a lot of engines that we don't even see here in North America. But a lot of times in our shops, we're getting a lot of right-hand drive vehicles that we're working on, a lot of oddball engines that are in some of these vehicles. So we have those engines loaded in PROSIS Pro to be able to help you there. So keep that in mind. That is available for you. And the other thing too with PROSIS Pro, and what I'll do here is I'm going to go to a live screen here just to kind of show you some of the stuff that we have been working on so that you've got it. And so a lot of you that are familiar with PROSIS Pro, I mean, you're used to seeing this screen already. And you know that this is the dashboard. So this is kind of where, we'll show some of our current events and you can download the magazine and that kind of stuff. So you've got that availability to do that. But the one thing I wanted to show you, and this is a couple little tricks here. So let's say you're in PROSIS Pro and you were looking up a particular engine. So let's say we look at, we're going to look at, for example, like a Daewoo engine. And if we go search, and it's going to bring up every single Daewoo engine that we've got. But I wanted to show you this is over here, before you even go to the lookup of that engine, and a lot of people don't realize that there's some little shortcuts here that you can take advantage of. The first thing is that you've got it'll tell you whether that engine is an interference engine. So if you see the red circle, I mean, that literally means that is an interference engine. Valves are going to hit pistons for that. So without even going any further in the program, have a look for that and you'll see that. And yellow circle means that we're unsure of that particular engine. And of course, green circle, that means that it is a freewheeling engine. So it's good to go. The other thing I wanted to show you here, we just got a couple more minutes. Keep in mind, rather than go into the engine lookup to find, for example, a technical bulletin or a image or a diagram, you can do that right from your lookup right here as well. So when you see this thumbtack, you go down, you can see it says, there's 4. So that means there's 4 technical bulletins there. Simply click that and it'll bring up those 4 technical bulletins and it'll show you that for that particular lookup. It'll do the same for diagrams. If I return back, and we see this little camera right here, and I click on that, it'll take you right to the diagrams and show you the diagrams for that particular engine. So just a couple shortcuts there. I didn't want to take up too much time, but it just, again, we're on the tech line too. I mean, if those of you that are using PROSIS Pro, give us a call anytime. We want to see you use this program right to its fullest. We really enjoy that you can use every portion of it because it's there as a tool, and of course, there's nothing worse than a tool in the toolbox you don't take full advantage of. So Keith is our next presentation. Keith Jones, it's cylinder honing for modern piston rings in the 21st century. And Keith's always a big help to us. and he does a lot of our presentations at our seminars and our technical regionals and that kind of stuff. So Keith, how's it going today?
I'm doing well. I'm doing well. How about everybody there?
Yeah, no, we're halfway through. Hopefully everybody's enjoying the presentation so far. So I'll let you carry on, and we're here listening, and we're here for you.
I appreciate it. I want to thank everybody for attending and doing this. I've done a lot of these in the past. I've always had a lot of fun doing it. This is kind of different, not standing in front of everybody and looking at all their smiling faces. So like I say, kind of a different thing, and definitely want to tip my hat to the other presenters. Great stuff, and the AERA folks, appreciate you putting this on. It's a difficult time that we're all dealing with, and I know for like Lake, I mean, he hasn't been out of his house in months, and kind of feel the same way here. So again, thanks everybody. I really appreciate you coming and attending this. But what we're going to talk about today is what's changed, what's different. Engine blocks have changed, rings have changed, oils have changed, and all of that affects how the cylinders are honed and what we have to do to get the finishes that we want to get. So here we're going to kind of touch on a few things, and it's what's changed. Cylinders today are much harder than they used to be in the old days. Blocks back in the 70s, 80s, they were pretty soft, and you could get away with a lot of things. It was pretty easy to hone. The rings had a lot of tension to them. The coatings were very soft, and that's really not what we're dealing with today. So the blocks have changed a lot, and there's exotic coatings, and we'll touch on that stuff as we dig deeper into the program. Rings today, as we've all seen, much thinner, much lighter tensions than they were even 10 years ago. And then to go back 20, 30 years, much thinner materials, much lighter rings, and like I say, some really exotic coatings by comparison of what we used to have in the old days. Again, oils, much lighter viscosity. I can tell you my own vehicle, my own Chevy truck, 0.5, what are you, out of your mind? It's Arizona. It's hot out there. I had to put a 510 in it. I couldn't, I just couldn't do the 0.5. and what's the point of all this? We're trying to squeeze more energy from less fuel. So much of this technology is race driven, but it's also OE driven. They want to get less friction in the engine, which means more fuel efficiency, less tailpipe emissions. And it's the same thing out of the race world. We want to take that molecule of energy and extract everything we can. So if we can get the friction down in the engine, the rotating losses in the engine down, we're going to put more power to the drive shaft, more to the wheels, propellers, whatever it is that you're into. But if we can make that engine consume less of its own energy internally, we're going to have more to deliver to the output device. Ring materials. Again, we go back to the old days. Rings were always made out of irons. Typically from the early days, they were made out of cast irons. Cast irons are very soft, they're brittle, they break, they wear quickly, and don't handle temperature very well. Again, we deal with much higher heats today than we did in the old days, much higher exhaust gas temperatures. We're dealing with unleaded fuels, and it's pretty easy to take a cast iron ring out in a high performance engine these days. So we really don't use a lot of cast irons. Ductile irons are still popular, still around, and they are very malleable, wear well, good flexibility. They're very durable, accept coatings fairly well, have good thermal transfer. Common coatings to see on a ductile iron ring are like chromes or moly. And I'll take a wave of hands. How many guys out there run a chromoly ring? Well, as a lot of us know, there is no such thing. The ring, what we're talking about is either the coating. It's either chrome or moly. It's not both. We're not dealing with tubing. So there were times when you had double chrome, meaning chrome top, chrome seconds. You had double moly sets, moly top, moly second. But today we pretty much run just a coated top ring and a non-coated second ring. So the whole chrome moly thing is kind of, like I say, kind of a misunderstanding. Manufacturing iron rings have to be poured in large quantities, big castings. You got to go to a foundry. You have to have castings poured. So there's a lot of wasted material, a lot of scrap. And where that's going is, the industry's gone to steel. This is a quick shot of what iron rings look like. Rings either come out of what's called a ring cuff, kind of a casted piece, looks like a rough cylinder. You ID it, you OD it, you slice it, you dice it. Or as you can see in the lower right corner, a ring tree, where they're casted very close to the sizes, basically the right IDs and ODs. If you look at that picture, you can actually see there's an inner and an outer ring, a smaller bore and a larger bore. So you'll take those pieces, you'll basically break them out of there like a model car kit, like a tree. And then again, ID, OD, heat treat, put the gaps in. But as you can see, there's a lot of machining involved. There's a lot of wasted material. Hence steel. I don't want to say we were the first people to get involved with using steel rings, but because I've seen steel rings all the way back into the 20s and 30s. But here in the States, we're one of the first. And what we found with steel is better durability. We use quite a few different steels here, from all different types of carbon steel, stainless steels, tool steels. We have some hybrid type materials. We actually work with a company called Materion, which is a materials specialist. We actually have a copper-based alloy that we work with. So depending on the needs of the end user, there's different types of material, and what that comes down to is heat. I like to say heat puts the tension in, heat takes the tension out. So there's different temperature thresholds that we deal with depending on the material. So if I'm dealing with an extremely high temperature environment, we're going to have to look at materials like tool steel. And as Billy mentioned earlier, there's a lot of different grades of tool steel. We work with M2. On our stainless steels, we work with a material called 440B. And there's different temperature thresholds at which that part heat treats, and of course the heat puts the temperature, the tension in. Heat can take it out. So kind of depending on the application, we would need to deal with you, talk with you, and say what's the right material for what my application is. Thermal transfer is very good with the steels, similar to the irons. But with steel rings, we open up a whole range of different coatings that can go on there, particularly PVD style coatings, mollies, CRNs, C72 titanium nitrides. We'll get into that a little later. The biggest thing about steel rings is the manufacturing process. We can do it out of coiled steel. Instead of having to pour the material, machine the material like that, we actually comes out of a coil of wire. So I actually have videos on our website you can look at, and I've got some actually on my laptop we could probably show later, but that's what a steel ring comes out of. It actually comes out of a big spool of wire. So when we do it, we actually cam coil the material. So there's very little scrap. I can actually cam coil that one ring, produce one ring. Instead of all this machine material that's left over, I end up with that one ring with very, very little scrap. So very little material has to be recycled. And in the big picture of things, it ultimately helps keep the cost down. So rings have changed from iron-based parts into steel-based parts because we can do thinner rings, lighter rings. It'll accept coatings that iron-based rings don't like to use. And again, helps keep the manufacturing cost down. And this is just kind of a visual representation of ring thicknesses. These are actually to scale. So you can see on the very bottom row, we've got the 1/16th, the 1/16th, and the 3/16th, which just a few years ago was considered the thin ring package. Then we've got the more modern 1 millimeter, 1 millimeter, 2 millimeter, which has become very popular, much lower friction, much lower drag, better bore conformability. And then even smaller than that, the 0.9 millimeter, 0.92 millimeter combination that we offer. Very nice ring package, very low drag, excellent bore conformability, less mass. And today we're doing rings as thin as 0.5 millimeters. So if you put that into thousandths of an inch, you're only talking 20 thousandths of an inch. Very small. It's about the size of an oil ring rail that would be on that 3/16 oil ring. So if you kind of put that into perspective, that's actually a compression ring that we do today, and they hold up very well. And that's because of the material technologies that are available today. Excuse me, I've got an itch. Wanted to show you this graph, and it kind of talks about ring tensions. And again, trying to show a little bit of history of where rings have gone. A 5/64 ring, and these were all done at 4/185 bore, by the way. The 5/64 ring with 190 depth, ductile moly ring, checking at about 7.3 pounds of tension, 7.5 pounds. And as you can see, as you're going smaller and smaller, lower and lower, the ring tension goes down significantly, all the way down to like a 0.7 millimeter ring, where we're down to about a 0.5 pound of tension, 0.7 pounds of tension, extremely light, extremely low friction, extremely light load on the cylinder wall. So it really significantly reduces bore wear. The rings last longer. People have a tendency to think that, thinner rings don't hold up very well. Wow. I mean, they're, again, like I said, there's guys that are still thinking the 16th ring is the little guy. And it's actually kind of the opposite of what you think, or a lot of people think. As you get into the thinner rings, they're much, much easier on the cylinders. They don't wear as poorly. They don't wear the bore. I have many, many race applications out there today that are going in excess of 4,000 race miles on 0.6, 0.7 mil rings, because again, they're so easy on the bores, they're so light on the wear, they just don't wear the parts out. And you can look at the bottom part of the page, looking at oil ring tensions, and I want to kind of touch on this in particular, because there's kind of a little bit of a misunderstanding out there in the industry, and I want to take a moment to correct this. Again, this has nothing to do with cylinder honing, but I want you to be aware of this. Oil ring tensions, a common statement that's used is standard tension or low tension. And what you have to remember is those standards are relative to the size of the part. What is standard tension? Well, a standard tension 3/16 O-ring is typically in the 20 to 25 pound range. A low tension 3/16 O-ring is typically in around the 15 to 16 pound range. And that's pound force. That's what it puts against the cylinder wall, not sliding friction up and down the cylinder that we would check with a fish scale. A lot of guys use that because that's the equipment that's available to them. So they'll fish scale and kind of look at sliding friction, which is a little different than how we test it. We actually test the tension or the force that it takes to compress it down to that size. But if you look at the next level down, the next line down, I should say, the 3 millimeter. I get this thrown at me all the time. I want a standard 3 millimeter. So it comes back to the question of what are you referring to as a standard 3 millimeter? A standard 3 millimeter is about 10 pounds. So are you asking for a 3 millimeter that's the standard for a 3, or are you asking for a 3 that's about the same as a 3/16? So you have to be careful with words standard tension, because standard is relative to the size of the part. Same thing with a 2 millimeter oil ring. A 2 millimeter oil ring is typically about 7 to 8 pounds. That's standard for a 2 millimeter. Now we can make 2 millimeter and 3 millimeter, they're much higher. We can make them much lower. So it's really kind of a matter of knowing what your application is and how much oil ring tension does it need. You know, if it's a street car driving every day, wet sump engine, you're probably going to want something more than 9 or 10, especially in an engine like a small Chevy, big Chevy that was designed around a much, much higher tension oil ring. You go back to oil flow, oil volumes, how much oil is being thrown around inside that engine. And there's many chances, many cases where it's going to take a higher tension oil ring to keep that engine dry. So just wanted to kind of hit on that real quick, just to be aware of what standard tension means. And it doesn't mean it's always the same number. It doesn't mean it's a 20-pound oil ring across the board. It means it's standard for the size of the part. Lake had talked about a little earlier in his presentation, showed you some hardness numbers. And these are some illustrations of actual ring face coatings. And in the upper left, as you can see, we've got cast iron with no coating. Fairly porous area, but no anti-friction, no anti-wear, very soft material. The one I want to kind of concentrate on, though, is the one in the middle top, molybdenum. It's about 800 Vickers hardness. And one of the unique characteristics about molybdenum is it's very oleophilic. It holds oil like a sponge. So keep that in mind as we move forward in the presentation about what the coating itself does, not only is from a friction point of view, but from a lubrication point of view. How well does that part hold oil? Next one to the upper right is electrofusion or hard chrome. That's a plated chrome, just like a bumper on a 57 Chevy or Cadillac, or had your wheels done in chrome. That's your electroplated chrome. Those types of coatings, fairly lumpy, fairly bumpy, kind of old school. They do work. They work fairly well. There's fairly good anti-rust characteristics, anti-friction characteristics, but it's not the easiest seating, quickest seating. It's hard to get it really uniform and really nice and flat. It doesn't want to mirror the substrate of the ring extremely well. Now you go to the lower row of coatings, and now you're into the PVD type coatings. And lower left is tungsten carbide carbon. One of the things Lake had touched on earlier was how long, you've got to kind of look at the duty cycle of the engine. How long is it going to run? The WCC coating is an extremely low coefficient of friction coating. It's a 0.1. So it's a very, very low friction coating, but it's in the big scale of things a little on the softer side. So if that's a coating or an application that I want to get 10,000 race miles out of, probably not going to be the right coating. Probably going to wear, but it's going to seep very, very quickly. So you always have to kind of look at the coating and what the application is going to be. Next one's chromium nitride. Very, very common coating today, very popular. About the middle of the scale as far as hardness goes on PVD type coatings, about 1,700 Vickers. Little higher coefficient of friction. I think off the top of my head, it's about a 0.4. Wears very well. Common coating to see put on stainless, on valve stems, on valve guides. not guides, but valve stems. And then you work your way up the scale into the titanium. Titanium nitride, about 2400. Harder coating, gonna last longer. Similar coefficient of friction to the chrome nitride, but ultimately it's gonna take a little bit longer to seat up. It is a harder coating, but wears better. And again, into the diamond-like carbon on the higher end of the scale. That coating can be in excess of 3,000. Again, not all DLCs are the same. And as Lake said earlier, you know, some are really good, some are really bad. Adhesion can be an issue with DLC. You don't want that coming off inside the engine. There's a billion little tiny razor blades, diamond-like, flying around inside your engine. So you got to be careful with DLCs. You know, a great DLC or a good DLC is a nice coating. It wears well. Again, low friction characteristics, but it can come off. And if it does, you don't want that flying around inside your engine. Next, we're going to talk about the actual cylinder itself, the hardness of the block. So we've talked about the ring. Ring materials are harder. We're into harder coatings than we used to be before, much harder coatings than we used to be before. But then you've got the cylinder itself, the actual cylinder wall that we're working with. And again, typical traditional old small block Chevy, small block Fords, Mopars, your typical gray iron cylinder, as you can see in the upper left picture, hardness scale. And again, we're jumping from, you know, coatings, we're looking at Vickers, now we're into Brunel. Cast iron, you're typically in the 150, 180 range on a cast iron block. And you can also look at the grain structure in the material, how it looks like little grains of rice. There's lots of little pockets, lots of little places and little pores to hold oil and retain oil. And all of this is about oil retention. Everything we're doing here and talking about is keeping that oil interface between, you know, the cylinder wall and the ring itself. You know, rings ride on that film of oil, and it's very important that we retain that. We start getting into the newer blocks, the dart blocks, bow tie blocks, your world blocks, and we start moving into numbers into the low 200s, 200, 250. We're dealing with a fairly big jump in hardness of the cylinder. So it does become a little harder to hone, a little harder to machine. But if you'll also notice, the grain structure is changing. It's changing significantly. We're going from that, more rice-like, more grain-like style structure into a more pearled or rounded structure, less pockets, less pores. We've all looked at gray iron. For those that are into iron, cooking utensils, pans, you oil that pan, you season that pan, you're getting that oil, that iron to actually hold oil on its surface, to create that cooking surface. And that's because that material is relatively soft and it's porous. As we go up in hardness, the cylinder doesn't want to hold that oil anymore. It gets to a point where it actually wants to start to reject that oil. Then we start getting into the even more modern type stuff, the hybrid, the hardened ductiles, compacted graphites, the later model Darton sleeves, LA sleeves. Some of the Dart blocks, we're pushing numbers in excess of 300 today. Much, much denser material, much more difficult to hone, doesn't want to hold oil as well. And then you get into more exotics, which we'll talk about later in the program. Coated bores. There's steel cylinders out there today. I've seen cylinders in excess of 550 Brunel today. People building cylinders out of, we talked about chromoly, building cylinders out of chromoly, trying to get that stiffer cylinder, which makes it just that much more difficult to hone. But it can be done with the right tools. And all of this comes down to the need to measure surface roughness. As you can see, as we talked about before, we're dealing with a much wider range of hardness in cylinders. You jump back again to say the 1970s, you're dealing with blocks that are all traditionally about the same hardness. We're dealing with relatively thick rings, big 5/64 rings with 20-pound oil rings. You can get away with a lot of things when you're dealing with relatively soft blocks and relatively hard, relatively soft rings, soft blocks, high tensions, excuse me. You can get away with a lot of things. The rings will correct an incorrect cylinder finish kind of on their own. Rings naturally plateau cylinders. But in today's world, where we're dealing with very light tension rings, hard coatings, and hard blocks, we're not going to get that wear that we would get essentially or initially with the softer blocks and the bigger rings. So it's a matter of having the tools available so we can actually measure those surface finishes. And again, as mentioned earlier, Billy had a real nice point. One of the most common numbers to use is RA, arithmetic average of roughness. The problem with RA is it's a big blend of numbers. And you can have what would have traditionally been looked at as a great RA and still have a horrible cylinder finish. And here's kind of an example of that. This is not as technical as what Billy put out there. And again, I keep mentioning my other speakers, but I don't want to some of what they presented was, or all of what they presented is really good, and covered a lot of what I'm talking about here. But here's some visual examples of two different surface finishes that both measure the same RA, but have two completely and totally functionally different characteristics. The upper surface, as you can see, has a beautiful plateau right across the top. My little pointer right here. Great low profile surface. And the surface down at the bottom, which is completely inverted, has nothing but peaks, no valleys. And using RA, they're measuring the same. Using just a simple pocket surf or something like that will only measure RA. You could have a great surface finish number, but have an effectively horrible surface finish. So that's why we don't use RA. And again, this is kind of a reflection of the same surface finish we just looked at. The above up here, if you can see the pointer, we've got no plateau, got lots of peaks. This is our RK, this is our core value, this is our valley, but we don't have what we've got down here, a nice plateau, that nice flattened out surface finish. And that's what's essential to getting good, quick ring seal today with thin rings, hard coatings, and hard blocks. As I said earlier, rings naturally plateau bores. They do that through the running in process. So back when you had soft blocks, soft rings, lots of tension, you could have a surface finish that didn't really have a lot of plateau. And through the running in process, those guys that have been around a while, like myself and some of the other people out there, I'm sure, remember the old days. It might take you 2,000 miles, 3,000 miles to wear to get a set of rings to completely seat up. And people would say, well, that's the ring. Well, sometimes it's ring, but generally it was a cylinder finish issue. The cylinder simply didn't have a good plateau. And it takes time for that ring to wear that plateau in. And it will do that naturally through the running process. And again, with soft blocks, softer rings, big rings, lots of tension, it's going to do it relatively quickly, but not so much with today's stuff. That's why it's so very, very important to have access to one of these, the profilometer, so you can actually measure that finish and make sure you're getting that plateau. This is the same slide that Lake showed earlier, and why I'm touching on this is rings ride on that film of oil. And it's so important to get that proper amount of oil retention on the board, especially in high cylinder pressure applications, applications that are have a lot of fuel going through there, trying to break the oil film down, getting into a lot of oil dilution, everything that's trying to kill that oil film. High vacuum situations, not uncommon today to see engines that run 20, 22 inches of vacuum in the crankcase. All that vacuum is doing is trying to pull all that lubrication off the cylinder wall away from the ring. During that ring reversal time, top and bottom dead center, when, as Lake indicated, the piston stops, everything slows down like that ski on water. It's coming off plane and sinking through the oil, through that lubricating area. We've got to have that oil retention and keep that oil film to keep that ring lubricated, the piston lubricated. If we don't get that, we're going to get into that heavily loaded area. We're actually going to get that metal to metal contact. And we're going to see that wear. We're going to see premature ring scuffing, cylinders that aren't happy, pistons that aren't happy, and it's because we're losing that lubrication. About 90% of the failures that I see customers sending me rings almost always come down to some sort of a lack of lubrication to the part. The ring itself is really a pretty simple piece. If I make it round, I make it flat, I make it light tight, I make it the best I can possibly make it, I really can't do more with that part. So if I put the part into an environment where I've got an excessive amount of fuel, I don't have that lubrication of the part, that oil film that creates that gasket, that sealing surface between the ring and the cylinder wall, we're going to have that failure. And I get the part in and I look at it, it's simply a lack of lubrication of the part. There's a lot of things that can do that to the ring, but that getting that cylinder finish right for that application is so important. It's the first step to eliminating that issue. This slide talks about pressure, and this is where we're talking about plateau honing. So if you can kind of follow the cursor, no plateau at all. So we're going to say that ring's producing 500 pounds per square inch of force against that cylinder wall. So with no plateau, I've got 100% contact. I've got 500 pounds per square inch of force pushing against the wall. No ability to lubricate, no ability to keep that ring suspended up off the cylinder. It's going to have full contact, and we're going to have a disaster area in a heartbeat, just like a bearing on a crankshaft with no oil. It's not going to last very long. As we come over to this slide shows almost no plateau, about 10% plateau. So now, instead of having that pressure spread out across that area, I'm sitting just on the peaks. I'm sitting on those points, on those tips. And during initial fire up, during that initial startup, with that much pressure against the ring on that cylinder wall, we're going to get it's just kind of like a razor blade against it. We're going to get into a lot of scuffing. So we're not only going to wear the ring, we're going to wear the bore, and we're going to create a lot of debris that's going to get into the ring groove, into the skirt of the piston, into the oil pan. We've all had those engines we've taken apart, and you see that layer of stuff down in the bottom of the pan, and you kind of grab it up and it's a little bit sparkly. That's your cylinder wall. More than likely you had a cylinder that was home too rough. It didn't have a lot of plateau, and through the running in process, again, the ring's naturally going to plateau that bore over time. We've ended up with all that material down in the pan. Well, that's prematurely worn block, prematurely worn ring, a lot of scuffing on the part, and almost always going to cause a delay or accelerate the wear process in the engine. As we come over to this slide, you've got about 40% plateau, and that's reduced the pressure on the ring from 5,000 pounds per square inch down to about 1,250 pounds per square inch. Again, less wear on the ring, less wear on the bore. We're ultimately going to achieve that plateau on the cylinder quicker, and we're going to have that ring seal that comes in faster. If you're on the dyno and you've got one of those engines that, it's like, hey, I get guys all the time on the phone, hey, we're 10 pulls in, we're 13 pulls in, man, she's really starting to come in. The power numbers are starting to come up, the blow-by starting to drop. That tells me right off the bat that we didn't have a good plateau on the cylinder finish, because the ring, again, we're back to it's doing the plateauing, it's doing the wearing, it's bringing that surface down, and every pull we put on it, it's doing that job more and more and more, and we're flattening that out. We're flattening the curve. We're flattening that and creating that plateau. And the power numbers are coming up, the oil consumption's going down, blow-by numbers are coming down. It's because we're creating that plateau. But the ring's doing the job. If we've got a really well plateaued cylinder, it's going to come in almost immediately. You're going to have that engine on the dyno. It's going to go 1, 2, maybe 3 hits. You're going to have that great ring seal, fantastic blow-by numbers, dry as a bone. That tells you right there you've got a really, really good cylinder finish. If you've got to keep beating on the thing an excessive amount, that's almost always an indication that there's something wrong with the cylinder finish. Generally speaking, way too rough. Doesn't have a plateau, even though you think it does, or you were told it does. So to the right slide here, we're looking at about what we're looking for in a properly plateaued cylinder. We want about 80% plateau. So about 80% of the surface flattened out. You look at the pressure numbers, we're down to about 625 pounds per square inch. Very few peaks, a lot of plateau, nice valleys. Kind of going back to the numbers we talked about earlier, RA. There's numbers that can be used. They're RA, RZ, which is your peak to valley height spread over 5 segment lengths. Then there's also a thing called the Abbott-Firestone curve, which is commonly seen on older profilometers. New ones will do it too, but the new ones will measure other numbers that we'll talk about in a second. But if you look at your Firestone curve, what are known as your MR1s and your MR2s, you can look at those ratios. And when you're seeing your MR2 numbers sitting up and around that high 70s, low 80s, that's representing your surface finish, how much plateau it does or doesn't have, how much material is above the curve, how much material is below the curve. So if you don't have a profilometer that will measure the newer types of numbers, you can work with the older numbers as long as you can measure the MR1 and the MR2. So what we're looking for today and what we're measuring today are referred to as the following: RPK, RK, and RVK. And RPK is, as it says, reduced peak height measures the portion of the surface's protruding peaks that will wear during initial loading. What that means, in essence, is that's the surface that the ring is going to touch when the engine's first fired up. When you first build that engine, that's the peak that's sticking through the film of oil. That's the part that's actually going to come into contact. So if we get a high RPK number, we're going to have a lot of wear metals that are going to occur. We're going to have scuffing in the ring. We're going to wear the cylinder bore. We're going to get that material into the ring groove. That can create micro welding. We don't want to see a really, really high RPK number. At the same time, we don't want a really low number either. We need there to be, again, kind of like cooking or any kind of a recipe, just the right amount. We want enough roughness on there to get the ring to bed in. Again, that break-in process is really the final machining process. That's the last step in getting that engine, the cylinder finish just right. We can only do so much with the hone. We can get it as perfect as we can, but there's still a little more to go. We've got to have that little bit of wear, that little bit of roughness, that little bit of friction when we first fire the engine up to get those surfaces perfectly made up, just like a flat tappet cam to a lifter or a brake pad to a brake rotor. Got to have that little bit of friction right there to get the surface to perfectly made up. The next number is the RK. That's the core value. Core roughness depth is used to describe the portion of the area that will support the load. And what that is, that's the bearing area. Why we don't use RA is it doesn't refer to the ability to bear a load. It has no reference on load bearing. Using these numbers, we can look at the peak roughness, the core roughness, and that valley roughness. And now we can describe the ability of that surface to support and bear a load. And we talked about the ring and that oil film. Well, you've got thousands of pounds of pressure that are trying to push that ring through that oil film and push that ring into the cylinder wall. If we've got the right amount of oil storage, the right amount of roughness, the right amount of bearing area for the application, that's not going to happen. The ring's going to stay on that film, and it's going to stay on top of that film, and we're not going to get that scuffing, that premature wear, and we're going to have excellent ring seal. The next value is RVK, and that's the valley depth. Valleys protruding through the roughness core value is the oil retaining portion or the troughs machined into the cylinder surface. That's your valley depth. What that speaks to, and I like to refer to it as a rung on a ladder. Just because we're throwing oil into the cylinder, we can have oil jets, we can have all kinds of volume. Just because we're throwing that oil up into the bore doesn't mean the oil is going to stay there. It's the ring's job to take that oil, scrape that oil back down into the sump, and create, again, just that right amount of oil on the bore to keep that part supported and not have metal-to-metal contact. If we don't get that depth, that RVK, the oil is not going to have anything to cling and hold onto and get a grip on. And the RVK is probably the number I see missed the most in cylinder honing. We go too far, we plateau too much, we lose that valley, and that's the most common number that I see that gets messed up. If we don't have that ability to retain oil, like I say, it's kind of like that rung on the ladder. Anybody ever played that game Crazy Climber? We're trying to climb up the side of the building. Well, it's hard to get a grip on there when the window's closed. And if we don't have that depth, it doesn't give that oil that ability to grab a hold of the bore and cling to the bore, stay on the bore. It ends up back in the oil pan, which is a good place for it, but we got to have the right amount of it on the cylinder wall to keep the rings lubricated. To look at all these numbers and measure all these numbers, we're going to have a profilometer. I use a Mitutoyo SJ210. It's a very popular piece of equipment. Measures a lot of parameters. The machines will do more parameters than you could probably ever use, but it will measure all the numbers that we needed to use. So that's a great machine. Whether you use a Mitutoyo or you don't use a Mitutoyo, that's neither here nor there, but you really want to have a machine at your disposal or access that will measure RPK, RK, RVK. RA is nice to have for non-moving surfaces like gasket surface, deck surfaces on cylinder heads, making sure that you've got that head gasket sealed up nice. But the RPK, RK, RVK are really the numbers that we've got to look at when we get into cylinder honing. And these are some target numbers that we want to look at when we're doing that honing. Real thin rings, 0.8 millimeter stuff, 0.6, 0.5s. We're looking for a target number of about a 10 on our peak roughness. RK numbers, we're looking at for about a target of a 25. My RVK, about a 35. But there's always a window. It's always you can have a little bit higher, a little bit lower. We want to kind of watch we have target numbers. General purpose stuff, and this is 99% of what's out there. Circle track, drag race, bracket race, street cars, daily drivers. RPK number, we're looking for a target of about a 15. My core value about a 40. And my valley depth about a 50. We get into high cylinder pressure applications, big boost, big nitrous, big turbo. Same thing. Peak value stays about the same. I want to see about a 15. Again, that's that roughness that the ring's going to touch when it first fires up. 10 to 15 kind of seems to be a real sweet spot. Brings the rings in nice, seats up really quick, but it's not hard on stuff. Doesn't create a lot of debris, a lot of junk. I want to bring that RK value up. That's my bearing area. I want to bring that up because it's going to support more load. And I want to bring the valley area. That's that oil retention. That's ability for that oil to cling to the bore. Now, these are good general numbers, but there are times where you're going to need higher than this. I have a very good customer of mine, builds real big diesel stuff, 4,300, 4,500 horsepower, big diesel, big pulling diesels. They're pouring so much fuel through this engine. He has spent thousands and thousands of dollars on different cylinders, as far as the materials, different types of hone, different ring coatings, and everything we see, we're always seeing this lack of lubrication, no matter what we do, material-wise, coating-wise. So, we talked about it quite a bit. I know Lake was involved with speaking with him, and we just started bringing that RVK and the RK numbers up. He literally got the RK values a little over 100, and the RVK numbers up into the 140s. Very, very high numbers, but a lot of oil retention, a lot of oil trapping. These guys pour everything through this thing, including the kitchen sink. I mean, it's diesel, alcohol, water. You're pouring all this fuel through this engine to the point that rust has become a problem in it. But getting those numbers up that high is what it took to keep the oil on the cylinder wall with that much fuel going through it. And guess what? All his ring seal problems went away. All the wear went away. Problem solved. It was simply cylinder finish. He's putting so much fuel through the engine, it's washing the oil film off the bore. So these are good general purpose numbers and all around good targets depending on your application, but they're not the be all end all. So I always say, hey, reach out to us, get a hold of myself, get a hold of any of the guys here, discuss your application with us, and we'll help point you the right direction. The one thing that there really isn't out there is a flow chart. There's Rottler equipment, Sun equipment, Winona, Surdy, AN style heads, diamond style heads. There's so many different types of materials and abrasives out there. The days where I could just give you a flow chart and say, do this, do this, do this, and you're going to get that finished. Those days are kind of long gone. I do have information on the website. It's good general information to help point you that direction. But that one-on-one interaction where we can actually talk about what you're using, what kind of equipment, what's the application, we can help guide you down that pathway a little bit better. I really wish, like I said, that somebody could produce just a piece of paper to give you to say, hey, do this, and that's what you're going to get. But anybody that tells you that's a flat outlier because there's just too many variables. One of them being this. This is a surface finish generated by a vitrified stone. Most common stone out there, been around forever. You can see very nice, clean cuts, not a lot of debris, not a lot of junk. You can see fairly defined finishes, fairly defined surfaces there. That's a 280 grit vitrified stone. But here's the next stone as a comparison. And this is why, again, it's really difficult to put a chart together that says, use this stone with this pressure on this, and you're going to achieve that, because we've got all the variables of block hardnesses, stone, coolant versus water, oil. All of these things make a difference when it comes to that surface finish. That's a similar grit diamond. As you can see, two completely different surface finishes. You've got the cuts, but you see the little dark spots. That's a lot of burnished material. Didn't cut really well, kind of rolled the material over versus cutting the material. And one of the things you have to be careful about when you're honing is you can falsely get good numbers when you're honing if it rolls that peak over. It didn't cut the peak off, it rolled the peak over. And you can actually get a good surface finish number and actually have a bad finish if it rolled that peak over, if you burnish that cylinder. But that's something you can pretty much see, and I'll have an illustration of that here in just a moment. And this is kind of the next thing that's, I'll call it, coming up in the surface finish or in the honing world. is CBN, cubic boron nitride. We've been using it for years, and in all kinds of cutters, or cylinder deck surfaces, valves, valve seats, and it's kind of working its way into the honing world now. What we're finding is it cuts very, very well. It cuts like a vitrified, leaves a very clean, very nice surface. You can see the nice lines, consistent crosshatch it produces. Not a lot of tore up junk, not a lot of burnished area, but it lasts like a diamond. So in today's modern machines, when you plug in a number and tell you want to take 5 thousandths out of the cylinder, and that's kind of why super abrasives work the way they do, is they don't break down a lot. Vitrified stones break down fairly quick and keep really clean, sharp abrasive. But it's hard to put that in one of today's computerized machines and tell it to take 5 thousandths out of the cylinder wall. It doesn't know if 5 thou came off the stone or 5 thou came off the block. It just knows it changed size. So with today's super abrasives, you really don't want the stone to break down much. And that can create an issue. That can load up stones and again create burnished cylinder walls. You get that dark look. And so the look of the cylinder really comes into play. And again, we'll show that here in just a moment. But super abrasives are changing, and you're getting where they break down a little bit more, and the bonding agents are a little bit different. And CBN is kind of one of the newest ones that's coming out. And I really like the CBN. Diamonds work well, vitrifieds work well, but I'm really kind of a fan of the CBN. So if you're looking at stones, talk to your supplier about CBN. I'm really seeing some remarkable surface finishes produced by CBN. That's one of the things you should see when you're done honing a cylinder. Now in this particular case, that's actually a Nicosil cylinder. But what you see is a very bright, very sparkly, very shiny cylinder. Cylinders should always have that nice, bright, shiny, sparkly look to it. It shouldn't be dark. It shouldn't be dull. It shouldn't be gray. That dark gray, nasty, you get that real black looking cylinder. That's a burnished cylinder. When you're done honing a cylinder, it should always go out, look bright, shiny, sparkly, brilliant. It should always reflect the light back. You should have that look of the rainbow colors like a diamond would. And that's a really good cylinder finish. So use the tools that you've been equipped with, your eyes, and look at that cylinder finish. If it looks dark, it looks dull, it's got that blackish look to it, it's most likely burnished. It's rolled the metal over. And even though you have a profilometer, and even though you can measure those surface finishes, you can falsely get a low RPK number because it rolled the metal over. But it won't fool on the look. The look is always important. You should always have that bright, shiny, sparkly cylinder. One of the most common things I see in honing today, and where guys get the numbers messed up, I'm actually gonna back up a little bit here and go back to those numbers. The most common thing I see today is RVK values are too low. They'll get the RVK and the RK flip-flop. They'll get them backwards. And generally what does that is too many steps in the honing process. In most cases, you're gonna have a roughing step. You're gonna get it really, really close to size. You're gonna have a sizing step, and they'll refer to as a finishing step. I'll get guys that'll bring it to size, leave it within 5 thousandths, say using a 220 grit stone. Then they'll come back in, use a 280 to get it within 2/10 of size. Then they'll come back in, use a 400 to get it to size. Then they'll come back in, use a set of brushes and stroke it, 10, 15, 20 strokes. Well, these numbers that we're looking at here, these 30s, 40s, 45s, we're talking micro inches. These are very, very small cuts. And it's very easy to lose that valley number very, very quickly when we start introducing a lot of steps into the honing process. Honing should be pretty straightforward. What I want to call less is more. A roughing step, a sizing step, and a finishing step. And on the finishing step, it's almost always better to leave it a bit rougher. On these numbers, let's just say for my general purpose number, I'm looking to get an RVK of a 45 to a 55. Well, when I start plateauing, what I like to do when I'm using my profilometer is I'll stop before I start plateauing, whatever that function be for you, whether that be with a fine grit abrasive, a ball hone, one of my favorites, or brushes. There's a lot of different ways to get there. It's like, we'll say getting to your house, probably 5 different ways to get there, but the end result is that you got there, you got the numbers. If we start off with that RVK number too low to begin with, it's only gonna go lower. So if I'm trying to get a target of say a 50, that window of 45 to 55, before I start my plateauing process, I better be in the 60s or 70s. It's almost always better to have that number be higher than lower because it's only gonna go lower when you're plateauing. So If you've got that profilometer, stop at that step before you start plateauing and take that look at that RVK number. At that point, that's really the only number I'm really concerned with is the RVK. If I want to be a 50 at the end, when I'm plateauing, I better be starting off around a 70 because that number's only coming down. Now we can come in and start plateauing with whatever tool we're going to use, a fine grit abrasive, a ball hone, brushes, and we can start going at it slowly. Come in, lighten the pressure up, 4 or 5 strokes, check it. We're not there yet on the peak and the core value, a couple more strokes, check it. Work your way along the line, but keep checking it. Don't wait till you're finished to check the numbers. You may have gone too far, and it's almost always a matter of losing that valley number. So important to keep that RVK number up, to keep that oil retention, to keep that oil trapping, the bearing area, the RK, the RVK, the oil retention area. Those numbers, I see it get flip-flopped so many times. We get into premature wear, bad ring seal, too much blow-by, oil control issues, all the bad things. Keeping those numbers up high, assure that proper ring seal. So just wanted to kind of touch on that. Many steps in the honing process is almost always a key to disaster. This is kind of a less is more. Rough it, bring it to size, hit it with a plateauing tool, whichever that one is of your choice, and then hit those numbers, checking them along the way as we go. This is Nicosil, and Nicosil has become very common today. Again, we've been talking about iron cylinders, but in today's world, there's a lot of exotic materials coming out. Nicosils are very popular, especially in motorcycle applications. Nicosil is a nickel silicon carbide, so as Lake said earlier, you don't want to put basically chrome on chrome. It likes most PVD coatings, chrome nitride, titanium nitride, work very well on it, but you don't want to put any kind of hard chromes against it. They're very similar materials, and alike materials generally don't work together, and you can get into adhesion problems. They'll try to pull the Nicosil right off the board, and that's always bad. One of the things about Nicosil, and it's kind of easy to tell, and this is another little trick for any kind of surface, when you look at Nicosil, you should see that really nice pronounced crosshatch, but kind of an easy test is what I want to call the fingernail test. If you don't have a profilometer, run your fingernails up and down that cylinder. You should see a nice pronounced crosshatch, very visible, very there, but it should feel glass smooth. You should almost not feel, you should see the crosshatch, but you'd almost not feel the crosshatch. That's proper Nicosil. If that cylinder feels rough to you, it is rough. And Nicosil being, again, what it is, a real rough Nicosil bore is most likely going to tear the rings up when it starts because it's so sharp, it's so hard. The rings, like we talked about earlier, will naturally plateau it down, but by the time it does that, it's going to destroy the rings. It'll literally chew them right out of the engine. So Nicosil should be very smooth, like glass, though you should see the crosshatch pattern. And the same thing kind of applies to an iron bore. You should see that beautiful crosshatch pattern, nice and uniform. When you run your fingernails up and down it, again, not a profilometer, not a true test, but that simple kind of a feel. You should feel the crosshatch, but it should not feel like a fingernail file. If it feels rough to you, it is rough to you. And if it feels rough to you, it's going to feel rough to the rings, and it's going to tear the rings up when you first fire that engine up. And that junk that's going to come off of there, it's going to get in the ring grooves, it's going to get in the skirts, it's going to get into the pan, and it's going to create wear problems. It can create micro-oiling problems between the ring and the ring groove. I have a customer that's been fighting an issue. When he hones with a vitrified stone, he doesn't have a problem. But he switched to diamonds, and he's still kind of learning the diamonds. And it's come down to he's leaving a lot of junk. He's leaving the cylinders a little too rough with his diamonds. So when he breaks the engines in, he's getting that junk, he's getting that grit, that abrasive into the ring groove, and he's having a micro-welding problem. And it's not the fault of the diamond, it's not the fault of the ring or the piston, it's just his surface finish. He's worked on it now, he's got those numbers down, that problem's gone, but he was just leaving so much junk on the board, that rough metal, which it shouldn't be. Another one of the things that's out today and very common is the arc plasma sprayed bore. These are becoming very popular. Ford's using it, Nissan's using it, Toyota's using it, Mercedes is using it. It's become a very popular material out there, and more engines are coming out with it all the time. When you get it apart, the cylinder is going to have a very dark charcoal look, very black look. These are really neat coatings because, like molybdenum, it's very oleophilic. It holds oil like a sponge. The problem with moly on a ring, and especially in today's engines, Molybdenum doesn't really stick well to the ring. It likes to come off, and that's why moly is not used a lot in real thin ring stuff, or engines that have real high cylinder pressure. Detonation can be an issue. Things like that will knock the mollies out of the ring, and that's why the hard coatings, the PVDs, have become more common. They have better adhesion, they stick well, they follow the substrate surface of the ring better. They just kind of do a better job than moly. But moly does hold oil like a sponge. So that makes it, you can get away with kind of missing the cylinder finish a little bit with a moly filled ring. You don't have the RVK, the RK, you can kind of get away with a little bit. The moly holding an oil, cylinder's not perfect, but I've got this backup over here. It holds oil. We might be able to get away with it. With today's coating, the PVDs, and again, the importance of getting that cylinder finish right is they don't have the ability to hold oil very well. Most PVD coatings are only about 4% porosity. So we have to be sure that the cylinder wall does the oil retention. It has to do all the work. I can't count on the ring to do that. But we've come out with that same style of coating, but instead of it being on the ring, it's now on the bore. It's the plasma sprayed bores. Many of them have a moly base to them. Some use titanium, some have tool steel in them. But the one thing they have in common is they're very oleophilic. They hold oil like a sponge. These are going to hone glass smooth, literally mirror finish, almost no visible crosshatch whatsoever. This takes very, very special tools, typically 1,000 grit, 1,200 grit diamonds to try to achieve these types of cylinder finishes. So I'll say this about those types of coatings. If you're not equipped with that kind of equipment, or you're just not sure, you're better off to leave it alone. It's very easy to remove these coatings if you're not familiar with how to hone and how to process them. I was in Australia a couple years ago, had a gentleman holding a Mercedes blocks, and he comes to me. It was really, I didn't come there to talk about honing, it was about some other things, visiting their shop, talking about piston rings, of course. And a gentleman came up from the back and said, "Hey, while you're here, take a look at this. I got all this black stuff coming up out of the cylinder." So we go in the back. He's got a 280 grit stone in a Mercedes block, 6.3 liter V8, and he's literally honing the plasma coating right out of the bore. He had no idea that he was doing that. And about a $10,000 block later, problem was fixed. So be aware of that coating. It's become fairly common today. A lot of it out there. And generally speaking, if you're not familiar with honing it, leave it alone. It's one of those coatings that doesn't really need a lot of help. Unfortunately, I had these slides out of order and just realized it. That's a surface finish of a freshly coated and honed Nikasil cylinder. As you can see down here, RPK is about a 6.9, RVK is 17, RK is 17. Now, we were looking at the numbers earlier for iron cylinders. Well, again, we're back to Nikasil being very oleophilic. It holds oil like a sponge. We can get away with an extremely smooth bore finish on Nikasil's Sumi bore, which is the picture you just saw before. That's the Sumi bore coating. Also done under the Flame Spray Technologies brand. There's quite a few different brand names, but all similar styles of coating. But Nikasil, we're looking down here at an RA of about a 6. Nikasil cylinders, you typically want to see them somewhere in an RA number, using that number, between a 4 and 8. Very, very smooth, not quite mirror smooth. Glass is usually around a 2, which is, again, we'll pop back about where you want to see these types of coatings, mirror smooth, no crosshatch. To where Nikasil about a 4 and 8. These are becoming much, much more common coatings today than they were 10, 15, 20 years ago, though they've been around for quite some time. And this is Alucil. This is a hypereutectic aluminum. It's a silicon impregnated aluminum. It's been around for a long time. People will remember it. The old Chevrolet Vegas were Alucil. This is not a coating. It's not a liner. It's what the cylinder is actually made out of. It's a silicon impregnated aluminum. There's a very specific process for Alucil. You can bore it, you can hone it, but you're going to, again, hone it glass smooth, mirror finish, no crosshatch whatsoever. There's a rouging process for Alucil. Sonnen offers it, Rottler offers it, quite a few different people offer it, but you're actually going to polish it to where it's glass smooth, no crosshatch whatsoever. Alucil is very common again today. BMW's using it, Porsche's using it, Audi's using it, Mercedes using it. It's coming back into favor because no liner required. Keeps the block very light. Weight's a big issue with the OEs today. This is not real common to see in race application stuff, but it has become more common and is coming back. So, you know, the day of the iron cylinder is always there, but keep an eye out for some of these exotics because they are completely different beasts and you want to be careful when you're using them. Again, call us, ask us. Glad to answer any questions we can for you. Last couple things I'll touch on, and I'll let you guys get going. I know we're going way over here. Crosshatch angles. You hear the word 45-degree crosshatch angle, and that's what's referred to as the included angle. Again, I'm pointing at the screen. I should be using my pointer here. When you hear 45-degree, that's the included angle, the measurement between the up and the down. A 45-degree crosshatch angle measured off the deck is about 22.5 degrees off the deck. Let's see if I can, you can easily measure this. Let me see if I can find one of these here with a plastic protractor. I actually sell, or I should say sell, I give away, it's not for sale, I'll gladly give them to you, this little angle checker. It's got a clear backing. Get this out of here. I don't know if you can see that or not. 0 lines the deck. That's the crosshatch angle. So if we're looking at this line right here and that, you know, you put that on there and that lines up, matches, that's 20 degree. Well, that's a 40-degree crosshatch angle. And glad to supply this to any of you out there. Just a matter, either call us, drop us an email, gladly send you a crosshatch angle checker. You can pick up a similar thing at Hobby Lobby for about $1.86, but just a nice little plastic protractor that you can double check your crosshatch angles. And the reason we do this is because crosshatch angle helps to determine ring rotation speeds. If we get a real vertical angle, a real steep angle, it's going to try to make the ring rotate fast. And this can cause a ring to line up. Very quickly rotating ring can cause the end gaps to line up. Fairly common issue if you've got an engine that's always trying to line the end gaps up. More than likely, it's a crosshatch angle problem. Too up and down, too vertical. Flatter the crosshatch angle, the slower the ring rotation speeds. And this illustrates that. You can do a real flat crosshatch angle, and this one's not that flat. This is 28 degrees included or 14 off the deck. As we flatten the crosshatch angle out, you start to slow ring rotation speeds. But it also acts kind of like a dam. Flatter the crosshatch angle, typically the lower the blow-by numbers. More vertical the crosshatch angle, typically the higher the blow-by numbers. An easier pathway, an easier travel path up and down the bore. But the same can be said for oil. There's engines out there that have very long cylinders, very tall compared to the stroke. A more vertical crosshatch angle helps to get oil propagation up to the top of the cylinder. Perfect example is a Harley Davidson. A lot of Harleys from the factory run a 60-degree crosshatch angle. More vertical angle helps promote oil migration up to the top where they're not getting enough oil simply because of the length of the cylinder. Some of your flat engines, Subarus, Porsches, some of those will run a more vertical crosshatch angle, but not because they're trying to get the oil up to the top of the cylinder. They're trying to get the oil back into the sump, making it an easier pathway for the oil to move. As we flatten the crosshatch angle out, the oil wants to move side to side, not up and down. So as we flatten that angle, we can get, if we get too flat, into oil migration, and we can get a chattering or stuttering effect as the ring is going over that. It starts to kind of lump up like driving over a railroad track. So too flat of a crosshatch angle can create a problem. Too vertical can create a problem. Typically, most crosshatch angles in a high RPM, short stroke engine, you're going to see them somewhere between 30 and 36 degree included. Most of your general applications, you're going to be probably in the 40 to 45 degree included. And there are some applications out there that are going to be in the 60 degree range. Some of your Harleys are like that. Subarus, a lot of your Subarus, just about every factory Subaru cylinder I've ever measured is sitting at about a 60 degree crosshatch angle. That's not to say that they can't use something flatter, but based off what they're doing, they're about 60 degrees right out of the box. So again, handy little tool to double check your crosshatch angles. Again, there's the illustration of a 60, 30 degrees off the deck, 60 degree included angle. And with that, I want to say thank you for attending. Again, guys, I really appreciate this. I know we covered a lot of stuff very quickly. Hard to go into depth on every subject here. So please feel free to reach out to myself, Blake, any of the guys here at Total Seal. Glad to answer any questions you have. Send you crosshatch angle checkers. we're here for you. We love the calls. We love talking to you guys. We love discussing gals. I don't mean to just say guys. We love talking to you because we want to help you. We want to know about your application. We want to know what it is you're doing and help guide you down the path to what is the right ring, what's the right cylinder finish, and how do we get it using your equipment? What do you have? You got a Rottler, you got a hand hone, you got a Sonnen. We can help guide you down that path. And again, thank you so much, everybody. I really appreciate you guys taking the time to watch this and attend today.
Super, thanks, Keith. I mean, excellent presentation. You're covering stuff that all the shops, I mean, we address this stuff on the tech line at AERA as well. And yeah, no problem going over. This is excellent information, very informative. And I do have some questions for you if you want.
Please, I look forward to it. Like Billy said, my favorite part.
Okay. So here's the first question for you. Are there any significant differences between an iron block cylinder and an iron liner in an aluminum block?
Well, if it's like for like material, if we're dealing with the same liner materials we are the block, no, they're gonna basically hone the same. The amount of oil retention of the material itself is going to be the same, but the aluminum, that's the next thing. How we're moving heat out of it. Iron block, iron sleeve into an aluminum block. The whole point is to get the heat, through the piston into the ring, ring to the wall, wall to the water, water to the radiator, and get the heat out. So there can be some difference in thermal transfer. Thermal conductance can be different depending on wall thickness. You are creating multiple layers of material that do move the heat differently. But as far as the actual surface of the material, as long, a 220 Burnell cylinder made out of the same material, whether it be the block or the liner, it's basically going to hone the same and produce the same type of surface. It's more about, again, how it's going to move, how it's going to distort because it's in an aluminum block, and thermal transfer. Those are going to be the differences.
All right, sounds good. Now here's an excellent question. So when using a profilometer, do you have to clean the cylinders from honing oil first when using the profilometer?
Yes, you do. And great questions, all of them, by the way. The stylus portion, and hang on just one second, because I just happen to have one sitting on the floor here. A gentleman bought used and wanted to get it set up and calibrated and working. This is the we'll say the work end of the profilometer. That little stylus, that little needle right there. And Billy again had earlier talked about skidding style and non-skidding style profilometers. This is a skidding. This little part of the housing right here is actually going to drag on the bore, and the little needle, the little stylus, is actually what's going to go down into the surface and give us that reading. These are, keeping in mind, relatively inexpensive in today's world. A Mitutoyo SJ210 is about $2,000. Again, there are profilometers out there that run in the hundreds of thousands of dollars. We have two of them here. Taylor Hobson, they're non-skidding style profilometers. We measure the face surfaces and the face trace profiles of all the real high-end rings, and used during production, and prototyping. They're non-skidding style, where this never touches the bore. The only thing that touches the tip. But to answer the question is, yes, it needs to be clean. We don't want any oils. We don't want any material in there, any debris. The debris or the dirt, the junk down in the crosshatch will give us a false reading. So you want it as clean as you can get it. But the other part is, these are a little potentiometer. And if we get fluid, we get oil, we get some of the nasty stuff inside there, this will stop functioning. And to replace one of these is about $400. Actually, a real good customer, good friend of mine, his name's Don. Don slipped while he was in the hone and dropped this whole thing in the tank. And we'll just say it don't work so good no more. So he had to buy a new stylus for it, which was I think $386 if I remember correctly, plus shipping. So bottom line, yeah, you want that to be nice and clean to get an accurate reading and to not create any damage inside here. Hopefully that answered your question.
Super. We had this question come in yesterday, and so this gentleman would like to know more information on gapless rings versus premium steel. At what point do you recommend customers switch over? Is it things like temperature ratings, durability on both, or how do you classify that?
Okay, no, excellent question. Well, and kind of two different questions, and so we'll answer both. The materials, like we talked about earlier in the program, are about temperature. A typical cast iron ring, and you could, if you had a heat treat oven, which we've got 3 of here, you could kind of play with this stuff. and it's kind of fun. You've got to look at how high the temperature is and how long you're going to sit at that temperature. But depending on the material, at some point in time, you're going to start to creep the metal. It's going to start to lose its tension. And again, for a ring guy, you think I'd have a million rings laying on my desk, but I'll use this one. When you look at a ring, you're going to have a free gap, this open gap. And sorry, this one's kind of not a great example, but you're going to have that free gap. And a great way to tell in an engine how the ring's performing is to look at the ring before you install it. File fit it, look at the gap, measure the gap, and write it down. So if you've got an application that's overheating the ring and it's simply getting too hot, you're going to start to see the gap close up. Let's say, for instance, that was 500 thousandths when it was new. You pull the engine down, it's not unusual to see the ring close up 100 thousandths or 80 thousandths. That's pretty typical. That's about a normal amount of creep in the metal. But if we start to see it doing one of these things, we're down 100 thousandths, 200 thousandths, or the tips don't line up, we've overheated the material. So depending on your application, we now have to look at what the ring was that we're using. Typical cast irons at about 1100, 1200 degrees for about an hour, you're going to start to do this to the metal. But if I take that same cast iron, and even though it's only been exposed to the temperature for a shorter period and take it to 2000 degrees, it's going to do this fairly quickly. So a great way to tell as far as what material you need for the engine is to let the engine talk to you, kind of be the, the ring or engine whisperer. Listen to what it's saying. Look at the parts coming out. Look at that free gap on the ring. That's going to tell you a lot about the condition. If you've been using a ductile iron ring and they come out, the end gaps are great, free gaps are solid, it's not losing its tension, it's holding up well. Well, that one tells you that material's ability to handle heat is working for you. That's right for your application. Excuse me. And it also tells us you've got a good tune-up. If you've got, let's say, the best material in the world, this toughest thing known to man on the, this day and age on the third planet from the sun, and yet it's still coming out like this, that tells me you've got a tune-up issue. If you know you've got a good tune-up, plugs look great, it's not knocking the head gaskets out of it, everything looks great, but yet you're still creeping the metal, you're annealing it, you're taking the tension out of it, you need to upgrade. And that may be the pathway into steel. You may have so much cylinder temperature and are dealing with such a high heat environment, nitrous, turbocharged blower applications, you're simply generating so much heat, you're going to take the tension out of the ring. You have to move up into steels, and then we move into stainless steels, different carbon steels, tool steels, all depending on how much temperature. So looking at the ring coming out kind of gauges what material you need as far as from a temperature point of view. And again, you can also call us and talk to us, tell us about what it is you're doing, and we can make some suggestions. Now, as far as the gapless portion of it, the gapless, that's about eliminating that end gap. That's about eliminating that blow by. That's about, in a normally aspirated engine, increasing the draw on the intake stroke. This is where the gapless really, really shines. By eliminating that gap, and keep in mind, everything we're doing here is trying to improve that ring seal. Right cylinder finish, getting the oil retention we need to keep the ring sealed, keep the scuffing off the skirt, keep this part lubricated, is all about improving that ring seal. And in a normally aspirated piece, it's about drawing air into the cylinder wall. Again, best camshafts, best fuel injection, best oil, all these things, best. If the ring's not doing its job on the intake stroke in a normally aspirated engine, we're going to lose some of that efficiency. So that's where the gapless really comes into play, is how much better it draws on the intake stroke, fills the cylinder better, gives you, as the tuner, the ability to do more, to do a better job, more air, more fuel, more power potential. Now, on the other side of it, into the blower, the turbo type applications, forced induction, the elimination of blow-by, keeping the junk out of the pan. And this does play as well in normally aspirated, especially in big fuel engines, mechanically injected alcohol, diesels, things where we're putting a lot of fuel through the engine. The gapless is really keen in keeping that fuel out. We're stopping it from getting down past the rings, down into the pan, killing the oil. The high performance diesel truck market today is on fire. We all know that. One of the biggest benefits I can do to that diesel is our gapless second ring. Not only does it have less blow by in the engine, but the big one is now it keeps the oil clean. You'll come back 5,000 miles later, go to change the oil. Guess what? Still looks like oil. Doesn't look like black coal because it kept all that fuel out of there. So kind of two different questions there. Hopefully that answered it for you.
Super. Thanks, Keith. So we got time. We'll ask one or two more questions, and then we're going to lead into presentation number 4. Just so everybody knows, we do have prizes to give away, and we will have time at the end on our final wrap up. So do hang on to make sure that you hear your name called for a prize. And so Keith, this one comes up all the time too. They've mentioned they've seen hot honing. They don't use it, but they're wondering how much of an influence that the temperature of the bore is measured and how much of an influence hot honing actually makes.
Well, that's an excellent question, and thank you. Hot honing is really neat, but it creates its own set of issues. I'm a big believer in anything that we can do to help replicate or duplicate that operating condition. You know, if that engine's running at 200-degree water temperature, I want to try to get the inside of that block up to 200 degrees. If it's got a bell housing bolted to it, why not have a bell housing bolted to the block? If it's got 2 cylinder heads, why not have the other head? I want to try to replicate everything I can, because just tightening the fasteners up on it can move things around quite a bit. So yes, I'm a big believer in hot honing. I think it's a great thing to do. The problem with it is, one, you've got to have a hot honing system. And depending on how you're doing it, it can create some kind of honing issues. If you're using one of the CK engineering machines, which is a great system, it's heating the honing oil itself up. So you're not only circulating that hot fluid through the block, which helps to mimic that cylinder distortion, you're also running 200-degree hot honing oil on you as the operator. So there's some things that kind of come in with hot honing. You are and run the potential of having 200, 210-degree liquids thrown at you and splashed on you while you're honing. So that's kind of the downside, is dealing with that hot environment. But the upside is it does help to move the cylinder and replicate it as much as possible into the operating world. So like I said, I like it. I think it's a great idea. But from an operator point of view, it does have some drawbacks. So that one kind of comes to you of what you like to do as far as the additional equipment that's required to do it. And do you mind 200-degree hot stuff getting thrown on you?
Yeah, no kidding. All right, I'm going to ask one more question, just because this particular question pertains to, I think, just about every shop, and it's always a question that comes up as well. So Keith, what are your tips for getting all the honing grit out of the cylinders after honing?
Wow, that's we'll say clean. The process that I use myself, and it works pretty darn well, but it's a lot of steps and a lot of stages, probably what a lot of people do. Is after the honing, after we're done, I'll come back in with a very high detergent oil. A lot of people like to use transmission fluid, but a very, very high detergent oil on a brush. The old cylinder, cleaning brushes. Myself personally, I've got the old Moroso cleaning brush kit, and I'll come in there with something, of that nature, very high detergent, to get in for my initial clean, scrub it out as best I can, get that fluid in there, trying to float that honing junk up out of the crosshatch, get that oil in there, something again that's very detergent, wants to clean, lift that abrasive, lift that gunk, that junk back up out of the cylinder. I'll then wipe it back down, get it good and clean. I then come back in with a good hot soap and water. The screen just flipped and now I'm looking at me, so it kind of freaked me out. I'll come back in with a very high surfactant detergent, something that's a very, very foamy, bubbly. The bubbles that are created in a soap are the surfactant. And surfactant is what helps to lift the junk up out of the hone, out of the crosshatch. So a very foamy, bubbly, hot water solution. I'll come back in, scrub it out with that. Once I've done that, I wipe it back down. Then my third step is I'll come back in with a good lint-free towel. Personally, again, I use those blue Scott towel that you get on a roll, you can buy at Home Depot, any good hardware store. I'll come back in with a clean solvent, a clear solvent, like a lacquer thinner, brake cleaner, something that flashes off really clean, really quick. I'll wipe that back down and I leave the towel, let it sit there, let the solvent flash off. Once it's flashed off, I look at it. If it's clean, there's nothing on the towel, I know my cylinder's clean and I'm ready to go to assembly. But if I've still got, and it'll kind of leave a brownish stain, if I've still got kind of that brownish stain on the towel, I'm not done. I come back in with my hot soap and water, scrub it out again, and we'll say wash, rinse, and repeat. But normally, I'll start off with an oil like a transmission fluid. Again, I'm old school. It's how I was taught, but it always seemed to work. And I come back with a very, very foamy, high surfactant, real bubbly Dawn dishwashing liquid. Always worked very, very well. hot water, scrub it out, clear solvent, and that'll almost always get it for me.
All right, excellent, excellent, super, Keith. Thank you. Very good presentation. Everybody, we still lots of questions coming in, and what we're going to do is we're going to bring on Ben now, and but what we'll do is, like I say, we're going to do a final wrap up. We're going to have all 4 gentlemen. They're going to be on the end. We'll have about 45 minutes to kind of wrap things up at the end. So if there's any more questions you had, or if there's any more questions that we didn't get to, we'll definitely get to those at the end. So what I'll do now is, like I say, we're going to have prizes too, so we'll do those at the end. But Ben Strader from EFI University, and Ben's going to talk about EFI considerations in high RPM engines. So looking forward to this. It's been a great day so far. So how's your day going, Ben? Are you there?
Oh, I'm doing great. Can you guys hear me all right?
You betcha, loud and clear.
Good. First try and everything.
Nice view on your screen. Where's that?
That's just here in our little, kind of our classroom office, whatever you want to call it. But yesterday I was sitting in my actual office and I noticed the background was pretty boring. So I thought it'd be more fun to sit out here where there was colors and shapes and stuff to look at. So.
Well, maybe we'll grab a fishing pole after your presentation. It looks pretty inviting.
Say when. I don't go many places without one in my truck, just in case I got to pull over somewhere. So I'm ready.
Super. All right. Well, I'll let you do your thing.
So hi everybody. I'm Ben Strader, and here with EFI University. Got to do a little introduction earlier. But I know a few people have probably joined in since then. So here at EFI University, we are first and foremost basically a training school. We really want to help other people, get better, especially in racing and motorsports. So we're not really in competition with some of the other places, the sort of mechanic tech schools, the UTIs and YOTechs and stuff like that. We kind of see ourselves in alignment with them and not in competition. So what we really do is focus on the real motorsports oriented type stuff. And I started it back in 2003 with the idea that engine builders wanted to know about EFI and fuel injection tuning. And we've been pretty successful. I think we've taught our courses in about 9 or 10 different countries around the world and had just thousands and thousands and thousands of people learn about engine tuning, including us. So along the way, we've really had the opportunity to work with high-end racing teams, manufacturers at the OEM and the aftermarket level, much like a lot of these guys that have been presenting today have been in lockstep with us the last 5 to 10 years in developing our program and sharing information. So as we learn more things, we refine and renew our curriculums, and we try to stay on the cutting edge as much as possible. So to that end, about probably 5 or 6 years ago, we started an engine development program here where we could share some of that high-end engine stuff with end users. And my goal in that program was not to teach a class on how to build engines. It's not, here's how a torque wrench works and this is how you put the gasket on the right way. We kind of assume that people come to our program have already been doing some engine stuff and probably already have some idea about that stuff, but really want to take it to the next level. And so I joke that we teach the things we most want to learn, and for us that's engine development work. And so quite often there's rarely ever a light switch that you can flip where you find 30 or 50 horsepower on an engine combination. It's almost always working hard and you find 3 here and 5 there and 7, and you keep working and you look 12 months later and you go back and say, wow, now I'm 50 better than I used to be, but it didn't happen overnight. And so a lot of that goes along with this high RPM adventure that I've been on for a few years. And to be honest, most people probably know about us or our school because of the publicity we've got from the Spinal Tap project, which I'll talk a little bit, in our thing here. I know Billy and Lake and Keith and everybody's kind of mentioned too. But that didn't happen overnight either. That started as kind of a hold my beer moment. Billy and I were standing around at one of the PRI shows, and I think it was after NHRA kind of came out with their new rule to limit the engine speed for the pro stock guys. And of course, Billy's been working with a lot of those teams forever. And at that time, I was working with some of the teams helping with the transition to EFI. And we kind of joked like, 10,500 RPM, like anybody could do that. Hold my beer. I bet we could do that with an LS engine. And so we kind of laughed and said, well, maybe we could do that with an LS engine. And that kind of started the whole thing. And it really was one of those things that, we kind of looked at each other and shrugged our shoulders and said, how hard could it be? I mean, we'll just put more cam in it and rev the thing up a little bit. Well, turned out it was a little tougher than that. And, we didn't really think of everything on that project. In fact, it wasn't like we built it and just said, boom, there you go. It's one of those things where you build something, and that's the whole concept of our engine development program. You build something and you sit back and evaluate what things went wrong. It keeps throwing problems and challenges at you, and then you back up and figure out solutions, and you solve that and you move to the next thing. And there's this whole series of dependent events that happen. And so we had a lot of adventures along the way to that. And so when you guys asked me to get involved and do a presentation, I thought, I think maybe I should share a couple of the hoops that we had to jump through or challenges that came up for somebody else that might say, I want to go beyond the normal engine that does, 5,000 RPM or 6 or 7 or, even higher. So because we specialize in EFI and because we specialize in engine development, I feel like we're uniquely situated to share some of that information. And so considerations for operating very high-speed engines with modern EFI systems is what I put together for you guys. And so we are the home of Project Spinal Tap, which was and is the world's first inline LS7 engine to exceed 11,000 RPM. And I'll put in hashtags on purpose. Like we didn't accidentally go there and miss a shift or something like that, but we took an inline, not a canted valve, it was a parallel valve deal, and we worked on it and worked on it and worked on it. We finally got there. And so I'm sure that at least a few of you have probably seen some of that, but I thought we tried this yesterday and it was a little tricky on the technical side to get the sound right, but I'm going to try to show you guys a little video here just so you can hear the sound of it. And so what I did is I made a little video where we focused in on the actual laptop data, and we'll play it through and see if this works for you guys. So there's kind of a shot looking down into the engine. Now, when we ran this thing for real, after all of the spintron testing and all the mocking up and assembly and disassembly and checking stuff, we put it on the dyno and actually ran it. And the beginning of the dyno pull. Now, when we talk about high RPM engines, I think I forget, somebody, Lake or Keith mentioned earlier, like, you don't start at 3,000 RPM, you start up close to where you're going to be. And so most of these dyno pulls that we do on engines like this are typically already starting the dyno run beyond the RPM where peak engine torque happens. And so we're not that interested in that area, because other than when you let the clutch out, you'll never see that RPM in a true, drag race, say like a comp eliminator or pro stock application. We go to 10.5 and you make a gear change and only falls back to maybe 9,000, even though the engine might make peak torque at say 8,000 RPM. So to avoid stress on the engine, you typically start a little higher. So the shot looking down in the throttle bodies of that engine there, and we started the dyno pull at 9,000 RPM and went up from there. So let's try this real quick. You can see here, you might be able to see my mouse. We're basically in a high idle situation, waiting for water temp and oil temp and pan vacuum, everything to build. And hopefully you can hear the sound here when I play it, and you can see the beginning of the pull at 9,000, and then it revs up at about a typical dyno pull rate of like 600 RPMs per second. So let's see if this will play and let us hear it. All right, so hopefully you could hear that. I've probably only listened to that 6 or 7 million times because the sound just never stops being cool. And I saw it in real life. So hopefully you guys like that. Hopefully you could hear it actually. So if you didn't hear it, somebody make sure and let me know and I'll figure out how to play it again. But so here's another example of an engine that we just recently did. That was an EFI conversion. This is a naturally aspirated small block Ford engine. It made peak power at over 10,000 RPM and over 3 horsepower per cubic inch, naturally aspirated, very serious piece. But what's cool about this engine is we use some prototype Holley 4500, what they call sniper throttle body injection units. They flow about 1400 and 14 CFM each. So we had plenty of airflow, but we're kind of moving into this era where we've been told forever that, you know, EFI will never make as much power as carburetors. And so I kind of, you know, I've had to look at that so much over the years and shake my head and go, but in fairness, nobody's ever done a real comparison of, you know, where the fuel's coming from. And so what's unique about the Holley new sniper throttle bodies is that the fuel that is discharged from them, if you look in there in the little inside those bowls, the injector bowls, there's injectors inside those, but they spray into like a little annular discharge ring, and the fuel is distributed all the way around the throttle bore. So when you look down inside them, there's no booster venturis to get in the way. And Billy kind of alluded to that earlier, where in a traditional carburetor, we're very concerned with airspeed through there to try to make sure we're metering fuel out of that venturi correctly. And the downside to that is having that booster venturi there hurts airflow. For a much smaller butterfly size or throttle opening, we can end up flowing a lot more air. The challenge has always been, how do we get the fuel high enough in the system that we get that benefit of evaporation and cooling effect so we can make the power that a real carburetor would make. So for the first time, we were able to actually run an engine and make more power with the EFI system than it made with a carburetor. So we were really, really excited about that project. And it was just phenomenally good from beginning to end. And so I just thought I would share that with you. So it's no longer just EFI as, you know, injectors down in the ports and we have to give up a bunch. We've been working for quite a long time now on these really high RPM engines using EFI. And so what are some of the issues with high RPM? Well, I chose three. There's probably lots more that that get overlooked, but I think there's three areas that sometimes people don't really think about or consider. And so I thought I'd build a little time to talk about each of them in there. So the first one is triggering. That's how we actually get the engine speed and position to the computer that's going to control things. After triggering, we have ignition dwell. If you're familiar with the old school, like a distributor that had points in it, dwell is kind of how long we have available to charge the coil so we can get enough energy. And then after triggering and dwell, we have the injector, what's called the dead time, and the offset. And these are all contributing factors to what makes it difficult to do these extremely high RPMs. So let's take a look here. So starting with the typical trigger system, what you'd have is a trigger wheel, what we'd call the reference. That would be like your RPM signal that's on typically the crankshaft. And then some engines also use a cam trigger, which we'd call a sync, because what it does is it synchronizes the position of the engine. So if I know where, for example, number one cylinder is relative to top dead center, what I don't know if I'm only looking at the crankshaft is whether I'm on the end of the exhaust stroke and the beginning of the intake stroke at TDC, or whether I'm at the top of the compression stroke and ready to start my firing stroke at TDC. By adding the cam sync, we can tell which half of that engine cycle we're on, and then we know how to fire which coil and which injector in the sequence of the engine. So we'll point that out again later when we talk about the idea of sequentially firing a system. And typically you would have either a magnetic or what's called a Hall effect sensor pickup. Those both have pros and cons, but generally what happens is if you're working on an engine, quite often people end up using whichever type came on the engine from the OEM. And so unless you're building an engine from scratch and you needed to choose, there's not really a ton of, you know, upside or downside that really makes one far superior to the other. Both can be used successfully. So typically what that would look like is you'd have a crank sensor here that's mounted physically to the engine block somewhere, and then on your crankshaft you have a wheel that's turning with some predefined teeth, the number of teeth, position, so on and so forth. And remember, that gives me my engine speed and position, but not necessarily the phasing of the engine. So I know where I am relative to TDC, but I'm not sure which TDC it actually is. By adding that secondary sensor, it does the same thing, but this one would be on the camshaft. And now I have a recognizable event, because remember, our camshaft is only spinning half the speed of the crankshaft, and therefore that event would occur less often, and so we can arrange a trigger pattern that makes sense to the ECU to work out where we're at there. Not all engines use those. In fact, the vast majority of pushrod V8 engines in drag racing do not use a secondary cam sensor because it's just more stuff to bolt on and, you know, more wiring to have problems with and things that can fail. So the vast majority of engines use some crank trigger and then typically an ignition distributor. So there's no need to know where the camshaft is because the rotor in the distributor is phased to always point at the right cylinder. And so we're going to look at that here in just a little bit. And since they're not trying to fire fuel injectors in any particular order because it's carbureted, they don't need that cam sensor. So the crank trigger or the ref sensor, it sits in close proximity to that reluctor wheel as we saw, and it provides angular position measurement to the ECU. Your computer would be programmed then with the tooth locations and the number of teeth. And so you'll hear people use terms like LS1 uses a 24X trigger and an LS3 or an LS7 uses a 58X trigger. And what they're talking about is the number of triggering events that are on that crank wheel for one revolution of the crankshaft. So the computer needs to be programmed with the tooth locations and the number of teeth in order for it to accurately understand where the engine is. So then these time-based measurements are calculated to report the engine speed relative to TDC. And what do I mean when I say time-based? Well, many traditional systems, you guys have probably seen an MSD flying magnet. So generally with a flying magnet, you have 4 magnets on the actual crankshaft here, and then we have our pickup sensor down here that's located in proximity to the pickup, so the wheel. So from a physical measurement standpoint, we only get an event every 90 degrees. So when I say time-based measurements, we can actually calculate the time between any 2 events and be able to work out pretty quickly how fast the engine's actually turning and whether it's speeding up or slowing down, so we can predict the right time to, say, fire a coil for a sparking event or maybe even a fuel injector or whatever. But in truth, most of it is based on an accurate guess of working out what the engine speed is after we physically know the position every 90 degrees. So when we put more teeth on the trigger wheel, we get a higher position resolution, but obviously that also requires more computational power. So for example, a stock GM LS, ECU or engine control unit typically limits the engine speed to approximately 8,000 RPM. It goes a little more than that on some, maybe 8,100, 82, but not much higher than that. So in order to make an LS style engine go above that low 8,000 RPM range, the first thing that we had to do was we had to dump the factory ECU and go to an aftermarket computer that was capable of much higher RPMs. There are a lot of things you can change and retune and reprogram in a factory stock ECU, but the hard RPM limit is not one of them. It's hard coded in the ECU and it's not easy to change that. So we did that when we were working on Project Spinal Tap, and after all the work and endeavors and the day that we finally got it running was such a wave of relief that ran over me of, oh my gosh, after all these years, 2 or 3 years of work, it's finally happening. And I'll never forget the first time we revved the thing up, it was like, it's going up. We started 8,000 or 8,500 or something, the thing's going up, and all of a sudden, bang, it just hits the rev limiter. I'm like, man, I feel so dumb after all this time. I forgot to raise the rev limiter, and we hit the limiter at 9,200 or 9,300, and I was like, man, that was a waste of a run and time on the valve springs and whatever else. So of course I go into the computer and I start looking and I go, well, that's weird. That I didn't actually forget. The rev limiter was set at 11,000+ RPM. And so we started looking into it, and we realized that we were actually losing our crank trigger signal in that 58X or 60 tooth wheel, mostly due to Hall effect sensor saturation. So to give you an idea, there's a look at the factory GM LS3, LS7, 9A, all of them. It's got 60 teeth on this wheel. They call it a 58X because there's 60 total teeth that are evenly spaced. But then what they do is they knock 2 of them off, so that every time that missing 2 teeth passes the sensor, we'll know where we are relative to TDC. If I just had 60 evenly spaced teeth, I could count the engine speed, but I wouldn't know the engine position because there's no way to differentiate which tooth actually lines up near TDC. So by having a missing gap, it's really 58 events and 2 missing, so we call it 58X. The nice thing about that is we have 6-degree position resolution because you have a 360-degree travel and there's 60 teeth. So, you know, it works out pretty nice to have a really fine resolution. So you got to ask yourself, why wouldn't you want that? Well, you would want that if you were running a normal vehicle. GM and Bosch and all the other manufacturers that make those kind of wheels, they do it mostly so they can have more finite control of the engine, specifically in reference to things like exhaust emissions. It's easy to detect a cylinder misfire if I can see the engine's accelerations and deceleration rates more often than, say, every just 90 degrees of crank travel. So not only can we see that the engine's speeding up or slowing down, but you could say, for example, I know that in one engine revolutions, there should be 4 excitations of the crankshaft. Every time one of the piston fires, it should speed that crankshaft up a little bit. So if somewhere around the revolution, somewhere around the circle, we see a dip in engine speed or a deceleration, we could work out pretty quickly that somebody didn't do their job and one of those cylinders probably misfired. And we can even tell which one it is if we know where it was in the firing order. So at an OEM level, that high position resolution makes a lot of sense. However, when we get into this really high RPM stuff, here's an example of what a healthy trigger would look like. So you're looking at an oscilloscope trace of a 68X crank trigger with a single long or wide tooth camshaft sink event. That'd be like a typical front mounted LS1 style or LS2 style camshaft trigger. And I don't know if you can see my mouse here or not, but the yellow ones represent the little 58 teeth, and then there's a gap, and then 58 teeth and a gap. But what you'll notice is the camshaft trigger here only happens every other gap, because remember, it's turning half of the crankshaft speed. So now we have a way to tell one of these gaps happens when the cam sensor is high, and one of these gaps happens when the cam sensor is low. So now we can differentiate not only that the gap happens X number of degrees before top dead center, but we can tell you which one of those is near top dead center on the compression stroke, so we know it's time to fire a particular spark plug. So that's what that looks like. But what'll happen on a typical Hall effect sensor like this, it's a little hard to see in this diagram. So what I'm going to do is zoom in a little bit for you. And you'll see here that while these typically are supposed to look like square waves, they get a little bit rounded on the rising edge. The slope here gets a little worse as the frequency or how often we're triggering it goes up. You can even see it here on the camshaft trigger and starting to happen. And even if I go back a little bit, you can now look in that blue and you can see it a little bit there. But notice the falling edge of that trigger is very sharp and very square. Well, our crank triggers tend to do the same thing. So first of all, when you're using an aftermarket EFI system, it's important to understand that if you hook up your crank trigger sensor, you typically have some flexibility to choose. Should I use the rising edge or should I use the falling edge of the trigger that the tooth on the wheel creates? Well, if you're going to do some high RPM stuff, you really want to make sure you're using the falling edge to trigger your events because it's much closer. So what will happen is we go higher and higher in RPM. These triggers are coming faster and faster in frequency. And so this edge gets more rounded and more rounded. And when that slope gets really steep down here, you can fall below the triggering threshold for what your ECU sees as an actual event, and it can get filtered out. And when that happens, you get into a situation where it will just drop a cylinder or cut or misfire, and it will fool you like it did me into thinking that you are sitting on a rev limiter when you're really not. So, so what's the right answer? Do I use a 4 trigger and give up my resolution? Or do I use a 58X trigger and have all the revolutions but have this high speed issue? Well, we ran into this problem in 2016 and 2017 when the NHRA Pro Stock teams went to EFI. Everybody on the surface, wanted the high resolution, but what we found is we got into issues where that could be a problem. And so we tried a bunch of different wheels. We tried 8 teeth and 12 teeth and 24 and 36, you name it. And what we found was the 36-1 or 36 evenly spaced teeth with 1 missing was a great compromise, because with a 36-1 wheel, we get every 10 degrees of resolution is now possible, but we could do a lot more total engine speed with a 36-1 than we could going to a 58X. So with the 58X, we get a little bit more resolution, but at the cost of a lot lower total RPM capability. Whereas when we were going from a 4X tooth to a 36X tooth, we get a ton more resolution. And so just as an example, if you could do 9,200 RPM with 60 teeth, and that was roughly what the limit was, well, if I cut those teeth down to only 36 events per revolution, that's 67% more RPM I could do. So by going to a simple change like going to a 36-1 trigger, we could theoretically do 15,300 and even more RPM. I say theoretically because none of us had the bravery to actually try it, and nobody missed a gear to try it on accident, but suffice to say it has no problem going well over 11,000 RPM like we did on the Spinal Tap project and on most of the high RPM engines that we use around here at EFI University. If it's below 9,000, we'll typically use the factory triggers with no issues. If it's going to be above 9,000, we save ourselves the heartache and we just cap off that rear crank trigger and go ahead and bolt a 36-1 on the front, and it solves the majority of our issues before they become issues. So that's a little something from me to you that will save you time if you decide you want to get into this high RPM game. Just use as much resolution as you need, but not more than you need because it can get you. So there you go. So that's just a little insight on what we learned from triggering. So let's talk about the ignition system then. So traditionally, your ignition system would have a single coil and a distributor, and you might have individual coils per cylinder nowadays with a more modern system. So the question becomes, well, what's the advantage? It costs a lot more. Why would I want to do that? I got more wiring, more things that can fail. So, you know, we could get the location relative to TDC and use that to determine the firing position for both my ignition system and my fuel injection system phasing. And we can fire each ignition event and just let the distributor sort it out, and then the spark plug gets its spark because where the rotors phase. So a lot of people do that, where they'll run, even if they're doing a throttle body type EFI system or maybe carburetors, but they want to run, you know, a distributor. It's easy to do that with a crank trigger and not need a cam trigger. So a lot of people do that. And what we're talking about here when that happens is when we go to charge the coil, we talked about dwell earlier. A lot of people say, what's dwell? Well, it's the time that it takes the coil to charge from your primary, your battery voltage, to the secondary level. And that typically takes between 3 to 5 milliseconds to fully charge. So we're talking about thousandths of a second. So in the graph here, you can see on an oscilloscope from when the circuit begins to draw current as we charge the coil. When it goes flatline up here, we call that saturated. So holding the circuit on to charge the coil longer than that point doesn't do anything for us in terms of potential spark energy, but it does tend to overheat the coil and the wires and stuff like that. And so there are physical limits to how long you want to charge the coil, but there's also requirements for how long you need to charge the coil. If you run out of energy here, so if I started charging this coil and I stopped in the middle before I reached the peak, I wouldn't have the maximum energy available to fire the spark plug. So maybe that's a problem, maybe it's not, but I'll show you, for example, this is, I don't know if you guys can see this or not, a typical modern, this is what they call the Mercury Marine or the smart coil that's used in tons of different applications. I don't have one of the old-fashioned coils to show you because I was born in 1976 and we're not using antique stuff anymore. Anyway, what happens is the construction of the coil has a big influence on how long you need to charge the coil. So the number of windings, how much iron's in there, as well as how much primary voltage you have. If I have a 16-volt system or if I have a 12-volt system, or for that matter, if you have a low battery and you only have 8 volts to charge the coil, it changes how long it takes to reach full spark energy. So let's think about that in a minute. In order to give full spark energy to the cylinders, we're going to need somewhere between 3 to 5 milliseconds to charge each coil. So I got 8 times I got to fire if I have a V8 engine. So that means 3 times 8 is 24 milliseconds, and 5 milliseconds times 8 is 40. So I need somewhere between 24 and 40 milliseconds worth of time to actually charge and fire all the spark plugs with maximum coil energy on a V8 engine. So in our little graph here, you can see the dwell time is how long I'm actually charging the coil from B to C basically, and A, I fire the thing. And now that I'm done, I can rest between A and B in my idle time. I can rest for however long is available before it's time to start charging again for the next event. So thinking about that for a minute, how long does an engine cycle actually take? Now, when I talk about an engine cycle for a 4-stroke V8 engine, remember I'm talking about 2 revolutions of the crankshaft. The first one fires half the cylinders, second one fires the other half. So here's an easy math problem for you to remember. If you want to know how much time it takes for an engine cycle in milliseconds, that's in thousandths of a second, all you have to remember is this easy little formula. It's 120,000 divided by the RPM. Go ahead and try it. I'll wait. All right, that's long enough. You guys are taking too long. I'll just give you an example here. So using that math problem, at 6,000 RPM, we have 20 milliseconds. But at 10,000 RPM, because the engine's turning faster, it only takes 12 milliseconds. And at 12,000 RPM, it only takes 10 milliseconds. Now think about that for just a second. Let's talk about 6,000 RPM. What's actually happening in an engine cycle, right? So we got to start at top dead center, and the intake valve opens while the piston begins to move down. So that creates a larger volume in the cylinder, which lowers the cylinder pressure. So we have a differential across the intake valve that will then cause air and hopefully fuel to start moving into the cylinder. So that piston's going to go all the way down to the bottom, and then it's going to start going back up and start compressing that mixture. And at some point, we're going to close the intake valve so that no more air and fuel can get in and no more air and fuel can get out. And we're going to continue compressing that mixture until somewhere near top dead center, we're going to light the spark plug a little bit early. That's what we call spark advance, to give the flame a little bit of a running start and get an advantage to burn all the mixture in the chamber. Now, that burning mixture starts to expand and it puts power and energy against the piston. That pushes it back down in the bore. It's putting leverage against the crankshaft, but the whole time my volume's getting bigger, so I'm losing pressure. Somewhere near the bottom half of that stroke, or getting close to bottom dead center, we're going to open the exhaust valve and start moving exhaust out of the engine. And then the piston's going to get to the bottom and stop, and it's going to start coming all the way back up again and start pushing that air out the exhaust valve because of the higher pressure being created by the lower volume. We get all the way to the top, and hopefully we'll have a low pressure there in the exhaust system that will help draw some of that air out and scavenge the cylinder, and then we'll be done and we can start over. So I had to do intake valve open, increase the volume in the cylinder, flow air and fuel in, get it all in and trap it. I had to close that. I had to compress the mixture. Then I had to spark it and light it on fire and create a combustion event, push down on the piston to create power and energy. Then I had to try to get rid of it all and empty the cylinder out. Now I had to do all that at 6,000 RPM in only 20 thousandths of a second. It took longer to say 20 thousandths of a second than it did for that to actually happen. Now consider when we did Spinal Tap, I had to do all that same stuff at 11,000 plus RPM, but you're literally filling and emptying the cylinder, and you're literally opening the intake valve more than an inch of lift 95 times per second. 1/1000. That's it. 95 times that just happened. So when we put that into the perspective of what a high RPM engine actually looks like, sounds like, and what's going on, it's really interesting to imagine all the things that need to happen in the perfect order and sequence in the little tiny amount of time that we actually have. But this formula doesn't just work for nice round numbers like 6,000, 10,000, and 12,000. You can do anything you want. You could say, how long does an engine cycle take if I was doing 5,374 RPM? You want to know? Take 120,000, divide it by the engine speed, and you'll know. So that's for you. You'll really use that. You'll really like that if you use it more in the future. So as you can see then, if I have a single coil, even in the best case scenario where it only takes me 3 milliseconds, let's say, to charge my coil, and I got to charge it 8 times, that's 24 milliseconds. Well, at 5,000 RPM, the entire engine cycle takes 24 milliseconds. That means with a single coil, after 5,000 RPM, I'm no longer able to completely charge and discharge the standard old-fashioned, points ignition or HEI style ignition coil. We physically do not have enough time left in the engine cycle to do that. Now, traditionally, the way to overcome that is start with a huge excess of coil spark energy, more than we actually needed to get the event done, so that as I'm losing some, I don't fall below the required amount that it takes to actually light the cylinder. So you can see here in this slide, some of this can be overcome by using an ignition system that starts out with a large excess of energy, such as an MSD like capacitive discharge ignition system. And basically what would happen there is The CDI stores energy in capacitors and can have a much higher primary voltage delivered to the ignition coil much faster, so we have more excess of time available. But even though our RPM is going up and up and up and up, I'm still going to have more ignition energy than I actually needed to fire the spark plug, so I can kind of get away with that time, as Billy calls it, the time-space continuum. And so while we could solve that distributor-based problem with a CDI, and we could get the spark energy we need, we still have a physical limitation by using a distributor rather than individual ignition coils. That maybe isn't a problem for a naturally aspirated drag racer, but if you're doing nitrous, if you're doing some form of boost with a procharger, supercharger, or a turbo, quite often you have pretty extreme swings in what you want to do with your ignition timing that are limited by the physical travel of the distributor and the rotor phasing inside the distributor. So by going to individual coils, then we can use a cam sync instead of just having a crank trigger and a distributor. If we use a cam sync, since we know where we are within the engine cycle, we could tell if I'm on the exhaust stroke or the TDC compression stroke. So now we can fire each coil and fuel injector simultaneously and in order, in the correct firing order. So if you think about that, where I had one coil that I needed to fire 8 times in one engine cycle, now I have 8 coils that individually only need to fire 1 time per engine cycle. So 1 divided by 8, obviously you get the idea. I have 87.5 more time for the coils to rest and be able to recharge. So in terms of doing high RPM, high energy type ignitions, you know, the benefit that we gave up by not having the high energy CDI capacitive discharge ignition systems, which in fairness produce a very hot spark, they do it for a very short duration. And so what can happen at extreme engine speeds is, even though I get a very hot spark from a capacitive discharge ignition, the actual spark event only lasts for, you know, 1 or 2 or 3 degrees of crank rotation. So if anything happens with your mixture distribution inside the cylinder where you miss it, you're out of luck. You're going to have a cylinder misfire. Even though the inductive style ignition systems like our smart coils, even though they technically have less energy available than a traditional CDI would have, they typically will discharge that spark across the plug gap at, say, 10,000 RPM for something in the order of 14 or 15 total crank degrees. So you might get 6 to 7 or even 8 times as long of an opportunity to fire the mixture because of the length of time it takes the spark to jump across the spark plug. So I'm a big fan of using these smart inductive style coils in a high RPM application because I have enough spark energy to do the job. I get a long spark duration to give me the most opportunity to make sure I get the mixture lit, and I get a lot of time to be able to make sure that coil is fully charged. So a great example of a way to use modern technology in a high RPM engine. So here's an example of individual coils in each cylinder. It gives us the ability to have extreme advance or retard functions, such as doing boost enhancement or smoother rev limiting. A lot of people say, what do you mean by rev limiting? And if you think about what's happening to the engine and the crankshaft, if you're at 10 or 11 or who knows what RPM, and all of a sudden you start banging the rev limiter, the amount of torsional twist that happens to the crankshaft because of one cylinder that's not doing its job, or 2 or 4 randomly. So we're pounding on the crankshaft and the counterweights are doing their job to try to keep everything in balance. And then all of a sudden I don't for a couple of times. That twisting motion of the crankshaft takes a beating, and so does everything else behind it, drivetrain and everything. So by being able to do some of our rev limiting by retarding the ignition timing, much like an OEM strategy, we can limit the engine's torque output temporarily with a 1 cycle or 2 cycle retard function rather than simply a cut and chopping that cylinder off. So we get a lot of advantages to the individual coil per cylinder type application in a high-speed engine that aren't necessarily showing through on the surface if you were only to look at the spec sheets of how much energy this one has and how much energy this one has. It doesn't really show up until you actually start doing this stuff. So there you go. Hope you guys like that. So let's talk about our fuel injectors. And I know I'm going kind of fast, and I'm not trying to buzz through it or you know, gloss over information, because I'm sure there'll be some questions, but I want to make sure we get through it, give you guys lots of time to enjoy and talk and ask questions. But one of the big ones that pops up a lot is what happens to the fuel injectors in a high-speed engine especially when we do this without a cam sync sensor. So let's talk about it a second. So the injector is really a solenoid valve. You have fuel coming in the top, and we have a valve that closes it. We have a electromagnetic coil here, the red part in the middle, and we energize that coil, and it becomes magnetic, and it draws the valve up off the seat. But remember that it has to do that against our fuel pressure too. So the differential pressure across the nozzle of our injector has a big effect on its performance, as well as how strong the magnetic field is in the injector. So when we talk about injectors, a lot of people talk about the injector size and the flow rate of the injector and pulse width and duty cycle and all these different things. But the one that I want to focus on for just a minute here is called duty cycle. And if you're not familiar, I want to simplify it for you, because the duty cycle of an injector is the comparison of the flow capacity of the injector to what your engine actually demands. So there's more technical ways to describe it when we talk about the relationship of injector pulse width to time per engine cycle and all that. But bottom line is, if you just think about it like this, the more horsepower your engine makes, the more fuel you're going to require. So, you know, you've got a dyno graph here. Whether I make 1,200 horsepower at 6,000 RPM or 12,000 RPM at 8,900 RPM or 9,800 RPM or 18,000 RPM, the reality is 1,200 horsepower requires a certain amount of fuel. So that being said, here's an example. Let's say I have a V8 engine and I have 8 injectors. Now these injectors, here's one, and here's one. They flow 80 pounds per hour each. That's what we call the slope of the injector. So since I have 8 of them and each one flows 80 pounds per hour, we could assume that I'm going to have a total of 640 pounds per hour of fuel flow available to give my engine. So what determines how much of that fuel flow the engine's actually going to see? Well, the answer is how much power you make. So let's say we have an engine that makes 1,200 horsepower. Now this 1,200 horsepower engine has a brake-specific fuel consumption of 0.45. If you're unfamiliar, brake-specific fuel consumption is a measurement that we take that shows us, for the amount of fuel we actually consumed, how much power did we actually make. So a typical high RPM, naturally aspirated, high compression engine, they'll be 0.45 or better. Most of the time even better than that, but this is a good example. So let's say I need to feed a 1,200 horsepower engine, and it needs 0.45 pounds of fuel for every horsepower per hour. Well, doing some quick math, if you multiply 1,200 times 0.45, you see that we're going to need 540 pounds per hour to feed the demand of that engine. Make sense? All right, so now let's compare how much fuel we need to how much fuel we actually have available. So in the next slide, we're going to need roughly 84% of the injector's capacity. Regardless of what engine speed we're talking about, we're going to need 84%. But percentages and real actual time, they're not the same thing. So let's take a look at what I'm talking about. Now, the slope of the injector determines how much time it will take to deliver the required fuel flow. So when I talk about that, what I mean is, we said the injector flows 80 pounds per hour. So since the slope is assumed to be fairly linear, it should then, if it gives me 80 pounds in an hour, it should be able to give me 160 pounds in 2 hours. And for that matter, it should give me 40 pounds in half an hour. And again, assuming our slope is linear, which at least in the usable portion, we're hoping that it is. But what I'm getting at is the slope is a linear amount of fuel delivered the more I increase the time that I turn the fuel injector on for. But pulse width is what we use to determine how long the injector is turned on for. So I'm going to have to give this injector a pulse width that will deliver the required amount of fuel to feed that engine's 1,200 horsepower. The question becomes, how much time is available to give it that pulse width? And the answer is, well, it depends on your engine speed. So let's take a look. So the injector is a solenoid valve. Here's the problem. Being a solenoid valve, the valve takes time in order to respond to a command. So for example, in our drawing here, what I have in blue is a theoretical pulse. This is the command where your computer turns on and says, hey, start flowing fuel. It goes bang, and it holds it on, and the distance that it holds that on in time is called pulse width. So theoretically, in my mind, I think, okay, the longer I hold it open, the more fuel it flows. And for the most part, that's true, except for the fact that if we go back and look at our injector, you can see that this magnetic coil needs to energize once that signal command comes, and that magnetic field needs to draw that pintle or that valve up off the seat, and that doesn't happen instantaneously. So because it doesn't happen instantaneously, we have a little bit of time where the injector misbehaves and doesn't do what we tell it. So we call that offset or dead time. Now, what affects the offset and the dead time are primarily three things. The physical makeup of the injector. How heavy is that valve in there? So take a look at this injector here. I hope you guys can see that. And then take a look at this injector here. This one has really lightweight, small components inside of it. This one has rather large, big components inside of it that allow it to flow a lot more quantity of fuel. But as you can imagine, the heavier those components get, the longer it's going to take before that injector can physically respond to that command impulse. Now that I got it all going and I say, okay, I'm good, stop, you can shut off, just be done, it takes a little bit of a time to put the brakes on and shut everything off as well. So the physical construction of the injector has a huge outcome on how much that dead time is. The next thing that affects the fuel injector is the actual fuel pressure that you're putting in this thing. If you put more and more and more force down in there trying to hold that valve closed, it's going to be more and more difficult to get that valve to open against the pressure. So fuel pressure will affect your actual dead time. And last thing will be battery voltage. The lower the voltage you have, the longer it's going to take and the less strength your magnetic field is going to have to be able to move that injector off the seat. So those are three things that are going to affect how much dead time we actually have. So when we look at that, here's an example of a dead time or a flow data sheet. This I stole from the guys at Injector Dynamics right off their website. So it tells me that they have an ID 1000 part number, and this is the dynamic flow data. Now, over here on the far right side, what you see is the actual slope, or what people would call the flow of that injector. You'll notice that the slope increases with more fuel pressure. Makes sense, right? If you had a garden hose and you turned up the water pressure, more water is going to come out in a period of time. But you'll notice that the offset here, which is in the table, and it's plotted out in microseconds, which we need to move our decimal place to get milliseconds. So for example, here at 40 PSI differential fuel pressure and 12 volts, we have 1210 microseconds. That would be the same as 1.2 milliseconds, okay? But what you'll notice is that for any given voltage of the battery, as my fuel pressure goes up, the delay or the offset that it takes to make the fuel injector open gets stronger, gets longer. And sometimes if we have a really low battery voltage, like over here at 8 volts, we get to about 75 PSI, it just plain won't open at all. So the dead time goes to infinity and you get zero flow out of that injector. So you'll notice that the higher the battery voltage is and the lower the fuel pressure is, the faster the fuel injector can respond. And so they give us this data so that what we would do then is program that table into our fuel injection computer. The computer will then reference the battery voltage and the fuel pressure at any given moment, and it will calculate how much fuel requirement the engine has so that it can work out what the pulse width needs to be to deliver the fuel. Now, we would typically call that the effective pulse width. The problem is, to get my effective pulse width to equal what the engine's demand is, I have to add the lost offset or the lost dead time. So when I take my effective pulse width, and I add in the required amount of offset time based on fuel pressure and battery voltage, what I get is the actual pulse width that's delivered to the injector, so that I might have to deliver, 10.5 milliseconds in order to get 9 milliseconds worth of actual flow out of the injector. So that's an important differentiation that a lot of people misunderstand. But when you start doing very high RPM engines, it becomes very critical. And let me show you why. So traditionally, people would say that you should limit your injector's duty cycle in an engine to 85%, and nobody ever really questions why that is. I hear people say things like, oh, it's because you don't want to overheat the injector and whatever, and it's like, no. You have a cooling medium flowing through the injector all the time anyway with your fuel. It's not about overheating it. It's about making sure that there's enough physical time left in the cycle to make the injector behave. So I'm gonna draw a picture for you, or with my words anyway, and let's use an example. So let's say I got my fuel injector, and based on my battery voltage and my fuel pressure, it has an offset or a dead time of 1 millisecond. Now, 1 millisecond, that's only 1,000th of a second. It's not that much time, but every time we fire this injector, we're gonna lose 1,000th of a second. So since that's a pretty small amount of time, it almost doesn't matter. And since, I don't want to add a lot of complexity to my system, I'm just going to ignore the cam sync. And what I'm going to do is just run a crank trigger and fire the injectors however I need to. So let's find out, what is all this dead time actually going to cost me in real numbers? Well, there's two ways that I can deliver the required fuel. Remember, it's required. I have to get that fuel into the engine. Otherwise, I'm going to be calling up Lake and Keith over there for a new set of piston rings after I lean it out and burn this thing up. So we want to keep that cost down. So we got to make sure we deliver the required amount of fuel. The engine is demanding that fuel, not asking for it nicely. It's saying, I got to have it. So a typical fuel delivery system, you got your tank and a strainer and a fuel pump, and it goes through a filter, and you have a pressure regulator that's keeping our pressure where we want it. And we have fuel injectors. So the fuel injectors turn on and off to deliver the fuel. And there's a couple different ways that we can manage the injectors that we have. Assuming that what we have is more than one fuel injector, we have to decide, do we want to fire them all in a sequential order, one at a time? Well, that's ideal, but we need both a crank and a cam sync sensor to be able to do that, so we can fire them individually within the firing order and place them at the right time in the cycle. But again, that cam sync, it adds a lot of complexity, and I just don't want to deal with it. It's more money. So there's nothing wrong with doing what's called batch fire injection for most engines. Now, in a batch fire system, we don't need the cam sync because we're just going to fire the injectors every revolution of the crankshaft instead of every other revolution in the firing order. What we're going to do is I'm going to cut the time that I fire the injector in half, but I'm going to fire it twice as often. So there you go. I get the same amount of fuel, half as much, twice as often. Everybody's happy. Well, let's think about that. So that means if I do that, though, on every engine cycle, since I turn the injector on twice, I had to pay for the offset and the dead time twice. So here's the deal. We are going to assume we have an injector with a dead time of 1 millisecond, 1,000th of a second. So that means we know from earlier that we had a 1,200 horsepower engine and it had a 0.45 brake specific. I'm just going back to our example. So we have 8 injectors. They flow 80 pounds per hour. So we have 640 pounds per hour available, and we need 540 pounds per hour. So we're going to need 84% of the capacity. In other words, I'm going to have to use 84% of the time available in the engine cycle to be spraying fuel. So that means whatever the engine speed gets to, I got to make sure that there's a minimum of at least 2 milliseconds left over to accommodate the offset or the dead time of my injector. If I don't, I will start cannibalizing my fuel flow into my dead time, and I will no longer have precise control over how much fuel the engine actually gets. So let's go back and look at our earlier example where I had 6,000 RPM. Well, that takes 20 milliseconds. So that means if I take my 2 out, I'll still have 18 milliseconds available to be able to spray fuel. At 10,000 RPM, there's only 12 milliseconds total available. I still have my 2 milliseconds worth of dead time because it's 1 per fire and I'm firing it twice per cycle. So then now I take my 12 and subtract 2, I'm only left with 10. At 12,000 RPM, it gets worse. I only have 10. I take my 2 out, now I've got 8. So using a little bit of algebra, we can go in and figure out, well, if that's the case, if you want to do this without a cam sync sensor and you're going to batch fire your injectors, you're only going to be able to get to about 9,600 RPM before you lose control of your fuel injectors. At 9,600 RPM, using our little formula, 120,000 divided by the RPM, we can see that there's 12.5 milliseconds available per engine cycle. So if I take my 2 milliseconds out for my dead time, since I'm batch firing this thing twice, that only leaves me with 10.5 available. Well, 10.5 available, 10.5 worth of flow out of 12.5 available, that's my 84%. So if I start increasing the RPMs above 9,600, I'm going to take my 2 milliseconds worth of dead time out, but then I'm not going to have enough time left to accurately flow all of the fuel the engine needs. So high RPM engine operation gets tricky if the dead time of my injectors are really large. So the question becomes, what are you going to do about it? Well, if you're the kind of guy that just runs big block Chevys, old school, and you want to convert to EFI and it's going to go in a boat and you're only going to see 5,500 RPM max, it's really not a problem for you. Forget everything I said and don't worry about it. Just go about your way and enjoy your day. However, if you're like me, 5,500 RPM is just kind of high idle. We're just waiting to start the dyno pull at 8,500 or 9,000. And so we actually have to pay attention to stuff like this. And ask me how I know, I'll be glad to tell you. So the question is, what do I do about it? Well, first and foremost, I could change to a sequential operation by using that cam sync sensor, because now I'm only going to fire the injector once per engine cycle. That means instead of having 2 milliseconds of dead time total, I'm only going to have 1. So I've cut that offset in half. It allows me to increase the range I can get to. The other thing I could do is I could use a larger flowing injector, because then the amount of time that I'll need to hold the injector open to supply the required amount of fuel that the engine needs will get smaller. So if I have an injector with a larger slope, I will need less time available to do the job. Or instead of using a 12-volt battery system, maybe I go to a 16-volt. You'll remember that the amount of time that it takes to offset the injector is dependent on battery voltage. So the more voltage I have available, the less time I have to waste waiting for the injector to respond. So then obviously I got more RPM capability available to me. Lastly, choose an injector that inherently has a lower offset. If you can find one that has a low enough offset, that has a high enough slope to give you the amount of fuel your engine requires, it's a great fix. And so all of these are things that we needed to do when we were trying to make these EFI, naturally aspirated, high compression ratio engines go to 10,000 RPM and beyond, because they were things that didn't used to matter, and now all of a sudden they did. So hopefully that was interesting and thought-provoking and gave you some ideas of things that you might want to implement in your own project. None of it's meant to be an absolute. We are always in the research and development learning stage, if you will. I like to say at EFI University, we only teach the things that we really want to learn. So with that, I'm going to open it up and take some questions, and we'll talk about it.
All right, super, Ben. That was a great presentation. That's
Thanks.
something that a lot of engine builders in the shops, and we don't get a chance to see, the stuff that you're showing. It's sort of a, we're learning tooling techniques and honing and that kind of stuff, but to actually learn about what's going on the outside, that was really, really well done. So thank you very, very much.
Yeah, no worries. Sure. Fun to share this.
Yeah, you betcha. What I'll do, I'll go to one question. We'll go one question for Ben, and then just to kind of keep things rolling on time, we do have other questions, Ben, and we'll get to those sort of while we wrap things up here. But the one question I've got that they're asking is, let's see here. Do cylinder pressures increase proportionally with engine speed?
No, most of the time they go down. Cylinder pressure is directly proportional to torque output. So your highest cylinder pressure is typically going to be where your engine makes peak torque. So if you look at like a typical dyno graph, you'll have a peak torque, and then your power continues to go up after that, even though the torque is dropping off. And the reason is that horsepower is a function of how much torque you can do over a period of time. So one of the secrets to making huge power per cubic inch numbers that we typically brag about, which frankly aren't that valid, is that as we do more RPM, we can get away with less cylinder pressure because we're simply doing it more often. For example, the classic definition of power is torque times RPM divided by 5252. Most of you guys probably know that. So what that really means is if my torque is 500 when I'm at 5,250 RPM, well, divide that by 5250, that means my power is also 500. But if I make 500 foot-pounds of torque at 10,450 RPM, that's the same amount of work that I'm doing every time I fire the piston. However, I'm doing it twice as often. So my 500 foot-pounds of torque becomes 1,000 horsepower at 10,450 or 540 or whatever the number is. So the cylinder pressures in a really high RPM engine, at least a natural aspirated one, are typically quite a bit less than other engines, simply because our volumetric efficiency tends to go down as we have less time to fill the engine with air. We're just making more power because we're doing it more often.
Okay, gotcha. Yeah, no, good info. All right, so what we're going to do now, let's bring everybody back on. So, we got Lake back on, and Billy and Keith, and again, Ben, thank you very much for your presentation. That was very well done. And we do have some more questions here for you. We'll just bring the whole crew back on here. And
nice to
this was a great day. I mean, to have you guys do what you did for us today. I mean, you literally spoiled us. And we realize that all of us, I mean, we're located all over the country here. So to put this together with technology and everybody's time, it was very well done, and a lot of really good information. So There you guys are, for sure. So everybody's back up there.
Getting the band.
What I'll do now.
No mute now. Okay, hey, so
there you go.
Ben was talking, right? So I have a question for Ben. Okay,
Oh, I
so
thought you were taking
yesterday, right? So yesterday I was dynoing or trying to break in that 250cc. I know I'm looking at I'm looking at Ben, not the camera. So I was trying to break in, or I was breaking in that 250cc engine, and I was just doing it on the run-in, Dad's run-in stand, which is basically a hydraulic pump, right? So I could load it up. And one thing I noticed is that just kind of beginning to, once it got some heat in it, was bringing up and making some sweeps with it, that at a low load setting, as it would rev up, I couldn't even get it to full throttle, and it would start cutting the ignition. I was like, something's weird, and scratching my head. Well, best, let me try putting more load to it and making a slower sweep, where I couldn't get beyond 7,000 RPM on that thing without any load on it, really. I can go to 9,200 RPM with load on it. It's EFI, and it's got a Delphi system on it. Do you think there's some kind of math in there that if it's accelerating too quickly, that it starts to cut the ignition? I mean, it didn't sound like a red one, but it was like weird.
My gut tells me you probably had more of a fuel delivery problem than an ignition one. And the reason I say that is when you try to rev on the dyno really slowly, you typically have to open the throttle very, very slightly, right? And so, because if you just whack the throttle wide open, it'll run away from you. Well, what happens is most people, including the OEMs, don't or can't spend a lot of time calibrating the engine at very high engine speeds with very low throttle settings, because you typically don't have enough engine power there to overcome the friction of the engine. So they have to motor the engine to even get it there, right? So what I've observed, especially doing that exact same thing on a lot of our engines, is that when you have, 5 or 6 or 7 or 8% throttle opening, but the engine zooms up because there's no load on it, it will typically get very low manifold pressure. And when that happens, the ECU will then calculate a very low air density and really draw back the amount of fuel it will supply the engine. And so I will see this all the time where guys will try to creep up the throttle opening and it'll pop and bang and misfire and run rough. And they go, man, it never did that when I had a carburetor. I'm like, well, your carburetor was giving it enough fuel for that application. So if you go down to the bottom end of your fuel table and you add some fuel in there, I'd be willing to bet Keith's salary next week that it runs smoother that way.
I was thinking about this yesterday. It's like, wait, I'm going to hold that question. I'll see Ben tomorrow, and I'll ask Ben.
Glad you did. That's cool.
Yeah.
Awesome. Hey, guys, let's just take 2 secs. We got some pretty awesome prizes to give away here real quick. Like I know Ben's got a really cool prize. So, Steve, what I'm going to do, I'm going to go back to you for just a minute, and let's give away the rest of that stuff, and then we'll go right back into the question and answer.
Sounds good, Rob. Okay, what we got, Ben has donated a online course gift certificate worth $349, and he's got a special code for that, and it's a one-time use. And what I'll do is, Ben, I'll pick the name, and then what we'll do is we'll just get you guys in contact together, and you can kind of walk him through the process or whatever needs to be done.
Yeah, great.
All righty, so we're going to pick the name here. Jerry Roberts.
All right,
so Jerry, we got your email address here, so probably next week we'll get everybody their information on their prizes and stuff and get that out to you guys.
And like I said, while that voucher code is for a specific group of our online training, which has been very popular lately with the COVID, if Jerry, if you decide you want to use it on something else, just let me know and we'll apply the value to whatever else you want. Enjoy it.
Okay, and then we also got a Total Seal $100 gift certificate. And let's see, the winner of that is Tim McCormick. So Tim, will get that information out to you regarding your Total Seal $100 gift certificate. And we got an AERA hoodie here. And let's see, that winner will be Ronnie Stidham. So Ronnie, we got a hoodie coming your way, so we'll get to you on some sizes and get that taken care of. And let's see, we got another prize here, an AERA soft-sided cooler. And that is going to go to Hank Coburn. Hank will get that together and get that sent out to you. And we have one last prize. We have another $100 gift certificate from Total Seal. And that prize is going to go to Jeff Baldwin. So Jeff will get that together for you and get everything out to you. All right, Rob, I'll turn it back to you.
Sure. Yeah, no, thanks. Some good prizes there. So just going to go through, yeah, we've got questions that are still coming in. So let's go to a couple here. Keith, this one's going to be for you. What grit flex hone would I use for a nitrided top ring on an OEM iron block and leave a plateau finish for the final stage?
Well, that one's kind of a tough. I mean, the ball hone is really made for plateau honing. Its function really is to deglaze the cylinder or plateau after a rigid stone. A nitrided top ring has no coating. It's just a hardened steel ring. So again, kind of like we were talking about, it has no ability to hold oil. So my recommendation there is to kind of two-step it. I'd probably go in with a rigid hone, maybe a 220 to 280 on the rigid, give it a couple strokes just to, again, lay that valley and get that RVK back in. Then come back in with a ball hone, about a 320 grit, half dozen strokes. That should give you some valley for oil retention and knock the tops down, get that plateau.
Super, thanks, Keith.
Welcome.
Alrighty, we have a question for Billy Godbold here. And the question is, the gentleman is interested in how using a positive displacement blower influenced choice of intake closing event.
There's the intake opening or closing?
Closing.
Okay. Intake closing, you know, on the intake events, the positive displacement blowers are really interesting on the intake opening. Intake closing is a little bit interesting because it depends on the port geometry that's going on. You know, if you look at a lot of positive displacement motors, whether it's a top fuel motor or something like the Mitsubishi 4G63, you know, a lot of these things have really short ports that the port's really not wave tuned. It's just sort of there. And in that case, you don't have to have as late of a closing as you'd think. But if you take a positive displacement blower and you can have a longer intake runner on it, you know, Edelbrock's a sister company to ours, and they do a pretty good job on their positive displacement blowers of actually making a fairly decent intake manifold with the blower. The better the intake manifold is with the blower, the longer runner, the better that's done. Then you can have the intake closing very much like you'd expect with a normally aspirated. Now, on a positive displacement application on the intake, the opening side actually is more sensitive to the closing as far as what people often get wrong. What I mean there is, like, if you take a guy who has a 4-liter blower on an LS, he may open the valve absolutely as soon as he can and not crash in the piston. It's always, the earlier you can get it, it's always going to flow more air, especially say if he's making 1,000 horsepower. But he's got 25, you look at the compressor map on that blower, it's a 2,500 horsepower compressor map. You get into NHRA factory shootout, that compressor map, you're scratching your head going, that thing might make 1,500 horsepower. And you got to make 1,500 horsepower to be competitive. So you can't open the valve so early that 300 horsepower go through during overlap. So the intake opening on positive displacement blowers, very sensitive to the size of blower. For a given RPM, those two applications, though, would absolutely have the same intake closing. So if you're running a Coyote and Super Stock and a Coyote and Stock Eliminator with a blower, even though one blower is twice as big as the other, the intake closing will be the same. Same thing if you had a 9,500 RPM LS had a 4-liter blower and a 2.3 liter, the intake closing would be the same as long as the runner length was the same. But the intake opening would be very different between the small blower and the big blower because of the compressor map, and you're really just running out of, you can't waste any air with a small blower. Ben, did I do that okay?
That was pretty good, buddy. I was thinking that.
All right. Question for Ben. When changing from a Dominator carburetor to a Sniper, will the intake manifold need to be modified as far as plenum volume and cross-sectional area of the runners to get the best performance?
So the plenum volume and cross-sectional area, let's talk about it in two different things. So a cross-sectional area of the runner is really there to feed the engine what it needs. So the area is about, total airflow, and the length is about the resonant tuning. So really, you're not going to change that whether you have a Sniper, EFI, or a Dominator. The biggest thing that we saw was on a carbureted engine, we typically make the intake manifold so you can separate the top and you can make plates in there to space it. And we'd have, half a dozen different spacer plates because you really got to play with how much plenum volume there is. So the plenum acts as like a reservoir for airflow to be able to feed the runners when the cylinder demand gets higher and higher. The problem is if you make that reservoir too large, then you can't adequately create a large enough pressure differential across the booster and the carburetor to draw the fuel out. And so if you get that spacer too small, you kind of choke the engine for airflow. And if you get it too big, then you can't deliver the fuel the way you want it. So in a carburetor engine, that plenum volume is very sensitive, typically somewhere between about 100 and about 102 or 3% of the engine's displacement is a good plenum volume to start with. So if I got a 350 cubic inch engine, I want my plenum volume to be somewhere around 350 or just a little bit more cubic inches of plenum volume. Now, when we move to the Sniper, because you get rid of the Venturi, and B, we no longer need that signal strength. Things like block deck height, which used to be a huge issue for these engines, is not. So what I'm getting at here is take a Pro Stock engine, for example, the deck height's critical because the length of the runner primarily dictates the resonant tuning at the RPM they need it to be. So if you want to peak at 10,500 RPM, the port length is X and your runner length has to be that length. Well, because the engine's a V, if I make the deck really tall out here and I have a really short runner to get it where I want, to connect those two in the middle, my plenum gets really big. Well, when the plenum gets really big, then I lose the signal to the carburetor and everything else. Well, by going to an EFI engine, we don't care about that signal to the booster Venturi anymore. So our plenum volume is able to be bigger than you would normally think it needs. That being said, we've done a bunch of testing and I haven't yet found any huge advantage to having more plenum volume than you actually need. So what we come down to is we can increase the airspeed through the butterfly by having a smaller butterfly diameter than we would typically have in a Dominator carburetor. So for example, you might have some fancy aftermarket Dominator carburetor with a 2,500, 2,600, 7, 2,800 throttle bore to be able to flow the 1,500 plus CFM it needs. But traditionally what happens is the airspeed through there is so terrible that you're only really able to trim the fuel delivery curve at one RPM range or another of the engine. And it gets worse when we have high transients. Billy, you talked about transients earlier. And I think one thing people miss is it's totally fine to do a 600 RPM per second dyno pull. We're going to start at a stabilized 8,000 and we're going to pull it to 10.5 at 600 RPMs per second. Problem is, that's not the way the engine goes down the drag strip. It goes through low gear at about 2,500 RPMs per second in a Pro Stock car, and that's as it's drawing the engine down because the clutch is locking up. In second gear, where everything's locked up, we might see 3,000, 3,200, even 3,400 RPMs per second of acceleration rate of the engine. That's nothing compared to the transients that the engine sees during a shift, when we might see negative 15,000 RPMs per second when you go from 10,500 to 9,000 RPM almost instantaneously. And so the reaction time that it takes for the carburetor to keep up and trim the fuel flow just can't happen. So you see wild swings in air-fuel ratio as it goes down the drag strip. We've eliminated to a large extent that with the EFI systems by using higher airspeed through the throttle blades, because we can use a 250 or a 2,300 size throttle blade and get the same total CFM that we used to have a 2,600 or 700 to get. So the plenum volume has a big effect on that with a carburetor, but not a huge effect with an EFI system. I hope that didn't ramble too much and go off the reservation there, but that's an area that we've spent a lot of time looking at.
Super, thanks, Ben.
Okay, our next question is for Lake. What's a good amount of zinc in parts per million for flat tappet camshafts and mild performance motors, say in the 450, 500 horsepower range?
Did Billy ask that?
No, he did not.
Really, I was building on that one, right?
This individual has heard 1,000 parts per million. What's your thoughts?
Well, if I want to be the smart ass, I'd say, well, what type of zinc are you talking about? I mean, there's zinc and pennies, and you put 1,000 pennies in there, and it's not going to lubricate very well. But I won't do that though. The best type of ZDP for flag tappet camshafts, as we learned working together with Billy, is the secondary ZDP. So the secondary type of ZDP is the best, and we saw really good results around 1,200 to 1,500 ppm of ZDP. That's what that range, not for break-in, not for break-in. For break-in, we actually saw pretty good results from anywhere from around 1,800 to up to 2,800. That was pretty forgiving in that range. If you get below that, things weren't good. You get above 2,800, things started to go away. There's a curve. I can actually draw it out if somebody really wants to see it, but they have to tell me before I go grab my pen and paper back here and draw it. There's at low levels of ZDP, wear is very high. As you start adding ZDP, wear decreases, and then as you add more ZDP to a point, wear takes back off again, it increases. Kind of like the Stribeck curve we saw. So really you want to be in that optimal range. That 1,800 to 28 of secondary is what's ideal for break-in. Past break-in, you want to be in that 1,200 to 1,500 range. That works really good for non-coated flat tappet deals and stuff like that.
Perfect. Thank you.
No problem.
All right.
Yeah, I just laugh because there's so much more going on than just that the people think that that's the deal, and it's just not. There's so much more going on with the chemistry.
So Lake, if you want to get them back, ask what's the right LSA for an LS engine, right?
You're number one.
One thing I want to say is that until like 10 minutes ago, I had no idea that there are people who had asked me questions privately, and I haven't answered them yet. So I'm sorry.
I didn't know that either. Maybe I have questions.
I will get to them. I had no idea there was all these questions, and I wasn't ignoring you. I just didn't know they were there. So.
No worries. All right, Keith, this one's for you. How thin of a ring can you still gas port?
We're able to take them down to, at this point, we've done as thin as 0.6 millimeter.
Okay. All right. Thank you.
Yes, you want those. They're good.
Yeah, really, as a matter of fact, in between sessions, just sold some gas ported top rings to a gentleman with a Subaru that Lake's been in contact with. And I know they're going to do a great job for me. So yeah, it's thin as 0.6 mil so far. Of course, the size of the port changes, the depth. How many are in there, of course, change, of course, the size of the board, thickness of the ring. We have different ratios depending on what size it is. But yeah, like I said, as thin as 0.6.
Okay, thank you.
Billy,
Mm-hmm.
Can you explain idle quality and how duration versus LSA affects it?
All right, well, idle quality is going to have to do with that overlap triangle that we showed graphs of. Now, the thing that there used to be this big debate, and the whole idea was it overlap duration that made the issue, or was it the area under the curve, the inch degree squared, what's the area under this overlap curve? And the answer is both of those matter, and there's more to it than that, because you could have two triangles, overlap triangles, that had the same area under the curve and the same events, but had a different shape. So if you imagine a triangle like this, if I skew it this way and skew it that way, I've still got the same area, but I've changed where it's located. And so not only is it overlap area, but it's where is the area? We know if we put a lot of that area too far back, that we can get some really weird stuff going on. But the shape of the intake opening and the shape of the exhaust closing, we did a camshaft, a CARB approved camshaft for an LS, And when they took it to the SEMA garage and tested the emissions lab, it actually was more overlap duration, more overlap area, but it was, I think, about 15% lower emissions than stock. And we're given 10 on the other side. So we were 25% lower emissions than we needed to be during startup before the cats lit. And I was kind of proud of that. So there's some things you can do with shape of overlap that change that misfire. And that's your major thing that you're seeing with, with the lope and the idle and everything like that, but also the carb stuff. So I wish it was as simple as, it can be 48 degrees at 6 thousandths. Okay, that's any number, or it can be this inch degree. It's really, really interesting how engines behave. And then the rod to stroke ratios come into play and compression comes into play. And even how the port layout, a Hemi head is different than a wedge head, and a pent roof is different from, a splayed valve. So every different combustion chamber, the valve angles can play into it. It's amazing the valve angles relative to one another, and the seat angles can play into it. The steeper exhaust seat can handle more overlap. There's some pretty bizarre. That's a much deeper question than probably the person thought. If you'd asked me 20 years ago, I would have given you a really simple, direct answer, and I would have been wrong.
Great, thank you.
All right, next one's for Ben. Can you please discuss in detail the proper grounding required for both steel body and fiberglass body vehicles regarding EFI systems?
Oh, maybe that's a tough one. Let me see if I can clear my screen first. So the grounding requirement isn't really any different for steel versus fiberglass body. You still need a clean, good path to ground. The only difference is it's harder to find that on a fiberglass bodied car. So traditionally, you're going to have some kind of ECU source that goes directly to the battery. A lot of guys want to cheat and go, well, I'll put this, battery lug here on the frame, and then I'll jump from there to the battery and whatever. And you can certainly get away with it, but more often than not, things crop up because of issues like that. Another big one is to make sure that you are tying the engine. A lot of guys want to tie the two cylinder heads together, and then from there, like a daisy chain, directly to a good clean ground source on the chassis. So, those are some things. The biggest one that gets missed more than anything else, though, is earlier I showed the guys these really high-powered, what they call smart coils. Lots and lots of companies are buying them and using them. They're typically made by either Mercury Marine or some knockoff Chinese place that's making them look the same and then selling them cheaper. But my point is, there's an extra ground wire on these that people often ask about. I go, what's that for? It says it needs to be grounded to the cylinder head. Why do I care? And they'll ground them somewhere else, and it has caused all kinds of problems. So we need a direct high current ground path from these coils directly to the cylinder heads, regardless if it's a tube chassis car or a stock chassis, a vehicle or whatever. Grounding is one of those things that's always important, and it's always missed. Doesn't matter what kind of car you have, the cleaner the path can be. And what I mean by that is the less breaks in the wire, the less connectors you're using along the way, and less interruptions between the thing you're actually trying to ground and the actual negative terminal on the battery, the better off you're going to be in the long run.
Super, thanks, Ben.
Sure.
Okay, I got a question for Lake. Lake, can you please provide an example of the difference in viscosity between the aforementioned 6,000 RPM engine and the 11,000 RPM engine? What is a typical oil viscosity in each?
Oh, cool. I was just actually answering that question. That guy probably that's what I was doing over here. I wasn't ignoring. Okay, so can you show me? No, we want to keep this place where everybody can see everybody. So an oil without polymers, okay, base oil isn't going to change viscosity with any change in RPM. So the viscosity is going to be the same. Remember, Stribeck is viscosity times speed divided by load. So if it's a straight base oil with no polymers added, the that viscosity is going to be the same even with increased RPM, increased speed. So what will happen is from say 6,000 RPM to 11,000 RPM, the film thickness will increase. The viscosity, which is resistance to flow, that's I think a lot of people think viscosity and they think thickness, and that's not the case. Viscosity is just a measure of resistance to flow. The more resistance to flow, the greater the speed. Those combined together, greater film thickness, thicker hydrodynamic wedge. So that's what you'll see. Now, the other slide I had up where we showed the shear thinning, when you add polymers to the oil, those polymers are like rubber bands, right? You stretch it out, what happens to the section you stretch? It gets thinner. So depending upon the type of polymer and the amount of polymer, the oil can shear thin to basically try to maintain that same film thickness, even at higher RPM. That way you don't give up on horsepower. So that's the kind of idea, you know, so that you can not only adjust, say, the SAE viscosity, you're also changing how the polymer thins. Ben, I'm thinking about your small block Ford, and we don't know how much power that oil change made, but going from, say, a 530 with one type of polymer, an amount of polymer, to a 520 with a different type of polymer and amount of polymer, saw a difference in how much power it made, especially up top, and that was using both of those levers there to improve efficiency.
Great, thank you.
Elaborate on what he saw there. That's fine.
Well, I was trying to think, like, what do I know that you don't? But it's rarely very
Lots.
much. But, we did try a bunch of different oils on that engine, both on the Spinal Tap project, and like everything else, everything you do, you learn from, and it gets applied to the next stuff. And so the Ford engine ended up benefiting from all the stuff we learned on Spinal Tap, and some of that was oil. And I think we tried some 30 weight stuff when we were breaking it in. We were trying a couple of different 520s, and I think we ran some 0W2 in that as well. And you know, you're looking for every advantage you can find. We played with oil pressures, we played with oil flow, which is really the same thing based on the way we did it. But you know, we were changing the springs in that engine for the oil pump bypass, you know, the overflow. And yeah, the oil absolutely made a difference. The question that was in my mind, and probably yours and everyone else too, is, well, did we give up any durability or reliability for that power? And so after we'd made about 20, which is a giant number of runs on the dyno for an engine like that. Typically those engines only make 2 or 3 and they go in the box and go to the customer, you know. So after we'd made about 18 or 20 passes with, I think, 3 different oils, we pulled it off the dyno and we took it down and we're like, oh gosh, what are we going to see? And to be honest with you, we just put it right back together with the same bearings and everything, and it was perfect, and we just kept right on running it. So all of them provided the required protection that we needed. But there was definitely some changes in power between 0 to 520 with chemistry and 30 weight. So I think probably on that engine we're probably talking just barely into double digits. You know, we're talking singles most of the time, but the fact that you could change oil and find 5 to 7 horsepower is unbelievable in an engine where we sometimes spend weeks looking for 2.
Mm-hmm. All right, super. Keith, I have another one for you. This gentleman's asked, ring gaps for turbo blower application. Is there a rule of thumb, such as so many thousandths per inch of bore per inch of boost?
Really kind of comes back to what we talked about earlier, tune-up. As a general rule of thumb, in most mild applications, we're not talking, 70 pound of boost on nitro, that kind of thing. You're going to run about just a 6,000ths per inch of bore is a general rule. That's a nice safe place to be, top and second ring for most applications. Really comes back to tune-up. I have guys that run very, very high boost levels that can surprisingly run very tight end gaps, but they have a they're very, very conservative on their tune-up. They just don't hurt parts. They're not knocking head gaskets out of it. They're not killing plugs. They're just very conservative. So as a general rule, about 6.5 thousandths per inch of bore, top and second for most what I call general applications. You get into the extremes, again, 70 pound of boost on nitro, that kind of thing. You may be as much as 8 thousandths per inch of bore, just depending on how it's tuned. Like we talked about before, kind of look at the rings coming back out of the engine. Look at how they look. Check your end gaps. The engine's kind of again, like the Oscar and the dog whisperer. It's talking to you. If you're paying attention to everything coming out, look at the gaps. Look to see if you see any budding signs on them. Record all that data. If it comes out, you don't see any budding. Next time you build it, tighten it up a couple thousandths. You probably get away with a little tighter gap. If you're seeing those little shiny witness marks on the end gap, go a couple thousandths bigger. But it's really about observing everything coming out. How do the rings look? How's the free gap? Do you see any signs of budding in the rings? But again, as a general rule, about 6.5 thousandths per inch of bore will generally get it.
So Keith, I got something I want to ask in relation to that same thing. So we don't get to play with a lot of, this probably sounds terrible, but we don't get to play with a lot of normal like stock stuff here. Everything we do is typically super high end and racy. And, we tend to chase, the groove to ring relationship a lot, as you and I have talked about this kind of stuff a ton, and ring gap and, the cylinder finish, and Lake and I worked on all kinds of stuff. But one of the questions that's been rolling around in my head for a while is how much relationship is there to temperature that the ring gets, which is, we know, is directly proportional to ring growth, between the piston design, not design, but makeup, a 309 hypereutectic alloy versus a 4032 versus a 2618. So we know thermally a 2618 grows way more than, say, a hypereutectic 309. So how does that affect a guy's ring gap and sort of ring to groove clearance? What do you guys do differently for that stuff?
Well, as you stated, the hypers, the downside of the hyper is, it's brittle, but as far as stability, it's phenomenal. It's absolutely fantastic stuff. If it wasn't so brittle, it just doesn't grow. It's stable as hell. The grooves don't move around. 2618s, 4032s. Like we say, they like to move around a lot more than the hypers do. So the hypers, you can actually run surprisingly tight ring to ring groove clearances. As far as end gap goes, don't really see a big difference end gap material to material. That's more about the actual ring temperature expansion of the ring. But ring to ring groove, that's definitely where you see the difference. The hypers, you can run surprisingly tight ring to ring groove clearances. The 18s and the 4032s grow a lot more. So you can obviously have to adjust the gaps for that. But I definitely like the hyper. You can run a lot tighter.
Yeah, cool.
Okay.
Super, thanks.
Question for Billy. When selecting a camshaft, which is the more significant spec to look at? Advertised duration or duration at 50?
Well, definitely the duration at 50. And the reason that is because cam designers lie. There's not a like hard and fast SAE spec that you can take somebody behind the woodshed for. If you say it's 288 advertised, and it's really 289 or 290 or 292 at 20, that's just the advertised spec. So really the advertised specs, if it's within a cam company and it's within the same generation of guy who is doing it, they might be halfway trustworthy. But if you're going to take cam manufacturer A and cam manufacturer B and look at advertising, you can't really tell about what's going to do what. And one of the things that we're starting to understand is, like when I showed you that, when I was running through at the very end, I showed some power differences at that test that Jeff Smith did with Engine Labs. And he was shocked because the 6,000 spec on the camshaft that made more torque and more power, more everything, it was bigger advertised duration, even though they're the same at 50. So normally you'd think, okay, if it's bigger at advertised, it's going to be a poochier cam, it's going to make less torque, it's going to make less power, it's going to be worse everywhere. But what you can't see is how that split of the advertised duration is, meaning that it was slower opening and faster closing. And that early opening side that we added to advertising, we had 4 degrees there, and it did absolutely nothing negative. And that sort of plays back into what we talked about, the overlap triangle. But when you look at the cams, they're all the same duration at 50. if they're degreed in with the same valve points, they should make peak torque and peak power. Where they peak should be within a few hundred RPM of one another. Now, how much they make, that can vary, but those 50 thousandths valve timing events, that exhaust opening, intake opening, exhaust closing, intake closing, those 4 events, if those events at 50 thousandths lift are about the same, where it makes power will be pretty close to the same spot. And I did like, before I miss it, the thing that Keith's saying about listen to your engine, whether it's something where it's motor oils, your EFI system, your camshaft, your valve events, or your rings, or your pistons, or your bore. It's amazing how much engines want to do the right thing. Half the time, we're trying to hold on to the reins so hard that we're trying to drive them someplace they don't want to be. If you can listen to your engine and really get to pay attention to it and get to know it well, there's a lot of crazy things that it's trying to tell you, and the great engine builders get that. And guys like us sort of pick it up along the way just over time.
I have a bunch of valve strings that would agree with that.
Yep. I told somebody about that low shot being like the happy wife, happy life. You know, if you're going to ask a whole lot about the valve spring later, you better treat it nice early. Yeah. You know, I've tried that with cam designs. I've tried that in my marriage. Being good on the front end is a good idea regardless.
Stacking up brownie points.
Yep.
Okay. We do have one live question here that is for Lake. So Mike, I believe is his name. We'll turn it over to you.
You there, Mike? Caller, you're on the air.
Well, looks like we're having technical difficulties with that again, but he did type a question.
Temperature?
Yes.
Am I on now? Okay,
Yep.
sorry.
Yeah,
we got him.
This is a really simple, basic question. We're talking about 220 degrees oil temperature.
Okay.
Where is the ideal place to measure that?
Ideal place to measure that is what oil in. So oil going into the main oil gallery, that's what the engine is going to see. So that's what you really want to where you want to measure. If you measure on the oil out, it will be quite a bit hotter, and that's okay. And that, you know, it's fine for it to be hotter on the way out because it's oil's a coolant. It's not just a lubricant. You know, one of the questions I had answered was, do you ever see an engine without oil? No, because this oil is not just a lubricant, it's also a coolant. And, you know, so it's important to have that ability to carry away the heat. So really, the critical temperature you want to look at is the oil going into the engine. I would rather use that as your point to measure from.
Okay. I've got a question. This one will be for Keith. It's basically from a previously asked question by someone else, but they're asking how much heat from the ring is absorbed by the piston? What are the various methods of ring temp control? Is it oil, cylinder walls, piston material? What's your feeling on that one?
Again, cooling of the underside of the piston, as far as, you know, ideally you want all the heat to go back through the ring, get it out of the piston, into the ring, into the wall, out to the water. But the most positive thing you can have as far as effect on the piston is oil underneath the piston. Oil is a coolant. If you look at the modern race engine, NASCAR in particular, last time, I don't get to look at RO7s a lot, but the last time I looked at an RO7, it had 5 oil jets underneath there to use as a cooling system for the piston. So oil is the most common coolant for the piston. There are diesel applications out there today that actually have pathways through the underneath side of the dome, you know, underneath the bottom side. This one's kind of got a hole in it, but through the actual pin, comes up around the side of the pin, around and back down as an exit to actually get oil underneath the bottom side of the dome. The piston's actually hollow, using that oil as a coolant. So oil is that's your best line of defense to cool the piston. Hopefully that answers the question.
Super. Yeah, thank you.
Actually, I'll go one up on you, Keith. If somebody
Thanks,
really
brother.
wants to know,
There you go.
there's a book called piston ring tribology, and it actually shows Keith's example of that diesel ring that's doing it. And in this thing, it actually says, and this is different research papers, it says that the majority of the cooling or the heat transfer out of the piston is through the oil, not through the piston ring. You know, and one thing we did at Gibbs, we actually worked on the selection of base oil that actually had the highest specific heat capacity to pull heat not only from the pistons, but also from the valve springs, because that's another big source of heat in the engine. And anybody that has a Spintron knows that even without combustion, you can get the oil pretty hot, can't you, Billy?
Oh, you can make bad smells from cheap oils. You know, one of the things that people don't really think about too, if you take it something like what Duttweiler runs at the salt flats, you know, in the Speed Demon, how much fuel he runs through the engine to cool the piston. You know, there's a lot of, you think the tune-up's conservative, but that's running on methanol, so he's running a lot of fuel through there. I'm pretty sure it's so that it makes it to the 5 mile mark.
Yeah, heater vaporization works really good to cool things
exactly.
off.
When you're putting, you know, if you looked at his fuel pumps, looked at his injectors, and did some quick math, you know he's not making that much horsepower. Yeah.
Just to touch real quick on what Billy said, you know, in a different world, sprint car engines, the amount of fuel that goes through those things is insane. And as you said, are we getting the energy out of it? No, but we can run a smaller radiator and a smaller oil cooler, which means less weight out on the nose of the car. And those guys are all about where the weight's at. So we'll pour fuel through it, create some kind of ring seal havoc to take 2 pounds off the nose of the car. But that's,
wait,
that's what they do.
You mean a crew chief would intentionally make the engine run worse than it's designed to do just to make the car handle better? No, never happened. That won't
Inconceivable.
happen on Sunday.
Keep using that word.
We should have Doug Yates in here, right? It's crazy to hear Doug talk about how just insane, you know, they run these cup engines anymore just for the aero benefit. You know, that engine's not running anywhere near what its real potential is in terms of, but because of the having to accommodate for the aero part.
Yeah, I mean, think about like Keith was talking about those piston squirters. You almost couldn't run one of those cup engines without those, but in a drag race engine, we take them out. We don't want that because that's windage and oil that's flying around in the crankcase. And it's like in the cup stuff, you know, you got to finish or you can't win. And we don't have to go 500 miles. We have to go, you know, 1,320 feet. So, you know, the application is always the king, you know what I mean? Like whether it's Billy choosing a lobe shape, it's a valve spring, it's you guys with rings or oil or whatever, application matters almost more than anything else.
Yeah, there's a lot of specific heat in those components. So, you know, that piston's absorbing heat. You know, in a pro stocker, if you're at wide open throttle by more than 7 seconds, you've lost anyway.
That's a good point. And it all comes down to the engine building. Damn, if we just didn't have to put them in the cars, we could build the perfect piece.
Right.
Exactly.
Okay, we got time for one last question. And this is actually for, it says Billy or Ben, but we can do Billy and Ben. On a valve spring shape, conventional or beehive, which is better for a higher RPM engine?
Well, I've never seen a beehive work at real high RPM. We tried to make a beehive spring for a pro stocker, and I believe it got to 10,000 RPM, and Elvis left the building. You know, it was a beehive outer and a cylindrical inner, and the beehive broke and sent shards through it. So, you know, and that was the biggest wire beehive. That's the biggest beehive we'd ever made. But generally, the beehive technology is about minimizing mass and letting you do things you normally can't do in a lower RPM, lower lift deal. About the highest RPM beehives I know are probably used in like a Ford Coyote deal, and probably about, what would you say, Ben, for a factory shootout car, a little over 10,000 RPM?
Yeah, so on the Ford stuff that I worked on, they're 10.1, 10.2, something like that is what the Fords go to. Yep.
But
But I
if you
think
look at the NHRA Pro Stock bike, they run a real lightweight dual. Now, if we could make a conical spring for a Pro Stock bike or a Coyote, I think it would be a better piece. But, you know, setting up to run a conical, you probably are, to make the first conical spring, you probably have tens or more thousands of dollars in setting up the equipment to grind it, because it's hard to hold a conical spring straight in a grinder. So that's why you don't see short run conicals. You know, you've got to really commit to make a few thousand springs.
so. Billy, we see a lot of guys that ask questions here. I think there's a misconception around the industry about the difference between a conical and a beehive. Everybody just assumes they're the same,
Yeah.
but tell us a little bit about why they're different.
Well, a beehive really was just to take some weight off the top of it, so you can make the retainer light. But basically, the beehive doesn't nest, and it's got 2/3 of a beehive is a cylindrical spring. You know, a conical spring, every coil is different, and a conical spring, every coil nests. So a beehive really is kind of not a conical, and it's not a cylindrical. It's sort of a hybrid. But the nice thing about beehive, it's much easier to make because you do have that 2/3 of it that's cylindrical that makes it quite easy to hold in the grinders and everything like that. So if you ask somebody at a spring manufacturing plant, do they want to make a cylindrical, a beehive, or a conical? They want to make the cylindrical. They'll make the beehive, but you start talking conicals and that you get called names and stuff thrown at you and everything, and eventually you just have to give them Scooter's front of the check, back of the check speech, and then they will kind of go for it.
But obviously there's huge benefits that we've been learning about with the conicals.
Yeah, if you can make it and you get it right, you know, and like we talked about, you saw my slide how I had that spring. You've seen them in real life, where you have to go in there, and when you do a conical, you have to make sure each spring is sharing its amount of the load that it can handle, that each coil is equally stressed. And that type of research in it, you just can't really throw one together.
Right.
That's why the number of SKUs number of part numbers is so small for conicals.
So when just since we're talking about it, when we first started doing the conical stuff, we didn't have a lot of the low shock lobes yet, and so they didn't like that very much. Do the traditional cylindrical and beehives fare better without a low shock lobe? I mean, we've obviously had in the last 3-4 years, giant strides, but you know,
a beehive probably is more like a conical in that it would like to be treated a little nicer on the opening. Some of the big triple springs you saw in NHRA Pro Stock, you know, 1,500-pound open guys, and even the 1,200+ pound duals you see in drag racing, those things are kind of like big gorillas. And if you can imagine, you know, you can slap those pretty hard without totally pissing them off because they weigh so much. You can't really get them excited. You know what I mean? So they're not as concerned about the low shock. As you start going to lightweight, NASCAR style conicals, NASCAR style duals, you start looking at the dual springs they run in today's modern dirt track engines and, you know, World of Outlaw type stuff. Those small diameter duals, they're very sensitive, and conicals are very sensitive. But the really big, heavy, old school stuff, it jiggles regardless. So, you know, it's just, you slap it, it jiggles a little bit more. Kind of like a big offensive tackle named Fred. You just hit him and he goes, okay.
Great. Well, I just want to thank all you four gentlemen, Ben, Billy, Keith, and Lake, taking the time out today, doing this super webinar for us. It turned out fantastic. We did it with no hitches, which is great. We had no technical difficulties. So again, I want to thank you guys for taking the time out of your day and doing this for our group that was in attendance today.
Privileged to be here.
Yeah, thank you. It is great. These are good friends of mine, and I really enjoyed being on this panel today. These are wonderful men. It's enjoyable to be talking with them.
I
Yes.
appreciate being in the company of these guys. Like I said, truly best at what they do. And I can only thank all of them for letting me be part of this.
Yeah, and I just want to say thank you guys for all your promotion and helping out with this. I mean, this was put together kind of a little bit at the last minute, and you guys made it a huge success. So again, very appreciative. And if there's any questions, I mean, anybody out there that still has questions, I mean, all of these guys are very accessible. So by all means, please feel free to reach out to them and ask any questions that you've got. And what we'll do now is I'm going to go over to Amanda here real quick. She's just going to wind things up and tell everybody how you can contact us and how you can do the survey. So guys, you have a good Friday night. You have a good rest of your weekend. And I know Ben and Keith, you probably got a couple hours left to put out yet, but the rest of us we're going to have a beer. So thank you very much, guys. Appreciate it.
Hey, I'm in. It's only
I was saying while we were talking, so it doesn't matter. We're even.
All right, thanks again, everybody. For those of you who will be signing off here, you will get a survey that pops up. Please take a moment and fill that out. Let us know how we did. If you have any questions for any of our presenters, you can pop those in there. Also, tomorrow you will receive a link to the recording of today's super webinar. That is yours to use as you would like. Go ahead and forward that on to other people or view it. If you had to duck out for a little bit, you can go ahead and view whatever you missed. And then lastly, if you need to reach anyone here on the AERA team, you can get a hold of us at 815-526-7600, or you can email myself at amanda@aera.org. Or even if you reply to any of the emails you get from GoToWebinar, those come to me as well. So if you have any other questions for anyone or need to get a hold of us for any reason, you can go ahead and do that, and I can forward them on as needed. So thank you again, everyone, and we hope you all have a great weekend.